high-density non-volatile SRAM design using resistive memories and selected devices acting as technology assist. And before I begin, I would like to thank with you.
My name is Naoto Horiguchi from IMEC.
So this is
I
the
will
outline
present
of my talk.
advanced
First,
architecture.
I will give you a brief motivation behind the non-volatile SRAM design. Next, I will present
My name
prior
is
work
Naoto
and
Horiguchi
present some
from
of
IMEC.
the
Hi Manoj, are you there?
Hello, good morning, sir.
Yeah, good morning Manoj. So my voice is audible properly?
Yes, sir, you are audible properly.
Okay. I just want to check. So Professor Mustafa, he will be the first speaker in this panel, right? In this session.
Yes, sir. And I have shared a single compiled file along with you and Professor Shuri and Professor Mukherjee.
Yeah.
Those are
So
the contents
the
on the speakers and their bios.
yeah. So I'll just read the bios before we start, right? So I'll do that.
Okay, sir. Okay.
Okay. So I hope he will join in time, and we could maybe start. We have. So I think the speakers have been informed to join 10 to 15 minutes earlier, right?
Yes, sir. They were supposed to join at least 20 minutes ago before the actual session, but no one has joined so far.
Okay, I think he
Maybe.
might have received the information, right? Huh.
Yes, sir. They got a separate mail.
Yeah, I saw that mail also.
Yes, sir.
Okay, so we'll wait till he joins.
Yes, sir.
Hey, Manoj?
Yes, sir. Please tell me.
Yeah, so is it possible for you to, in the screen of this WebEx meeting, can you put this technical program of this session for next for few hours? So,
Yes, sure.
yeah, then it will be better, right? If somebody enters, you will see that, okay, well, this is the hall for this session.
Yes, sir. Sure. ICEE team. Hello.
Professor Mustafa, good morning. So this is Nihar and session chair for this session. So thank you for accepting our invitation to speak in this session. So I could not hear you, Professor Mustafa. So I could see you, but I could not hear you. So Manoj?
Yes, sir.
Can you hear Professor Mustafa? Because
No,
I
sir,
couldn't hear.
no, he is not audible.
Hear me now?
Yes, yes. Yeah,
Yes, sir.
thank you. Yeah, now I could. So how are you doing?
Good morning, everyone.
Yeah, good morning.
Okay, I'm going to share my screen just to be sure that okay. You can see my screen, right?
Yes, it's clear.
Okay, very good.
So so we have 4 minutes to start. I hope the other session is going on. So I hope that will be over and the participants will come to this session.
No problem. So how many attendees so far?
So I don't see anybody. So Manoj, do you have any idea?
No,
Sir, we won't be able to see here. Actually, there is another link for the delegates where the actual session is going on. This is for the volunteers and speakers only.
Okay.
Yeah, but we should be able to see, right? If even if they cannot attend this, should be able to see, right? Huh?
I think you can see parallelly where that delegate link is provided.
Okay.
Okay. So the talk is about 25 minutes, followed by 5 minutes Q&A.
Yeah, right.
Okay.
So actually, there will not be Q&A. Means so the attendees can ask questions through their chat box. So I'll just read those questions if I have access to the questions. I hope.
Okay.
Yeah, because yeah, this method is also new for me. So I'll see how it works today.
It's gonna be fine.
That should be. So Manoj, there will be questions in the chat box, right?
Yes, sir. Yes, sir. All the questions will be here in chat box, and if any other participant is asking any live question, then they can do after the talk is over.
Yeah, but for the participants to do live questions, they have to hear, right, in this link.
Yes, sir. Yes, sir. In this link, in chat box, we will see all the questions. So, can you see the chat box?
I could see the chat box, but yes, I could see the chat box. I
Yeah.
could even, but yeah.
You can see the chat box also. It's fine.
Yes, sir. All the questions will present here only.
Okay. So Mandar, you joined?
Hello, I'm here.
Okay, so you will be the next speaker, huh? So Manoj, you could tell me whether the other session is running or it's over, right? That's
Sir, I think the inaugural session is going on there, and within few minutes it is going to end. Hello, can you hear me, sir?
I can hear.
yes. I can hear you, Manoj. So it will take another 15 minutes for the inaugural session to end.
Not that much time. Let me check what is the status currently there. Otherwise, we can start the talk at
No,
our
I
actual.
don't. Means we could wait for 5 minutes because I want the participants to come from the inaugural session to this session, right?
Yes, sir.
So
Sir.
all the parallel sessions, so they should go.
Yes, sir.
So Dr. Mustafa, we may have to wait for 5 minutes.
That is fine.
Yeah, thank you.
Hello, sir. Sir, the inaugural session has ended, so I think you can proceed with this.
Hello, Professor Nihal.
I'm listening. So yeah, so we could
Yes, sir.
start.
I think the inaugural session has ended. Now we can start.
Sir, the inaugural session has ended, so I think you can proceed with this.
Okay. So, good morning, all of you. So, we'll start our session. This session is on emerging logic, memories, and neuromorphic devices. So, we have uh, 4 invited lectures in this session and 1 oral presentations. So, these invited lectures will be given by distinguished speakers. Our first invited lecture will be given by Professor Mustafa from UC Berkeley and KAUST. So let me welcome Professor Mustafa. Um, I'll just read a brief bio of Professor Mustafa before he starts his talk. So Professor Mustafa is a jointly appointed professor at UC Berkeley and KAUST. He had a rich industrial experience and had previously worked at Sematech and Texas Instruments. His research is mainly focused on heterogeneously integrated CMOS electronic systems for multidisciplinary applications, with more than $50 million support from Boeing, Lockheed Martin, GSK Novartis, McLaren, Siemens, Aramco, SABIC, Intel, IBM, Texas Instruments, Samsung, Panasonic, TSMC, UMC, HP, and US Department of Defense. He has served as lead author inventor of more than 450 journal and conference papers and international patents, for which he has received 45 plus international awards, including Edison Awards 2020, several IEEE Outstanding Achievement Awards, and UT Austin Distinguished Young Alumni Award in 2015. Recently, his lab, Innovation Bluefin, has received the Best Innovation Award in the world's largest consumer electronics show, CES 2020. He is a fellow of IEEE, American Physical Society, and Institute of Physics UK for his contributions to flexible and stretchable CMOS electronic circuits and high-k metal gate planar and non-planar CMOS electronics. So with this, I again welcome Professor Mustafa to present his talk. And today he will talk about high-performance computing on physically flexible CMOS platform. So it is to you, Professor Mustafa.
Thank you, Nihar, and thanks for inviting me. My talk is going to focus on the mainstream CMOS electronics, but a version which is which in the past it was thought that it's not possible because it's so let me actually show you something that over the time the electronics have evolved not only within its domain of performance or the energy savviness, scaling, connectivity, or cost. These are the key metrics which have been associated with the scaling of the electronics technology, but more importantly, to bring them to at our convenience, to make them portable, to make them multifunctional. And that's why we see from desktop to laptop to tablet to smartphone, we have seen that how that has evolved. Now, the question is that what are we expecting going forward? So one of the emerging applications that we think of is having functional sensory systems integrated to this kind of computing. And if you are using one of the smartwatches, then that definitely has lots of body vital monitoring processes going on. And what we expect as an emerging applications frontiers are the automated vehicles and robotics, Internet of Things. So anything you put the smart wording, it becomes, it needs to have some kind of sensory system. Healthcare for wearable health monitors. If you look at the top left portion, you can see a Texas Instruments based one of the functional system, which includes a temperature, motion sensor, temperature sensor, humidity sensor, pressure sensor, light sensor, and they have a multi-standard wireless multi-core unit, the MCU, and then there is this antenna and the connector. Now, overall, this whole system, it has its own footprint and it is rigid. You cannot bend it, and they are fairly complex systems. Now, the question which has driven me in the last 7 years is, can we actually have a flexible version of the same thing without losing any of its performance, functionalities, reliability, cost effectiveness, energy efficiency, nothing, okay? So when I look at what is really happening, then you can see on the top right portion that exactly what TI, this multi-core system has, the same version is refabricated in our lab with the silicon CMOS technology, where you can see these antenna. This has its own, these are the batteries, and then this is the MCU, and this is the BLE, and it really works as a coin architecture, which means that you can have the sensors on one side, and all these chips which are interface related, they are basically going to be embedded within the middle layer, and then the other side is going to have the antenna as well as the energy harvesting system. So now every single component, unlike any other flexible or stretchable electronic technology that we are aware of, every single component is essentially here is flexible. And that's why when I look at the key metrics today, from performance, energy efficiency, scaling, connectivity, and cost, we carry them forward, but then we redefine these, that what is going to be the key metrics for our electronic technology going forward. That's going to be depending on the functionalities, because our application range is going to vary beyond our computing, communication, or display technology. They have to be reliable, because if you think about the automobile electronic technology, they have to be reliable for 15 to 20 years, unlike our smartphone, which we often change in every 3 to 4 years. And since we are talking about the electronics which we are going to carry, either implanted or wearable, or even in our pocket, we do definitely need to make sure that they are going to be safe enough. So if we take these important metrics, then we have to basically work on their cost effectiveness. Otherwise, it's going to be only accessible to a few number of people compared to the rest of the world. Okay. So one areas of like that we heard about the flexible electronics, I would like to actually point out to some of the very the prominent one. One of these is the LG or Samsung. They have their flexible displays, flexible solar cells. This is from Alta Device, one of our colleagues, Ilya Yavlanovich, the 3.5 flexible solar cell technology. You might have heard the Samsung Galaxy Fold. As far as I know, that in India, they actually released a few of these. This is exactly not flexible. This is the carefully hidden micro hinges are making it sure. So it's essentially only the display itself is the continuous. It's similar to Motorola Razr. And one of these our own, where we have embedded flexible series of LEDs, red light LEDs, which are powered by the micro lithium ion battery, so that because the near infrared wavelength of light can help in enhancing the bone regeneration. So instead of using the metallic dental braces, this way the dentist, they can actually pre-program, and this can provide us with the digitized, far more precise the dental care that is required. So this would not have been possible if we didn't know how to actually make the flexible electronics, or in my case, transforming the traditional rigid electronics into flexible one. Why? Because they're mostly inspired by nature. Most of the objects that we deal with in nature, including ourselves, they have asymmetric terrain of surfaces. They're soft, and that's why we need to actually cover large area electronics. We need to deploy them everywhere. That's why ubiquitous. They have to be implantable, and then definitely the stylish electronics. What are the challenges? Integration is a major issue. Reliability of them, whether they are going to be not only the electrical reliability, but also the mechanical reliability, and they have to be cost effective. So if we take them and look at where are the flexible electronics today, then these are some of the prominent one: IMEC, Illinois, San Diego, Holst, Northwestern, UC Berkeley, Javis Group, Anarias Group, Stanford, Zinan Bao. You can see then on every single of these demonstrations, you definitely have these rigid ICs. So they are packaged dies. Now, many people are going to argue, and I agree with them, that they can scale them down. But if that is the case, then Apple Watch has already won the game, and there is no reason for us to pursue flexible electronics, except for the fact for display technology or for high energy harvesting. So the question is that why do we need the CMOS ICs? This is mainly for data management. No matter the data that's coming from the sensors, we need to make sure that they're processed, they're communicated, they're stored. And these are some of these, as you can see, that they're basically ceramic packages. But obviously, people will argue that there is RFID, radio frequency, the detectors, which are basically you can have in flexible format. However, we have to ensure that they are not for data management. They have a small library, a small memory, and they mostly use in barcode technology and any other places to ensure as a comparator so that it can actually tell us yes or no decision. Okay. The question then that are the chip sizes are shrinking? Not exactly. If you look at the Samsung, SK Hynix, Micron technology, you can see that the chip size actually is varying depending on the complexity, and the more and more that, as you know, that we need more and more performance, more functionalities, the number of chips and the size, they are not actually going down. They're rather increasing along with the big data. So now take an example that let's say that we would like to monitor our heart rate for the 7 days continuously and the ECG condition. What we get is, depending on the sampling frequency per hour, per day, per month, or per year, we are basically generating a lot of data. Even if we think that, okay, so we are going to transmit the data immediately to our smartphone. Our smartphone, they're coming today with the 64 GB or that kind of, or 128 GB data set. You can easily fill this up with your apps and movies and the songs and photos. But beyond that, the rest of the data that is actually the space that is available, that is not sufficient. So we really have to come up with electronic technology, which are definitely high performance, their high memory capacity, the seamless communication, all these things. But now I also want them to be on physically flexible platform. Okay. So the question is that why do we need silicon for this kind of data management? We understand that we need to do the data management. We are using these encapsulated rigid ICs. Well, the rigid ICs contain not only silicon, they also have, sometimes they can have the germanium, gallium nitride, silicon carbide, 3,5 base rigid bare dies. But bulk monocrystalline silicon 100 orientation is used in 90% of the electronics, because it's not their best, but they're optimal semiconductor. They are relatively low cost, and it has been thoroughly studied. So they essentially, they are really a mature technology. Now, if I compare with the state-of-the-art silicon FinFET technology with the carbon nanotube transistor versus a two-dimensional moly-disulfide, I actually chose a modest grade silicon FinFET, whose performance is not the most spectacular one, but I chose with full conviction the best performing ever carbon nanotube experimentally, as well as the moly-disulfide. And when we compare, you can see from the delay per stage and energy per cycle, then one way or other, the traditional technology like FinFET with silicon stands out. So the only challenge that they have, that they are not naturally flexible or stretchable, okay? So that's why if we can make a fully flexible CMOS electronic system, then that's going to be useful as well as impactful. And that's the reason that the question is that why we are not making them. Well, if you look very carefully, after making that 1100, 1200 steps to make a transistor and then wiring them up through the interconnect levels to a M19 to M13 to M3, whichever level that we go, then we dice them using mechanical sawing, and then we align them, we house them, we wire bond them, we seal them. So there's a lot of mechanical processes are involved. So, and this technology has been established as a sophisticated one, but a mature and reliable one, and that can handle the rigid wafer dies. And the question now is, can the CMOS processes be effectively used for ultra-thin flexible substrates or die handling? Now, the question is, I have to go and check the fundamentals. If you look very carefully, silicon is actually a rigid and brittle material. It's, you can see here that as we are reducing its thickness, obviously its radius of curvature will go down. We can actually flex it further. So basically, if we thin down a material system, its flexural rigidity goes down, they tend to become flexible. However, because of the nominal strain constraint within silicon compared to graphene or other flexible PCBs that we can think of, that silicon actually is not the right choice of material for this kind of abrasive CMOS processes, okay? A few example can be, if we reduce the thickness of our silicon to 8 micrometer compared to 500 micrometer or 750 micrometer that is being used with the rigid wafer, then within strain of 1%, yes, we can see them that they're still intact. But as we go down below 8 micron, then we can see that they become unstable. And here you can see that they are actually becoming wavy, or means like they are taking a shape of like potato chips, like with lots of balls. So these are not usable for any tracker. Okay. Let's say that, can we do wire bonding? Well, to do wire bonding, we need to actually have like some sort of bonding force that has to be applied. Now, if you look very carefully, that if like, you know, that when we are doing with a standard rigid substrate, yes, the principal strain is within the limit, and it's not going anywhere close to the fracture strain, and we can do it very well. Up to 9 micrometer, we can do it, but be less than that, they are going to actually face the fracture, and it's not going to be useful, okay? So flexible wafers or dies, they are ultra thin, and that's why they are fragile, and they're basically incompatible for the state-of-the-art processes. So the question is, we would like to use silicon or gallium nitride. They are high performing, but they're rigid. If we make them flexible, then they become vulnerable. And then we have to deal with the mechanically challenging the CMOS processes, especially for packaging. So how we can actually converge them in a meaningful manner that we can save the performance and everything, and still we can make them physically flexible, and people can use it, okay? So one of the questions that has intrigued everyone, that how we can actually make silicon thin or flexible. Well, I think I will go back to one of the historical paper by Ilya Ablanovich that was published in 1987, where he mentioned a paper which is 10 years before that, pretty much when I was born, that in a little notice paper, two Japanese researchers, they actually show the first ever lift-off process. They made essentially flexible 3-5 material, but they didn't claim it, okay? So initially, when Max Lagali and then followed by John Rogers and many others, they started using silicon on insulator where you have a buried oxide layer and on top you have the silicon on insulator layer silicon where you make all the active devices and then you have the substrate itself. So the idea was that, okay, we make them and we will be actually then removing the buried oxide layer. So the top layer is already loosened up and so that's flexible. Now, that is fine for one device. How about when we are making a circuitry? We need to have device isolation. So how? First, we can make FinFETs, the way that we go all the way and make individual fins and they're connected one way or other. Or we can try to actually use a thicker silicon SOI where we are going to introduce the shallow trench isolation, or we can use the historical mesh isolation. So now let's assume that I've done that. I'm going to remove the buried oxide layer. What we are seeing here, we are essentially seeing that all these devices are floating around, they're discrete. Here, it's humongously costly to have this kind of thick, and it's not going to be flexible. And this one, we know that the bird's beak, that kind of stress coming from the mesh isolation is making it impractical. So now Allied Material Company, they actually say that they can grind, which is an abrasive process, and make them thin enough. But it is not true. We have tested it out multiple times. The thinning ability is very limited, and that's why it's not flexible enough, and it's also costly. And it's going to damage the devices on top of it. Well, we can use the Virginia Semiconductor ultra-thin silicon, but according to their own admission, that these are defective substrate and not for high-quality electronics. And anytime you do a high thermal budget process, after that it's non-usable because the other equipment is not going to even take them because they are so much actually bowed up or curled up. So that's why removing buffer layers, simple process, it's costly, transistor isolation, warping. So I accumulated the advantages versus disadvantages that we know of. So the question then is John Rogers group in Illinois and then now in Northwestern, they have used a 111 substrate because 111 detection is easy. 100 can be etched off easily because they have low atomic density. But unfortunately, if you look at that, their defect density is substantially high. So these are not good for anything except bipolar junction transistors. Well, there is also, we can think of from a mobility perspective, as you can see, that 100 is far better for NMOS for 11 compared to any other orientation. And for whole mobility, 110 is better, but not the 111. Okay, so Chipfin in Germany, they basically actually make anodic silicon, then they do the epitaxial process and then lift off. But this essentially is an expensive process and low throughput. Now, UT Austin followed by IBM, they have shown that they can use a metallic stressor layer to peel off by causing controlled cracking within the silicon substrate. But again, it's a complex and destructive for free-hanging microelectromechanical devices because they will be completely gone when this spalling process will be applied. And that's why none of this seems to be the sustainable solution that we are looking for. So we have to really figure out the way that where we can actually deal with bulk monocrystalline silicon, which is the 90% of the electronics technology, the flexing using standard CMOS process in cost-effective manner. So what we did, we basically took the bulk substrate, we built the devices as they should be, we identified the shallow trench isolation areas, then we make trenches, then we make the spacer layer to protect them, and from the bottom layer, we flow xenon difluoride to actually create the trenches, and they go isotropic nature. So not only they go vertically, they also go laterally. And then when they mix with each other, the top portion has been peeled off. Okay, we carried them out with different designs, and we actually did experimentally a model followed by experimental validation that which is going to be the best possible the design architecture, so that we can actually consume much less area for making the trenches and preserve these areas which are going to be for the device fabrication. Okay, we have also tested it out that how we can actually enhance the efficiency of the etching. So we are not utilizing lots of gaseous chemistry. It's also environmentally, we have to be benign enough. At the same time, we can actually do it in a high throughput manner, so that in a given time, we can produce and process more and more substrates in a reliable fashion. Okay, so design consideration is depending on the material, their crystal orientation, process selectivity. And then when the top layer is gone, then we do the chemical mechanical polishing to get to the pristine level. We have done it for 6 times for the 500 micron substrate. And the question is that how much area that we are sacrificing to make this porous network? Well, if you look first, that even in a 3 nanometer technology node, we have to make or contribute 20% of the areas for shallow trench isolation. We need only 10%. So we do have a large leverage or leeway to do it. Now for multi-level interconnects, it's a famous picture from IBM. As you can see that there are so many gaps available. So it's actually easy to work with multi-level interconnect substrates. So I'm going to actually show you that how one of my former students, he is now in Zurich in Switzerland. So he is actually peeling off this the substrate, which is a silicon. You don't see the devices because these are this is covered with the oxide layer, and then you can see that he is going to peel off completely and going to actually bend it multiple times. And this is without any kind of encapsulation at the moment. So when we remove the oxide layers, there are a bunch of these the devices, those just came out. So it's an scalable for ultra scale devices and absolutely compatible for the extreme ultra large scale integration, compatible with the multi-level interconnects. We recycle the remaining substrate, so it lowers the cost. And we did some of our analysis. It actually, after you have the die, it required 65 cents per centimeter square. And this extended to non silicon. It's applicable to silicon germanium, gallium arsenide, and indium phosphide. So how does the device look like? So we actually built multiple of these FinFET CMOS circuitry. FinFET is the one which is a current standard architecture for the transistor technology, which are vertically aligned. So essentially, depending on you have one channel inversion layer here, you have the other layer on the other side. So this is basically, you have the gate from 2 sides. Sometimes you can also have the gate on the all sides. So what happens is you basically create 2 inversion region by this the gate area. Okay, so you have more and more electrostatic control. Your width is the height of the fin on one side, and the other side. So 2h plus this narrow fin width. So you also have W over L, because the L is limited. W we are increasing substantially, so we can actually enhance our performance too. Here are some of the fins. You can see that with the tiny nitride as metal gate and the high K dielectric covering them up, because it's an ALD, so the coverage is pretty good. This is actually, the fins are always being made in arrays. You can see on the top portion, you can see the bottom portion, the interface layer is stable and actually of high quality. This is a top view of the fins connected array, the source and drain, and this is the gate actually is covering all these different fins on the same array. And here you can see that how the contacts are being landed on this FinFET architecture. So we followed exactly the industry standard integration flow. my previous experience in TI as the lead process integrator for 22 nanometer FinFET CMOS in 2006 and 7 helped me to actually do this. And then we had 70% yield. So, but then we made them using the process that I showed, the flexible version of it. Why? Well, not only FinFET is the state-of-the-art architecture, they also are very unique architecture, because if you look at physically that, okay, so fins are aligned in this way, but then when I bend it, it might be that I'm bending the fin in this way, or sometimes I'm bending the fin in across its feet. So we don't know, but depending on that, many interesting things can actually happen, because the stress will be there because of the deformation induced stress. And if we can control them, depending on that, we can actually see net decrease in current or net increase in current, depending on its orientation, depending on which way it has been stressed, which way it has been bent. And you can see that, like, the stress analysis actually shows the compressive versus tensile, that how that will be translated across or along the channel in the fins. Okay, so that's why the physical deformation induced strain is very important, and that's also important for the FinFET. But this basically makes this analysis highly complex. I'm going to show you the transfer characteristics. As you can see, that the unflexed means the rigid versus the flexible one, where the gate length is 250 nanometer versus the gate length, which is pretty long. And you can see that when we have done it, the tensile 5 centimeter bending radius. So at that point, we can see that this is actually doing really well. The increasing gate length in this way, the VDS we kept at -1 volt, the fin width was 50 nanometer, and the number of fins was 20. And this is essentially the NMOS, what you can see here. And we had the gate length is 90 nanometer versus also the gate length was 100 nanometer. So they're far more scale. We see on each occasions the on-state drive performance does not change under flexing. That is good, because the first thing we would like to make sure that because of the new processes that we are doing, as well as because of the user's habit, we are not going to impact the as it is device performance. Now, after that, if it gets improved, great. If it doesn't degrade, then that's also good, because we are retaining the exact performance that we get from its standard rigid version. However, the gate-induced drain leakage current increases under flexing. The reason is very simple. In a transistor technology, there are multiple films which are ultra thin, especially the dielectric. Nowadays, we use the high-K dielectric. When we apply different kind of mechanical anomalous straining, then it is entirely possible that there will be mechanical rupture within those the thin films. And when that happens, especially in dielectric, it means that there is a discontinuity in its the film, and it means that there will be leakage, which will eventually lead us to a variety of the failure. Okay, and we do know that the high K fracturing under flex conditions could lead to this increased giddle. Here are the some of these the IDVD plot. As you can see that when we are applying, we did some of these thorough analysis, that we kept it bent at a certain bending radius for year long, 1 year. There is no 12 months long we kept it, like radius 0.5 centimeter at an LG 90 nanometer. As you can see that how they're behaving. The performance and reliability, what we are intended for, is to minimize no to low processes induced impact comparison with when we compare that with the rigid version. And we have to understand that it's highly unpredictable because that's why we need to actually build the fundamental understanding, and the mechanical is a new variable. How much time?
So, Professor Mustafa, I think, is it possible for you to finish in the next 4-5 minutes? because we
Yeah,
have
of course.
already exceeded
Thanks.
the time. Yeah.
Yeah, of course. Okay, so now, as I mentioned in the beginning, that we followed a coin architecture, so which means that you most probably have seen every single demonstration. The sensors are here and the I/O transistors are here. It means that they are dissipating heat, and even if I'm talking about brain-machine interfacing, I'm giving up my valuable sensory areas, and at the same time, I'm dissipating heat in the areas where they should not be. So the best way is essentially to actually follow a 3D architecture like a 3D IC. It's going to minimize the area, the consumption. It's going to reduce the heat. It's going to be actually lower interconnect delay and higher interconnect density. The question is that through silicon via itself is difficult, but can we do the through polymer via? And we have actually figured out how to do it. And based on that, our results actually shows that the portion which are touching these 0.5 millimeter thick silicon substrate are the sensors. The other side is essentially the antenna, and in between them, all these I/O, the flexible devices are there. So now is the time to compare the fully flexible integrated system. This is from IMEC. There is no system. There is bare die only. Okay. Then there is the American Semiconductor. It's around it's actually close to $1 billion investment. So there is no system that they have ever been able to show. They sell bare die like ADC, BLE, NFC, and OPAM. And this is ours. We heterogeneously integrate hybrid materials and diverse devices. We continuously use bulk silicon 100. We maintain ULSI CMOS, high thermal budget. It's a coin architecture, like a coin. One side sensors, the other side is the energy harvesting and antenna, and in between are the memory, logic, the wireless communication, and the battery. And it's a fully flexible system. If we compare, you can see the data that when we compare ourselves with the American Semiconductor, we are not restricted to anything. It's just the accessibility to the bare die that we need. So from a power consumption perspective, the voltage supply, the flash, ADC resolution, we are toe to toe with that kind of $1 billion investment. Okay. So with that, I'm going to actually summarize my talk. Redesigning the CMOS is actually going to open up a new frontiers in the CMOS technology, especially Professor Mark Lundstrom of Purdue University, NAE, and the founder of NanoHub. He always says about our work that we are expanding a new area for the CMOS technology, repurposing CMOS technology. Heterogeneous integration is going to be the key. We need to build the fundamental understanding about how the anomalous mechanical deformation really impacts the device performance. And we showed a coin architecture with a fully flexible standalone multifunction CMOS electronic systems for a variety of applications. And more importantly, we retain the performance, integration density, energy savviness, reliability, and plus we make them flexible. I would like to acknowledge my past and present group members, my collaborators, and variety of grant agencies and industry sponsors. So I would conclude my talk here, and I'll be happy to take questions, I guess, through the chat box.
Yeah, so thank you, Professor Mustafa. It's a very interesting talk. So the floor is now open for some questions. So the participants could ask questions directly or through the chat box. So Manoj, can you please guide me if there are some questions in chat box, because I don't see any questions now. But for the participants, we can have questions directly, because already we have exceeded. It's already 10 minutes past 11:30. So we should be able to take 1 or 2 questions.
So I think there is no query in chat box, and if any participant is want to ask any live question, then they can ask.
Yeah.
Hello, sir. I have a small question.
Yeah, please go ahead.
Yeah, sir, how are you making this flexible silicon durable? Means that even a small space won't break the silicon flexible. So is there any compound or any element you are adding to make it durable or?
It essentially, yeah, whenever you know the factual rigidity, then you have to place the piece of silicon in the neutral plane of the encapsulation materials. So they are going to provide the sufficient protection that's going to actually keep them flexible, but at the same time, their mechanical integrity is going to be preserved. Okay, but obviously we have to be truthful because we always provide that up to what kind of bending radius you can bend it. Beyond that, you will not be able to bend it. Make sense?
Yeah, yeah, yes, yes, sir. Thank you for the.
No problem. Thank you.
Are there any other questions? So I have a couple of questions to Mustafa. So one thing is so if you compare the performance of bulk devices, like let's say FinFET transistors made on the bulk silicon, very thick silicon, and how your devices compare to that, right? So is it equally performing or is it 10 times less performing?
No, it's equally performing. This has been, we have shown this consistently time to time because we have always focused to keep the performance as they are while making them flexible. Okay. Our objective is not to enhance the performance. Our objective is to retain that performance.
So what is the cost of fabrication? Means if you look at the manufacturing cost of your devices, so how does it compare?
So as I mentioned that every per centimeter square, you have to spend 65 cents at the least.
Okay. And how does it compare with the normal silicon transistors?
I think obviously that 65 cents per centimeter square is actually nothing because if you look at per centimeter square, we can easily pack in today 1.8 billion transistors. So 65 cents divided by 1.8 billion transistors is nothing.
Yeah, exactly. So another question about reliability, because when you are bending, so
Right.
does is there any change in? I mean, so I'm talking about hot carrier reliability, or are there any device breakdown issues? Yeah.
Okay, so I think as I mentioned that the physical anomalous strain can actually break the dielectric, but that's why we provide that up to what kind of bending radius, how many times it can be still operational. So that's definitely is there, and I don't that we have done that kind of a study continuously with the hot carrier or those phenomena are not available, and here is the reason. So and these are experimentally validated and modeled and supported by also the folks who actually work with the DFT analysis. So basically, you most probably know about Scott Thompson's work in University of Florida, that he shows that okay, if you can bend a little bit the standard rigid wafer, you can engineer the pi factor. So essentially, you might actually get 6 to 7% of the mobility enhancement. I was one of the co-authors of many of his papers. But here is what is going on. In flexible electronics or flexible silicon, you just do not have that much of the substrate available. You have already thinned it down. So when you have thinned it down, it just cannot exert the force, the stress that is required to actually do that. And another point is that silicon is an indirect bandgap material. There is no way that you can apply that much of a stress. They are going to realign and will make themselves a direct bandgap material. So no, there is no particular reason that they will be like that. Whether I do recognize many times people are actually very interested that are they going to be that thin that we can do quantum mechanical confinement? No, we don't need to. I think like, for those we can use the ETSOI or those kind, and there are different architectures we can use and different kind of substrate. But the main objective here, maintain what we have, add flexibility. Okay.
So thank you, Professor Mustafa, and it was a very interesting talk. So we'll move to the next speaker. So let's thank Professor Mustafa again. So our next speaker will be Dr. Mandar Bhoyer from Micron, India. So Mandar, can you please, is it possible to share your screen?
Sure, sure. Is it visible, sir?
Yes. So yeah, so you could, I think, full screen mode. You could go to the full screen mode. All right. So let's welcome Dr. Mandar Bhoyer. So Dr. Mandar Bhoyer is currently working as a TCAD modeling engineer at Micron Technology India. He joined device technology department team at Micron in this year in May 2020, and is involved in R&D for upcoming memory technologies. He received his MTech and PhD from IIT Gandhinagar in 2015 and 2020 respectively. He was a visiting research scholar at IMEC Belgium and JEST Japan during his PhD tenure. His research interests include emerging memory technologies, high voltage CMOS devices, and advanced CMOS architectures. So in this session, he will talk about variability sources in nanoscale bulk FinFETs and Titan, a promising low variability war function metal for 7 and 5 nanometer CMOS nodes. So Dr. Bhoyer, it's to you now.
Thanks for this kind introduction, and good morning to all of you. So I would be speaking about the variability sources in the advanced FinFETs and the solutions that presented to reduce it. So the outline of my talk is basically, first I would be emphasizing on the need of the variability analysis in advanced FinFET technologies. Then I would be discussing about what are the challenges associated with an experimental based kind of study and why was it adopted. To overcome these challenges, a systematic segregation strategy was proposed. I would be discussing about it in detail, and I would be also demonstrating the validation of it. And finally, to reduce the dominant variability source, promising low variability work function barrier metal would be introduced, followed by the summary. So all of us are aware that as we are scaling down the device dimensions, process-induced variability is becoming a major concern. Let's take an example of an SRAM. So with process variations, the VT of the transistors in SRAM starts varying. As the VT of the pull down or the pass transistors increases, the SRAM transistor starts failing. And the rate of failing further increases as we are scaling down the minimum operating voltage. So overall, this hampers the production yield and minimum operating voltage in SRAM transistors. So not only memories, but it is the logic as well as the analog circuits that are getting hampered because of this process-induced variability. And therefore, process-induced variability has become a major concern and slowing down the device technology scaling and needs special attention. So various process-induced variability sources have been demonstrated for bulk CMOS and the previous generations of FinFET technologies. I'll be basically discussing about FinFET, so which is the current technology that is in use. So the different variability sources are fin edge roughness, the gate edge roughness, which can cause a change in WFin or LG respectively. There then can be variation in the work function because of different factors, which we'll be discussing later. There can be variation because of random dopant fluctuations, mobility fluctuations, EOT, or oxide charge variations. There can also be variation in the source and series resistance, thereby hampering the current characteristics. Now, as we are scaling down, and to sustain scaling, the fin profiles have gone dramatic change. The fins have basically become thinner, taller, and straighter in nature. This has been basically done to sustain the short channel effects even though we are scaling down our gate lengths. Now, this change in fin profiles have increased the processing complexity by introduction of different patterning techniques. At the same time, we have also introduced some complex processing steps like replacement metal gate and so on. So in such a complex scenario, the question arises, does the variability source that have been discussed earlier still holds in this advanced technology nodes? And that is where we thought to look upon. If we look at the literature, various reports are available. So few of the reports basically tell that the line-edge roughness would be the dominant variability source in advanced FinFET regimes. There are also few studies that shows that the fin-edge roughness would be the critical factor when we would be entering in the regime where fin widths are less becomes comparable and cause quantum mechanical effects. And we are already in sub 10 nanometer kind of fin width regime. There are also few other studies that suggest that we would be having metal gate granularity as the dominant variability source. At the same time, we also find some reports that suggest that metal gate granularity won't be there because we have adopted gate last or RMG kind of techniques. Few of the reports in the literature also suggest that the random dopant fluctuations or the variation in the source and series resistance would be the dominant variability source. Now, if we look at all the literature, the conclusion is not clear. Why is it so? The reason is simple. Most of the studies are based on simulations where they try to predict what would be happening in the next generations of FinFET technologies based on the limited knowledge in the earlier generations. And that is the reason the exact variability source and its impact is not known for this advanced technology nodes. Solution for this is an experimental based kind of studies. Once we know the dominant variability source, then we can use it for in different dimensions. First, we can reduce its impact by proper process tuning in that particular module, or even the compact modeling engineers can use it to accurately model that source and helps, which would be helpful for accurate circuit simulations. And that's the reason we focused on experimental based kind of study to investigate the variability source in advanced FinFET technologies. The FinFETs that were used in the study were fabricated in IMEC on a 300 mm line. The fins were patterned using multiple patterning technique. The self-aligned double patterning was used, and the fins had a fin height of around 26 nanometer and different fin widths all the way from 7.5 to 4.5 nanometer were used. After following the conventional CMOS process steps, the gate stack was deposited using replacement metal gate process, where the final EOT was around 0.8 nanometer, and the work function was set using multiple metal layers. In case of NMOS, we have used titanium nitride, titanium aluminide, and titanium nitride as shown. Once these devices were fabricated, electrical measurements were done. To investigate the total variability, identical transistors spread across 145 different dies along a 300 mm wafer were measured. And for random variability, the mismatch between the match pair of transistors was measured. And these measurements were repeated on 145 different dies. So after this huge number of device measurements, the transfer characteristics were plotted, and the spread that can be observed in the off current and the on current clearly emphasize the severity of total variability. Post segregation, it was observed that most of these total variations were coming up from the random variations. And that was the reason our most emphasis was on random variability sources. Now the major challenge occurs how to segregate the impact of these variability sources. In simulations, it's quite easy. We can turn off one of the source, turn on one of the source and turn off all the others and check its impact and gauge what is the impact of that particular variability source. But in an experimental measurement, all the sources are acting together, and it becomes difficult to judge which one is the dominant and to what extent. So what is the solution for this? What we need is a systematic segregation strategy. A strategy which should be non-destructive in nature. That means it is totally based on electrical measurements and does not have any physical kind of measurements. And secondly, it should be such that it is not only useful in this technology regime, but can be easily adopted in upcoming technology nodes. And we proposed a systematic segregation strategy to separate the impact of different variability sources from electrical measurements, and let's discuss it for the current. So the on current of a transistor basically depends upon VT, GM, and RSD. And therefore, using a simplified error propagation law, we can segregate the variability sources in ion in terms of VT, GM, and RSD, where the first component, VT, basically represents the variation in WFIN because of FER, LG because of GER, EOT, random dopant fluctuation, oxide charges, or work function variation. The second factor basically captures the mobility variations along with WFIN, LG, and EOT variations. Now remember, the simplified error propagation law is based on the assumption that these three components, VT, GM, and RSD, are independent of each other. But that is not true in this advanced technology nodes, where we have a strong relation between GM and RSD. And that is the reason we decoupled GM independent of RSD by using this simple formulation, and that was used henceforth. While the last component, RSD, captured the variation in source density resistance occurring because of WFIN variation, random dopant fluctuations in the source drain, especially the extension regions, and our contact resistance. Now, the highlighted quantities in this formulation were calculated from the quantile plots of ion, VT, GM, and RSD. The straight line behavior of these quantities with respect to normal quantiles clearly emphasize that these quantities are following normal distribution, while the remaining quantities were calculated from the correlations. So correlation of ion with respect to VT, ion with respect to GM, and ion with respect to RSD were plotted, and the slope of this regression line helped us to give this quantity. Once all these quantities were known, the impact of different component was plotted. It is clearly observed that the calculated ion variability from this formulation matches with that of the measured ion variability. This clearly validates our segregation strategy. Then, second noteworthy thing is that VT has a major source. VT is the major source of variability in ion variations, and that is something that needs to be looked upon. Second, we also looked up at the random variations in IOF. Since IOF depends upon VT and SS, its variation were decoupled in form of VT variations and SS variations. Both these components were calculated as we have done for on current. And it was observed that the VT variability is also responsible for the IOF variability. And it gave us a clear conclusion that the VT variability is the dominant factor in ion and IOF variations. And so it was investigated in detail. Now, again, at the same problem. The challenge was segregating the impact of these different variability sources from VT variations. And so, again, a systematic strategy was proposed, and which was as follows. So, any variation in RSD can cause VT variability. But the good thing is that RSD can be electrically measured. Similarly, a variation in WFIN, LG, and EOT can cause VT variability. But the thing that can be noted is that these factors cannot be directly measured from electrical measurements. So what we did is that this factor also affects SS variations. And so SS variations were used to gauge the impact of these factors. And finally, the remaining factors, that is random dopant fluctuation, oxide charges, and work function variations cannot be electrically measured. And so for time being, we have coupled them and call them as X factor variation. Using the simplified error propagation law, the variations in VT were segregated in terms of variations in RSD, SS, and X factor. Now, the LHS can be calculated from electrical measurements, and the first two terms in the RHS can also be calculated. And so that gave us the impact of the last factor, that is the X factor. So the results are here. And it was clear that SS and RSD have negligible impact on the total VT variability, while most of these variations are coming up from the X factor, which is the random dopant fluctuation, oxide charges, and work function variations. And let's discuss the physics behind all these factors one by one. The method that was used for calculating VT was the constant current. And at such a low current levels, the lower impact of RSD is impacted. So lower impact of RSD variations is also expected. Moving to the next factor. So first one is finish roughness. Fins in this technology nodes are generally patterned using different multiple patterning techniques like SADP, SAQP, since our common lithographic techniques aren't capable to produce fin widths of these dimensions. And the thing is that fins which have been developed using spacer-based techniques have correlated sidewalls as compared to those that have been developed using resist kind of patterning. Using spacer-defined patterning, even if there is an FER, it is not causing any change in W fin because of this correlation. And this clearly tells us the physics behind why we are not observing any impact of FER. Then the correlation between VT and SS and VT and double was plotted to gauge the impact of GER and EOT. No correlation was observed between this quantity. A strong positive or strong negative correlation would have been a signature of strong EOT or GER variations. And this clarifies that there is neither a significant FER, GR, or EOT variations in this regime. Now the question arises, okay, FER is not there for fin width of 7.5, but will it get emphasized as we are scaling down our fin width and it enters quantum confinement regime? The answer is no. We did the measurements and plotted the Pelgram plot for fin width as low as 4.5 nanometer. And no significant increase in variability was observed. And this confirms that the dominant variability source is not present within the fins, but it is somewhere outside the fins. And so we move on to the last factor, that is X factor. So the random dopant fluctuations in this technology can cause one because of the channel doping or because of the random dopant fluctuations within the hollow implant. But fortunately, we don't have any channel doping in this technology nodes. So that factor can be eliminated. To gauge the impact of hollow implant, TCAD simulations were performed and for transistors with different channel dopings and with and without hollow implant. But it was observed that the VT sensitivity, even with this extreme change, was very negligible. And this helped us in eliminating the impact of random dopant fluctuation in this technology regime. With all the other variability sources eliminated, we need to look just at the QOX and phi-m variability. So the Pelgram plot was plotted for transistors with different EOT, and the AVT, that is the slope of Pelgram plot, reduced as we scaled EOT. This was a clear picture that it is the oxide charges that are reducing, that proportional to the dielectric thickness are reducing, and the variability is reducing. So the AVT was plotted as a function of dielectric thickness and extrapolated to dielectric thickness of 0, where all the oxide charges can be eliminated. And we got a AVT number of around 2 millivolt micrometer, which basically told us that around 10 to 15% of the variability for the EOT of our interest is coming up from the oxide charges. To further verify this theory of oxide charges, we used different annealing splits. So this annealing was basically done after high-K deposition, but before the metal deposition. And it helped in eliminating the charges, which can be confirmed from the reduction in the gate current with different annealings. And this reduction in charges also helped in reducing the AVT, and the AVT number went and saturated to somewhere around 2 millivolt micrometer. And this confirmed our theory of oxide charges. So with oxide charges producing around 10 to 15% of the variation, the dominant variability source is none other than the remaining source, that is the work function variation. So work function variability can come up from because of different factors. One of the factor is metal grade granularity. So grains with different crystalline orientation can cause different work functions and can result in work function variability. There can also be variations or fluctuations in the work function metal thicknesses, and that can cause work function variation and impact the VT. Now, few studies earlier have suggested that metal grade granularity won't be present in this technology regime. And to investigate that, we measured wafers with and without silent soak. So this silent soak was basically performed on the barrier metal layer, that is the bottom metal layer of titanium, and on the same ALD platform. Introduction of the silent soak amorphizes this titanium nitride, and we get metals with smaller grain size. This helps in reducing the random variability by around 27% and confirms the presence of MGG even in RMG process technologies. To summarize this complete proposed segregation strategy, it can be shown here. So finally, it is the QOX and it is the phi-m that is the dominant variability source responsible for VT and ion and IOF variability. And this proposed segregation strategy, as promised, is completely based on electrical measurements, which has a non-destructive nature. Now, one thing that can be noted that the VT used in this complete analysis was based on the current constant current method. And there has been a common myth, or there has been a claims that the VT extraction method not only affect the VT variability, VT values, but also its variability. Now, again, the question arises, does this fact hold even though we are scaling down our technologies? To investigate that, we looked at VT extracted to 6 different methods, which had dependence on different parameters, and checked the total and the random variability. And it was observed that the variability is constant for all these methods. And this can also be backed up through a mathematical formulation where it can be shown that and a higher work function and oxide charge variation actually masks the negligible amount of variations in mobility, RSD, or other factors. And that is the reason we are getting same variability in spite of the extraction method used. This helps us in concluding that VT variability is actually independent in this technology regimes where we have significantly higher phi-m and QOX variations. Now, since phi-m was the dominant variability source, we need a solution to reduce it as much as possible. So the basic approach was to look at the gate stack. We are already using the barrier, the bottom metal layers, which has titanium nitride or stacks of titanium and tantalum nitride in our NMOS transistors. So what we introduce is a new metal layer that is titanium tantalum nitride, and which was introduced by co-deposition of titanium nitride and tantalum nitride using the ALD deposition technique. And this these transistors with titan gave the same VT, even though we are having a smaller kind of a thickness as compared to the nominal titanium nitride. And the second noteworthy thing was that the effective change in VT with scaling of LG is quite less as compared to the pure titanium nitride. This confirms that this new metal gate stack has conformal kind of deposition within the gate trenches, and which is actually a good sign. Now the question arises, does this gate stack anyway affect the performance of our FinFET? The constant gate current for these two stacks and the overlapping nature of ion IOF characteristics and ideal Whittling characteristics clearly tells us that the performance remains unaffected. This clearly shows that the gate electrostatics, the EOT, mobility, and the gate stack integrity remains unaffected with Titan. And in addition to all this, the significant factor is that the transistors with Titan show around 44% lower VT variability, total VT variability, and around 27% lower random VT variability, and which is really a good number. To understand what is the reason behind this improvement, we again invoked the proposed strategy, and it was observed that most of the reduction is because of the lower work function variations in Titan-based gate stack. Now, to understand the physics, it can be looked upon in this way. The crystalline phase of Titan and titanium nitride is more or less same. So this helps us to eliminating the MGG factor. MGG is more or less should be more or less same in both these transistors. But one of the factors that can be that could be responsible for this is the conformal deposition of Titan, as we have seen before. And this helps us to summarize the Titan part, where Titan is providing a significantly lower VT variability. It has conformal deposition, and it is scalable. It has a scalable nature, and in spite of all this, it does not affect the FinFET performance. And so it is a promising work function metal layer for future technology nodes, where basically we would be having limited space because of fin pitch and the gate speed scaling. And this brings me to the summary. So the challenges associated with an experimental based kind of study were first demonstrated, and to overcome those challenges, a non-destructive and a cost-effective kind of systematic strategy was proposed, which helped us in segregation the impact of different variability sources in on-current, off-current, and VT. It was observed that VT is the major contributor to ion and IF variability, and most of this VT variability is coming up from the oxide charges and the work function variations. While the much hyped FER, GER, random open fluctuations, and EOT variations are not that significant in this technology regime. And finally, a low variability work function metal, which is promising for upcoming technology node, that is Titan-based gate stack, was proposed. I would like to acknowledge my current organization, Micron. Thanks the organizers of ICEE 2020. Since most of this work was done at IIT Gandhinagar, I would like to thank my supervisor, my institute, IIT Gandhinagar, and our collaborators at IMEC, all the funding agencies, and all the audience. Thank you. And I would be happy to take if there are any questions.
Yes, so thank you, Mandar. And so now the floor is open for some questions. So we have time for 3 to 4 questions. So are there any questions in the chat box? I do not see any questions in the chat box. So are there any questions from the audience and the participants? Okay, so since there are no questions, so I have few questions. So so basically, how this variability segregation methodology will work for advanced devices? Let's say if you want to go for nanosheet FETs or for these devices.
So the first approach while developing this technology, this segregation strategy, was that it should be completely based on electrical measurements, and so it does not involve any kind of physical characterization where we are slicing down our devices or something like that. And electrical measurements can be can be done on any type of device architecture. And if we look the other device architectures like nanosheet FETs and compare them with FinFET, even in those technology regimes, we would be basically having these edge roughnesses would be playing a role, especially the gate edge roughnesses. When we have sheets with larger widths, we surely won't be having random dopant fluctuations, because even in those kind of technologies, we have undoped channels. But there would be this strategy, and at the same time, since we have multiple stacked kind of sheets in nanosheets FETs, and we are actually decreasing our pitches. So work function metal would also be a dominant factor there. So more or less, the dominant variability factors that have been observed in this study would be present even in those technologies. And since this approach is totally based on electrical measurements, it can be easily extended on the need-to-know basis to these advanced architectures.
Okay. So do you expect this kind of variability in 2D material-based FETs?
Yeah, if we talk about the edge roughnesses, which is basically coming from the lithographic point of view, then the work function variations because of the metal gates. So if these things are remaining constant, these things more or less would be remaining constant even in 2D FET. So they would be we would be surely seeing these factors there. But other factors that we need to consider about the 2D materials is that we have thinner, we have sheets kind of things. How is the mobility changing with kind of a strain or those kind of things? And so there may be few additional factors that would come into play even in case of the 2D materials kind of architectures that needs to needs to be looked upon as compared to silicon.
Mm-hmm. So how will it play for memories, right? Less memories are also very strongly scaled devices nowadays, right? So how will it? I mean, how the variability is affecting the memory performances?
So if we basically talk about the memories, what we have is two different components. One is the storage element. Let's say in case of DRAM, we have a capacitor. So, and the second is the CMOS periphery devices that are used for driving the gates for reading and writing kind of things, and for sensing the voltages. So if we look at the scaling trends that are happening, so to continue the scaling trends in memory, we are in case of DRAM, we are also scaling, aggressively scaling the CMOS architectures. And as we are scaling down the CMOS architectures, we are coming up, we are noticing this kind of variability sources. And so variability is becoming a major concern even there. And if we are talking about the architectures like 3D NAND or some kind of a thing, the processing complexity that it has of stacking multiple metal layers and having a uniformity between these layers is really a challenge. So surely variability is also a concern in memory sector.
Okay, so thank you. I think this is a very nice presentation, and the Icee organizing team is thanking you again for this excellent talk. So we'll now move to the next speaker. So I'll request Mr. Sanjay Kumar to present his talk. So Mr. Sanjay, are you there?
Yes, sir.
Yeah. So can you please share your screen and your present?
Yes, sir. Sir, is it visible?
Not yet. Yes.
Okay. Thank you. Okay. Good morning, all of you. And my name is Sanjay Kumar, and today I'm going to present my presentation on the analytical modeling of Y203 based memory system for the artificial neuron application. And this is the content of my ongoing slides. Why we need of the artificial neurons and the key point of my talk. Then analytical model equations, which I have used to model the experimental data, and then analytical model results and validation with the experimental data, and then application, and finally conclusion. And firstly, I'll talk about why we need an artificial neuron in why we need the artificial neuron in nowadays. So basically, the artificial neural network is an abstraction and simplification of the biological neural network, which is present in our body to transmit the information from one end to another end. And secondly, the artificial neural network imitate the human brain functioning, and at the same time try to achieve the better performance in hard problem solving task. And then moreover, the highly simplified artificial neurons model sufficient for the useful for modeling and analysis, which is enable the better understanding of the processes in human brain and and animals. And basically and more, the learning and operating in the artificial neuron network use only for the local information. For example, during the learning, for changing the weight of the synapse, or basically is the normalized conductance of the device, you can say in the case of the memory store RM devices to work as an artificial neurons. So only the state of the two connected neurons are ended, and then the locality principle make the artificial neural network more biologically plausible. And that is a summary of my talk. Firstly, the artificial neurons and the synapse are the key unit of the information in the biological neural network systems or neuromorphic systems. And basically, the memory store systems are the frequently used in artificial synapse because of they have the simple structures, gradually changing the conductance and high density integration. It's change the conductance as per the applied input voltage, and having an MIM or MIS structures in their fabrication process. So basically, these are simple structures, and it's a shows the very significant impact or applied the input voltage as well as the amplitude of input voltage and the pulse width of the applied input voltage. So here a non-linear analytical model for the Y203 based memory system with a new parabolic window functions has been discussed in the upcoming slides. And the modeling data, and then further the modeling data is verified by the experimental results for the fabricated devices in our labs, which confirm that the developed models can be realized the basic functionality of spike neurons and has a great potential for the neuromorphic computing application. And these are the basic model equation, analytical modeling equation. So equation first is basically describe or govern to the non-linear IV relation as discussed by the Stanley Williams in 2010 in the Nature publications, where the input voltage and output current having some relation. So here the first terms describes the flux control memory store behavior with the symmetric behavior, and then the second term is associated with the ideal diode behavior basically. So here the W basically the W shows the state variable, define the state variable, and N is basically the free parameter to control the non-linearity dependency of or the drift velocity of the ions. Is maybe the metal ions or oxygen we can say, and on the over the applied voltage. And alpha and gamma, alpha and beta is the fitting constant and depend used to the characterize the device in on state. Basically it's a experimental fitting parameter. So it's a these value the value of the alpha and beta depend on the your device material based devices, which shows the experimental data in the range of the current range in range of milliampere or microampere range. And then the equation second is show the new parabolic window functions, which ensure the state variable is bound between 0 and 1, and is defined by the equation 2, where basically the parameter x is define the range of the window function f within the 0 and 1. So it's a bounding parameter for the window functions. And equation 3 is describe the rate of change of the state variable with respect to time, where A and M are the parameter to determine the dependency of the state variable on the input voltage, and M is always an odd integer. Then that's the analytical model results and validation with the experimental data. So here we have shows the basic schematic of device, which is already fabricated in our labs, and the resistive switching characteristics of the MIS structures, where the N-type highly conductive N-type 100 orientation N-type silicon substrate used as in a bottom electrode, and Y203 oxide layer used as in a switching layer around having in a thickness of 80 nanometer. And then aluminium uses in a top electrode. So here is the aluminium and Y203 in between that. So this shows the Schottky behavior in nature, as reported by the Das and the authors. So here the figure first shows the proposed parabolic window functions, as I have discussed. Basically the value of the x is defined the state variable from 0 to 1, and so the value of x is varies from 1 to 2. And then window functions are bounded between the 0 and 1. And basically, the figure 2, the right hand side figure shows the resistive switching characteristics of the Y23 based memory system. And this is the black lines shows the analytically IV characteristics, which is very close relation with the experimental data. So these equations are these analytical modeling are governed by the equation 1, as I previously told in the previous slides. And the value of the alpha and beta are the vary from system to systems, which are the range of the. So here the current range is milliampere. Suppose your system's range in the range of the microampere or nanoampere. So the value of the numerical value of the alpha and beta is varies according to the system performance. And then there's the analytical model results validation with the experimental data. Then there's the synaptic plasticity behavior of our memory-stive devices, basically called as the potentiostating and depressing mechanism, or that is called the long-term potentiation and long-term depression mechanism in the Y203 based memory-stive system. In this case, basically we have captured the change in the synaptic weight under the excitation of the successive positive. Is a positive, that is positive in case of the potentiostating and negative in the case of the depression cycle for the Y203 based memory-stive system. So in this case, we have applied in 50 positive cycles over the devices, the having a 4 volt is the pulse amplitude and 100 millisecond is the pulse width. And then the device conductance is continuously increases as with respect to the number of pulses. So in this case, the basically this is called the learning behavior of the devices. So it's continuously increase the device conductance, also known as the normalized device conductance, which is denoted by the synaptic weight of the neuron, and is a synaptic weight of the devices, or so-called the artificial neurons. And in the case of the negative voltage apply, they're having a polarity just reverse from the positive to negative, with having the same amplitude and pulse width. So here we also applied a 40 volt, 40 pulse within a minus 4 volt amplitude and 100 milliseconds, and the device conductance is continuously decreased. And then in this case, the device resistance is increased, and device goes to the high resistance state, you can say, or in the off state. So this mechanism is known as the depressing mechanism, or is called, as you may also call it, a forgetting process of the mechanism of the device. Then that is the application, how to the memory-stive devices work as an artificial neurons, or so similar to the biological systems. So memory-stive is an artificial neuron in biological system. So where we have fabricated in a crossbar array, a 4x4 crossbar array, where the bottom electrode uses in a postsynaptic neurons and top electrode uses in a presynaptic neurons. And so here real neurons structures of the human brain, where the pre-synapse and post-synapse are having are connected within a certain distance. That is, this gap is called a synaptic clip. So basically, this gap is filled. This gap is in the case of the memory-stive structures. Here the this green lines show the metal oxide layer, which is act as a synaptic clip, And in the case of the memory stimulated devices, basically the neurotransmitter, in this case, in the real system, the neurotransmitter is a transfer information from the presynaptic neurons to postsynaptic neurons, and then this is further connected to the another neurons to transmit the information from one end to another end. And in the case of the memory stick system, in the case of the, if you are using an active metal as in a top electrode, so the metal ions, or in maybe in the case of the reactive metals, both the top and bottom electrode, so here the oxygen defects or vacancies in the metal oxide layer is play the role as in a neurotransmitter to transmit the information from the top electrode to bottom electrodes, and then act as an artificial, it shows the characteristics like an artificial neurons. And these are the conclusion of my presentation. Basically, the development of the MMST model can be helped to understand the basic characteristics of the neuron, which further open the way of the develop the human-like brain and the silicon brain. And then the model, the proposed model result shows the close relation with the experimental data of the Y23 based memory systems, and in its neuromorphic characteristics. Moreover, the proposed analytical model leads to the better nonlinear behavior at the device boundary at the end of the applied voltage. Yeah, thank you.
Okay, thank you, Sanjay. It was a nice presentation. So now the floor is open for some questions. Are there any questions from the audience?
Just one question to you.
Yes, sir.
The models which you have considered for this memory set, due to fabrication, there might be some variability always, because when the same device can't be fabricated and there might be device to device variability. So have you considered that thing, and will it affect in your this neuron development, or will there be any constraint for that?
No, sir. Till now, I have not considered the device variability actually.
So do we need to consider that thing, or we need not to consider it? That's my another question.
No, sir. I'm trying to consider those things and improve the model further. So analytically, how to improve that. So I'm still working on that.
Okay.
Okay. So thank you. Are there any other questions?
Hello, Sanjay. This side is Manoj Kumar. Actually, I have a few queries. Like, first of all, what is the on-off ratio of your device? Maximum on-off ratio?
So it's a maximum on-off ratio we have reported is around 40 on-off ratio.
40. Okay. And second thing, as the programming conditions of your device are too high, I mean, you are applying 100 millisecond of programming pulses and 4 volt the amplitude. So how you can optimize those programming conditions?
So after the fabric, this work is 5 years before as my seniors fabricate the device, and then still I am taking the range of 10 milli the pulse width, and then characterize the device. So still I am getting these fabrications results. So not
but
able
as,
to.
but as you shown in your slides that you are using 100 millisecond of programming pulses, and 4 volt is the amplitude of the programming pulse. Like
So this fabrication, basically this fabrication work has been done by my senior. I'm recently switch on the fabrication part of my devices actually.
Okay.
So till now they have used the 100 milli pulse width, because whenever they go down the 50 millisecond or 10 millisecond, so basically the switching ratios goes down, and the resistive switching is very minute in the result. You can't decide case depend on the basically the switching is due to the joule hitting or maybe the other reason behind that.
So when you are applying tens of millisecond programming pulses, then what is the amplitude of the pulse?
Sir, amplitude of the pulse is 1.5 volt. 1.5 plus minus 1. Yes, sir. Yes, sir.
And what is the read volt?
Basically, if you replace the bottom sides N-type silicon with the aluminum, because MIM structures basically.
Yeah.
MIM structures. So you can apply it in or having in the Itria having a thickness of around 50 nanometer. I have taken the 80 nanometer. Yes, but if you are reducing the thickness of the 50 nanometer, then you applied a voltage in the range of plus minus 1.5. and having a pulse width 10 milliseconds, so you get a significant results. We have also reported in the different paper. We have reported these results in.
Okay. Thank you, Sanjay.
Thank you, sir.
Yeah, so there is a question from audience. So this is from Mr. Ranjit S. So the question is, how have you calculated the synaptic weight? Is it a conductance or percentage change in conductance?
So basically, this is the conductance, and then normalized to the 0 to 1. That is converted into the percentage. Firstly, it's normally calculate the conductance of the device, and then convert into the percentage via normalization. That is called the normalized device conductance is called the synaptic weight.
Okay. Okay. So thank you. So I have one question. So this TDI, right? So Y203. So why have you chosen this dielectric? So what is because in the memory store application there are a lot of dielectrics has been used now, right? So what is the advantage of using Y203?
So basically, first of the Y203 memory system shows the basically Schottky behavior with the aluminum and having a very low lattice mismatch with the silicon substrate. Okay, so we have used and they're having a very wide band, wide bandgap of 5.7.
No, but for memory store application, why do you need wide band gap?
No, so
Is it
yes,
necessary?
sir, no, yes, sir, I am agree with you. But we have a very low lattice mismatch with the and the silicon substrate when we are switch on fabricate the MIS structures in case of the.
So lattice mismatch. Let's say the lattice mismatch is very high. So what will happen? Will it create any issue?
Yes.
So what kind of issue will it create?
Please create the more surface roughness, which is I think create the deposition of the upper layer when you use the deposit the metal for the contacts, and surface is quite rough, so the interface is not clear to configure the device.
Okay. Okay. So thank you, Sanjay, for the nice presentation. So now we'll move to the next speaker. So next is a recorded presentation from Professor Jaydeep Kulkarni of UT Austin. I will request Manoj to load that video. In the meantime, I'll introduce Professor Jaydeep Kulkarni. Professor Jaydeep Kulkarni is an assistant professor in the Icee department at University of Texas at Austin, and he currently holds AMD endorsed chair position in computer engineering. He received his PhD degree in electrical engineering from Purdue University. Prior to joining UT Austin, he worked at Intel Circuit Research Lab in Hillsboro, Oregon for 8 years. He has filed 35 patents and published 25 papers in the Harvard journals and conferences. His current research is focused on machine learning hardware accelerators, in-memory computing, emerging nano devices, heterogeneous and 3D integrated circuits, and hardware security. So since he's based in UT Austin and it is currently 12 midnight, he has kindly sent us a video recording of his presentation and we'll play it now. So Manoj,
Good afternoon, everyone, and welcome to this presentation. My name is Jaydeep Kulkarni. I am from University of Texas at Austin. And today I'm going to talk about high-density non-volatile SRAM design using resistive memories and selector devices acting as technology assist. And before I begin, I would like to thank conference organizers for giving me this opportunity to share this work with you. So this is the outline of my talk. First, I will give you a brief motivation behind the non-volatile SRAM design. Next, I will present prior work and present some of the earlier non-volatile SRAM bit cells and talk about various pros and cons. I will then proceed to the proposed 6-transistor, 2 RRAM and 2 selector device non-volatile SRAM memory array. And I will present the operating modes such as store operation and the restore operation. Then I will present the VT improvement because of the VT reduction that one can achieve in this non-volatile. And finally, I'll talk about the amount of power savings that we could get because of the state retention, in situ state retention functionality. And finally, I will conclude this talk with the key findings. So let's begin with the motivation behind the non-volatile SRAM. So if you look at this plot, which shows the power dissipation as a function of technology node, it turns out in advanced CMOS nodes, the contribution because of the leakage power is increasing. And if we take a look at the floor plan of modern SoCs and microprocessors, more than 70 to 80% of the die area is occupied by the SRAM arrays. And these SRAMs contribute significantly to the total power consumptions. For example, if you take a look at the standby leakage power, which is a significant contribution in this advanced technology node, the low activity SRAM arrays, especially the ones in the last level cache of the memory hierarchy, they contribute significantly to the total leakage power. And because of the higher leakage power, the energy efficiency degrades. So to mitigate this issue, non-volatile SRAM technologies have been explored. And the key idea behind the non-volatile SRAM is, instead of putting the data onto an off-chip non-volatile memory, because it is expensive from energy efficiency as well as latency point of view, is it possible that we could store the data in situ in this SRAM array and then turn off the SRAM array without corrupting the data? And that is essentially the name the non-volatile SRAM indicates.
So Sanjay, something happened. So can you download and play it?
Sorry, participants. Actually, there is some technical issue.
Sanjay, should I share my screen?
Just 2 minutes, I'm just downloading and share it to you. Just 2 minutes.
No, I have already downloaded, so I could share.
Should I share, sir, or you are sharing, sir?
Yeah, I am doing that. Oh.
Good afternoon, everyone, and welcome to this presentation. My name is, for example, if you take a look at the standby leakage, power, which is a significant contribution in this advanced technology node, the low activity SRAM arrays, especially the ones in the last level cache of the memory hierarchy, they contribute significantly to the total leakage power. And because of the higher leakage power, the energy efficiency degrades. So to mitigate this issue, non-volatile SRAM technologies are being explored. SRAM is, instead of putting the data onto an off-chip non-volatile memory, because it is expensive from energy efficiency as well as latency point of view, is it possible that we could store the data in situ in this SRAM array and then turn off the SRAM array without corrupting the data? And that is essentially the name the non-volatile SRAM indicates. So what exactly is the non-volatile SRAM? Well, a non-volatile SRAM, it offers in situ state retention, meaning thereby you can store the data, the contents of that bit cell within the same cell using a non-volatile memory bit cell on top of the 60 SRAM bit cell. And we don't have to transfer the data to an off-chip memory array. And the key idea is the contents of the bit cell, they are stored onto an NVM bit cell sitting right on top of that silicon 60 SRAM bit cell before we transition into sleep state. And as we transition into the sleep state, we could turn off the SRAM array, the 6 transistor SRAM array, completely, because we have retained or stored the state into the non-volatile bit cell counterpart. What exactly it allows us to do? The non-volatile SRAM, because of the in-situ state retention, it also in reducing the active power consumption. This is because the non-volatile SRAM decouples the conflicting VT, the threshold voltage, and the Vmin, which is the minimum operating voltage for the successful operation. The non-volatile SRAM helps us to mitigate or to decouple this VT and Vmin correlation. This is very important because in the conventional 60 SRAM design, in a high-density SRAM design, the VT of the transistors is typically scaled up in order to minimize the leakage power. But with the increased VT, also comes increased sigma VT, the increased variations in the VT, and that translates into higher active Vmin. And the higher active Vmin means higher power consumption. So with this non-volatile SRAM, since we are completely turning off this bit cell array during the state retention period, we can reduce the threshold voltage from high VT to lower VT. And because of reduced VT, sigma VT, the variation in the VT is reduced. And that will help us to improve or to reduce our active Vmin and hence the total power consumption, thereby improving the energy efficiency of the bit cell. So the purpose of exploring or investigating these non-volatile SRAM bit cells. So let's take a look at some of the earlier non-volatile SRAM bit cells. The schematic on the left shows a 6 transistor 2R RAM bit cell, and it has one control line, RSL. The advantages of this bit cell is it's a zero silicon area overhead because the RRAM bit cells are formed on the back end of the stack. And also it is a dual-ended restore operation. However, the limitation of this bit cell is there is a significant intra-bit cell and inter-bit cell short circuit current, because one of the state of this RRAM would be in the high resistance state, other would be in the low resistance state. But now if you have this common RSL across multiple cells on the same row, then there could be a short circuit possibility or the sneak current possibility between the adjacent cells. And it may sometimes lead to functionality failures or metastability condition. So to minimize this effect, the other approach is one can now include additional transistor, the 7th transistor, and have only one RRAM bit cell. The advantage of this bit cell is it incurs zero intra or inter-bit cell short circuit current because of this isolation transistor. And on the flip side, it has 16% larger silicon area because of this additional transistor. And furthermore, it also has a single-ended restore operation. The next bit cell topologies are 7 transistor, 2 resistive RAM bit cell. So in addition to the 6 transistor SRAM, the 7th transistor is used to isolate these 2 RRAM devices from the adjacent devices. But nonetheless, there is still some sneak path that exists within the cell. And also because of the 7th transistor, because of one additional transistor compared to the 6T portion, it has 16% higher or larger silicon area. That brings us to the 8 transistor 2R bit cell, non-volatile SRAM bit cell, which has 2 resistive RAM devices along with the 2 additional transistors used for the isolation. The good thing about this bit cell is it has a dual-ended restore operation. And because of isolation transistor, there is a very minimal bit cell short circuit current within the cell and also with adjacent bit cells. But what is the drawback of making it a 8 transistor 2 RRAM bit cell? Because of 2 additional transistors which occupy the front end area, this bit cell is 33% bigger compared to the 60 baseline 60 SRAM bit cell. So if we take a look at various different non-volatile SRAM bit cells that have been proposed before, if we try to eliminate the isolation transistor, it incurs some short circuit or sneak path effect. And if we try to include that isolation transistor to minimize this sneak path, then there is a bit cell area penalty. And if we go with this 8T2R bit cell, which completely isolates the intercell leakage current, then the drawback it is 33% bigger area. Now, if you think about a high density bit cell, which is used in the last level cache, and when you have multi-megabit LLCs, the last level caches in a microprocessor, increasing that bit cell by 33% is not a good value proposition. Meaning thereby, just for the purpose of reducing the leakage, if one has to increase the bit cell area for 33% for this last level caches, it may not be good use of the area. So towards this effect, the key thing that we need from the emerging technology point of view is that can we come up with an isolation device which is back end of the line, and that can be used to minimize this intra-cell leakage current, and that does not occupy the front end silicon area or does not increase the transistor count. So to that effect, currently we do have which could be used for the isolation purpose and which can be integrated in the back end of the line. And one example is the selector device, in particular the threshold selector device. As shown in this middle figure, this threshold switching selectors, they exhibit hysteresis with respect to this voltage bias. And when the voltage exceeds a certain value, it abruptly transitions into a metallic state, giving very low resistance. And when the voltage across it drops below a certain value, it again transitions back into the insulating phase. And this is a volatile operation. This can be achieved with various mechanisms using various materials. For example, if you take a look at MOT insulators, the switching mechanism in these materials, such as vanadium dioxides, niobium dioxides, it is based on the principle of MOT transitions or Perel's instability transitions. And one can get this abrupt looking bidirectional transition. Also, it has some finite amount of switching time, and depending on the type of material and the fabrication method, one can get very high speed switching times. There are another way one can create this threshold switching selectors using conductive bridge RAM type of device, such as silver and copper doped hafnium oxide. And the key mechanism is this. In this case, the switching is based on the conductive filament formed in the silver and the copper ions. So such technologies exist. The question is, can I take advantage of these technologies in order to implement a non-volatile SRAM bit cell? And brings us to the proposed 6-transistor, 2-resistive RAM and 2-selector SRAM bit cell, as shown over here. This selector device and a resistive RAM device, it forms one branch connected to the storage node of a 6-transistor bit cell, and the other branch is connected to the second storage node. And they are connected by this common line called as the control line. The figure on the right shows the 3D interpretation of this proposed bit cell. And note that any additional devices we are adding in the back end of the line, so we are not increasing any front-end transistor in this design, which means we can implement this in a high-density 60 SRAM footprint without, and this could be useful for the last level cache of a microprocessor. And also, as I mentioned earlier, because of this non-volatile SRAM functionality, we can reduce the threshold voltage of the CMOS transistors of the 60 SRAM bit cell, which can provide us lower beaming and also zero standby leakage when we are in the state retention mode. So let's see how exactly this behaves. So in the SRAM only mode, we don't want any interference because of this additional back end of the line devices. So the control line is biased at VCC by 2, and the device parameters are chosen such that the selector device has a switching threshold which is above VCC by 2. So no matter whether the bit cell is storing 0 or 1, the voltage across the selector and the RRAM stack is close to VCC by 2, which keeps the selector device in the insulating state and with very minimal snake path leakage from this control line to one of the storage node. And the read-write operations of the SRAM bit cells are not affected except with slight increase in the capacitance at the storage node. Let's see how the state store operation takes place. It happens in 2 phases. In the first phase, the control line is raised to VCC. So if the left node is storing a 0, a current will start to flow from this node, CL node, through the left side PTM, the phase transition material, or the moving on to the RRAM device through the VL node, then to the NL node, and then into the ground. In the second step of the state retention or the store operation, the control line CL is discharged to ground, and in this case, we are programming the other RRAM in such a way that the current flows from the supply node VCC to the PR node to the VR, then the right side resistive RAM device, right side selector device into the VSS. So by having this two-step operation, one can program both sides of our RAM stack depending on the data stored in the storage node. One thing to note that the switching voltages of the RRAM and the selector device has to be within the same voltage range for this CMOS transistors, which are typically thin oxide transistors. So the programming voltages of this RRAM device has to be within the same voltage window as that of the rest of the logic transistors. Now let's talk about the restore operation. So the figure in the middle shows the timing diagram for the store, sleep, and restore operation. So during the sleep mode, the bit cell VCC is completely collapsed. The word line is also at 0. The control line is also at 0. So basically all biasing voltages are at 0. And hence there is 0 standby leakage. So when we are coming out of the sleep mode, the first thing is done is the control line is raised to VCC by 2, so as to make sure that irrespective of what voltage the VL and VR can have during the wake-up sequence, the selected devices are always in the insulating state and there is no accidental bit flip or any accidental sneak path from the random voltages which are present at this storage nodes. And then the supply voltage is raised up, and as a result, the VL and VR node can get set to some random values or undetermined values. So the next step that is performed is by boosting the word line voltage intentionally beyond the supply voltage and applying 0 on the both bit lines. What we are trying to do is trying to remove any residual charge from both VL and VR nodes, and we are intentionally boosting the word line so that this is a stronger device compared to any of the bit cell transistors, which guarantees that VL and VR are set to be 0. After that, once the word line is deactivated or deasserted, depending on the resistance difference or the RRAM resistance ratio, the VL and VR node will start to charge with the RC time constant, and this R would be determined by the RRAM resistances. And during this restore operation, the selector device is into the metallic state. And once it develops enough differential, the positive feedback action of the cross-coupled inverter pair turn kicks on, and that completes the full rate voltage transition, completing the restore operation. The figure on the right shows the floor plan of this array. In this case, we are performing the restore operation in a row by row basis, because during the restore operation, the current is flowing from the control line onto the storage node, and we are doing it at a first row by row level. This to minimize any inrush current that may appear on the supply line and which may disturb adjacent circuits which are sharing the same supply rail. And furthermore, the way this operation is done is we are first removing residual charge on the storage nodes and then performing this differential RC charging method. And that's why we are performing it on a row by row basis. So this slide again captures various operating modes of the proposed 62R2S non-volatile SRAM bit cell. Again, to recap, the SRAM mode, the control line is held at VCC by 2 so that the selector device remains in the insulating state and does not affect the underlying SRAM operation. The store operation takes place in 2 phases. The control line is initially raised to VCC to program one of the RRAM bit cells, and then it is discharged to ground to program the remaining RRAM bits of this NVS RAM. The restore operation takes place in 3 steps. In the first step, control voltage is raised to VCC by 2. In the second step, the supply voltage is raised to VCC by 2, and the word line is boosted above VCC to remove any residual charges from the storage node. And in the third step, based on the RC time constants difference, which are created by this resistance ratios of the RRAM, it completes it kicks in the feedback mechanism of this cross-coupled inverter pair, and that completes the full state retention operation. So now let's take a look at what exactly benefit it gives us in terms of the Vmin. And as I mentioned, Vmin is the minimum operating voltage for the successful operation, and higher VT typically results in higher sigma VT, higher variations in the VT, and that translates into the mismatch of these different transistors, which are typically minimum geometry transistors in the 60 SRAM. So this plot on the left shows the probability of failure plotted on the log y-axis, and figure on the x-axis shows the supply voltage. And this plot shows the right Vmin improvement for the baseline design, which is shown over here, and it has high VT transistors. And if we were to able to reduce the VT of the proposed NVS RAM bit cell by 50 millivolt and try to extrapolate this failure characteristics all the way up to 1 megabit array target size, one can get up to 120 millivolt lower right Vmin compared to the baseline high VT 60 SRAM bit cell. And if we do the same analysis for the read failure, so read failure plotted on the y-axis, supply voltage on the x-axis, and compared to the baseline SRAM, the proposed non-volatile SRAM with 50 millivolt lower Vmin, lower VT, gives us 100 millivolt lower read Vmin. And this analysis is done with 10,000 Monte Carlo simulations with a sigma VT of 30 millivolt and 10% variation on each of the device parameter. So one can see that by lowering the VT of the NVS RAM transistors, one can get up to 100 millivolt lower Vmin, and that can significantly improve the active power consumption. Now let's take a look at the total power savings. The figure on the left shows the total power as a function of activity factor. And this activity factor is how much time the array is being accessed for the read-write operation. So the figure here shows for the 60 SRAM, which operates at 100 millivolt higher Vmin. So in this case, it operates at 0.8 volt, compared to the proposed SRAM, the non-volatile SRAM, which operates at 100 millivolt lower Vmin. And if you take a look at this, there is a break-even point above which the proposed SRAM actually will consume higher power. And this is because how many times we are going in and out of the retention mode. It takes some energy to program this RRAM bit cells and also to restore the values from the RRAM bit cells onto the 60 SRAM. There is a cost associated with it, the power cost associated. So we cannot do this operation very frequently. However, for this last level cache where the activity factor is very low, one can expect significant power benefit using the proposed 62R2S non-volatile SRAM bit cell. And figure on the right shows the total power consumption as a function of memory capacity. And as the memory capacity is increased, one get larger saving in this total power. And that's where it becomes very attractive, especially for the last level caches, which typically use high density SRAM bit cells, and they're predominantly in the sleep state. They're very accessed very rarely. So this brings me to the summary or the key findings of this research work. So we proposed a non-volatile SRAM bit cell using resistor memories and selector devices as the technology assist rather than any circuit assist or any transistor level assist. And we are enabling the state retention functionality in the same 60 high density SRAM footprint without adding any additional transistors, front-end transistor. And that has a huge implication in terms of enabling it in a HD SRAM footprint. Furthermore, because we are performing the state retention operation in situ, we can decouple the VT and the Vmin requirement that is otherwise present in a conventional 60 SRAM bit cell. And because the VT of the transistors can be reduced, as we don't have to worry about its leakage during the sleep mode, because that is taken care by the non-volatile feature. And because of this reduced VT, we get lower Vmin, and that translates into lower power consumption. One thing also I want to mention that on-ramp devices and selector devices, they have limited endurance compared to the logic transistors. Then the question may arise whether they are really okay for this non-volatile SRAM operation. The answer is could be it's a positive answer because the rate at which we are entering into this state retention or coming out of the state retention is not that high compared to the active mode of operation. So as long as we maintain the enough sufficiently low probability of going in and out of the state retention modes, it is possible to use the limited endurance RAM and selector device technologies for this purpose. So this concludes my presentation. And once again, I would like to thank the conference organizers for giving me this opportunity to present this work with you. And feel free to reach out to me and send me an email if you have any questions. Thank you very much for your attention.
Okay, so let's thank Professor Kulkarni for sending his recorded presentation. So, are there any questions? So then I will share it with him, and he will get back to you. Are there any questions?
Sir, I think there are a couple of questions from Dr. Vinayak.
Yeah. So I think you could.
Can you see the chat box, sir?
Yeah, I could see the chat box. So basically, I'll I'll mail these questions to Professor Kulkarni, and he could, I think, answer those questions via email.
Okay, sir. Okay, and then we will forward those answers from him to Dr. Vinayak.
Yeah, sure. I'll copy Dr. Vinayak. I think we have mail ID of Dr. Vinayak, so I think we could do that.
Okay, thank you.
Thank you.
Okay, so I think our session is now over. So I like to thank all the participants for joining this session, and we'll have another session starting at 2 o'clock. So I hope all of you could join again at 2 p.m. So thank you and goodbye. So Manoj, I think we'll
Yes,
talk
sir.
to Wilfred later, right? So
Yes, sir. He is requesting to deliver his talk tomorrow. So tomorrow, anytime we can reschedule his talk. Yes, sir.
Okay, let's see then.
Okay, sir. Thank you.
Okay. So Saibal, I saw you joining. So
Yes, hi Nihar, how are you?
I'm fine. So we'll join back at 2 p.m. right? In this same
Yes,
room.
session starts at 2. Yes.
Okay, then see you then at 2 o'clock.
Okay, see you Nihar. Yeah. Thanks. Bye.
So ICW team, can you play the theme?
Yes, sir, sure, facing.
Okay.
from IMEC. I will present device architecture evolution from nano-C to CIF for CMOS getting to N2 and beyond. First of all, I would like to appreciate organization committees of this conference for giving us opportunity to present our latest device special. We have two in we develop this how we deal with between top and bottom. So those is a challenge has to be tackled properly for the future is the CMOS switch CFET integration.
Hi Manoj, can you hear me? Sure. Should I talk about this? Fine. This is VH. Hello, Manoj, can you hear me? Hello.
Hello, sir. We can hear you. Ahmad this side.
Hi, Ahmad. So, this is then. So, the talk begins at 2 o'clock. Is that correct?
Yes.
Okay. So, should I just see if you can see my screen?
Sure, sir. You can share and check it.
So, I'm sharing my screen. When I say share, yeah. Can you see my screen?
Yes, sir. I can see your screen.
Okay. Beautiful. Okay. Okay. Thank you. So, I'll just
Sure.
join maybe after you guys are ready. Thank you.
Then how are you?
Hey, how are you?
Going on?
Good to see you, Shaival. Hi.
Yes, 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 yes. So you're
So
back
we're
to
all at
India?
home.
Yeah.
Yeah, India.
Okay, okay, that's good.
How are things in Indore?
Yeah, it's okay. Cases are still rising, but otherwise it is okay, fine. Yeah, it is fine.
Mhm.
The COVID
I
cases are
see. I
still
see.
on the rise, but otherwise everything else is okay. So how the things in
But
Mumbai?
institute is
Yes.
got it.
So how are things in IIT Mumbai,
Scary,
Bombay?
right? I mean,
Yeah. Yeah, can you hear me then?
like take off my video.
Yeah, that is what also what I have done. I just switched off my video thinking that the internet connectivity might be an issue. So can you hear me now? Hello? Hello, Udan, can you hear me?
Yeah, I can hear you. I can hear you. Can you hear me?
Yes. So that is the exact reason also yes, yes, I can. I just switched off my video as well, thinking that connectivity might be an
Okay.
issue, and that's why maybe that's why I closed my video.
Yeah. Yeah. Yeah, it's pretty crazy.
So how are things in IIT Bombay?
IIT Bombay, it's I mean, we are struggling to get our students back. I know that some of you guys are doing
Okay.
slightly better than that, right? I mean, meaning I think your students never left or something like that. I
Yeah,
think
they
IIT
have
Gandhinagar. Go ahead.
no, they have left, but initially they were allowed phase wise in a phase wise manner, like
Oh, okay,
70
okay.
to 80 students each. They did
Mm-hmm.
the re-entry of the PhD students to IIT Indore campus as of now. Masters
Mm-hmm.
and BTech students are not available, but yes,
Mm-hmm.
in phase wise manner they have just allowed.
I see. I see. Okay, got it. So what about classes? You guys have, I mean, I know that you guys have started, right? I mean, you are.
Yes, our in semester has just finished. It finished day before yesterday, and our next semester is going to start. First year classes has already started, like BTech first year. Our next semester is starting on 21st of December. Like almost no gap in between.
Wow, that's intense.
Yeah.
Yeah. But
Hi,
the
Manoj.
weather.
Yeah, Manoj, are you online?
Yes, sir. Yes, sir. I'm here. Yes, sir.
Yes. So should we start the session because it is almost 1:59?
Yes. Sorry, sir. Sorry, sir.
Yeah. Should we start our session because it is almost time?
Yeah. Yes, sir. Yes, sir. Can you hear me?
Yes, I can hear you.
I think we can start, sir.
Yes. Actually,
So
intentionally, yes, Uday, please.
Go ahead. So one question, Shwebal. So how long is this thing? Just so that you, I get a sense. So this is about. So talk is till 2:30, right?
Yeah, your talk is 2:30. Yes.
So I should finish by 2:25 or something, right, or something like that.
Yeah, that should be fine.
Okay.
That should be fine. So actually, I have stopped my video, Manoj, because there was some problem in the internet connectivity. I think both me as well as Professor Udayan, we have stopped our video because initially we started it and then it was some network issue.
No issue, sir. No issue.
Okay. So, okay, formally, I'm Shaibal Mukherjee from IIT Indore. I would welcome you all in the session of ICEE conference in the session number 2. Starting with the invited lecture in this session is from Professor Uday Ganguly from IIT Bombay. So just to give you a brief information about Professor Uday, because already many of you who are working in this domain of research activities, you may be well acquainted with the work of Professor Uday at IIT Bombay. So Uday Ganguly received his BTech degree in metallurgical engineering from IIT Madras in 2000. And then he moved to USA, Colin University, where he received his MS and PhD degrees in materials science and engineering. In 2006, Udayan joined Applied Materials to serve as the technical lead for flash memory applications development at Applied Materials Front-End Product Division at Sunnyvale. He has joined the Department of Electrical Engineering of IIT Bombay in 2010. He has authored or co-authored more than 50 journal articles, 90 conference proceedings, and more than 25 patent, both under applied mode or granted mode. His research interests are in semiconductor device physics and processing technologies for advanced memory computing and neuromorphic systems. He likes to experiment with teaching/learning methods like think, pair, share. He has contributed to the TFAC National Vision for ICT 2035. He works to augment national semiconductor manufacturing capability at Semiconductor Labs, Chandigarh, for which he has won the Dr. P.K. Patwardhan Technology Development Award 2018. He has been an editor for IEEE Electron Devices Letters since 2010. So today his lecture is on experimental demonstration of 3-terminal PCMO-based RRAM for efficient in-memory computing. So with this, I just would like to invite Professor Udayan to please share his idea and research with us. Thank you.
Yeah, thank you, Shwebal. I hope you can all hear me and see the screen.
Yes, definitely. Yes.
Okay. So thank you for the very kind introduction, Shwebal. You know, it's a very small community in India and it's growing and all of us know each other, and the people who are in the audience, I think, you know, we expect, you know, interesting ideas from you and to sort of take the work forward. So in that light, you know, we would want to talk about the kind of work that we are doing at IIT Bombay. On the top right, you can see the IITB nanofab. So we have a nanofab in our campus, which is one of the oldest in India. And it enables us to sort of work on experimental nanoscale devices. And this is an example of that. So this is an experimental demonstration of 3-terminal PCMO-based RRAM for efficient in-memory computing. The work is primarily done by my PhD student who's just graduated, Dr. Sandeep Lashkare. And from a simulation modeling position, Vivek Saraswat, he's a PhD student, he's been supporting it. So, so quickly, I think there's a time button here somewhere, or maybe I should just use my phone. Okay, so quickly, so this is the overview. So you have, I'll talk about a little bit about neuromorphic engineering, and then we are going to talk about how we work on 3-terminal RRAM, how do we fabricate it, and then what sort of physical questions or physics questions we answer. And then ultimately we want to go and talk about in-memory computing, and then talk about future work. Okay, so very quickly, neuromorphic computing, why do we want to do this? Well, there's a computer, and then the computer essentially was made or conceived and developed by the human brain. So if one really ultimately wants to demonstrate the best computing machine that humans understand or know, it must be the brain that we must try to replicate. So there are many aspects of the brain which are very interesting. So there is self-learning, it's compact, it combines storage and computation. It's very extremely efficient in power, very robust, meaning that you can jump around and you can sort of, live until 80 years and then your brain still keeps working. And it's the ultimate real life problem solver, right? Which is something that computers aspire to do. So what is the numbers? So the numbers here are the brain works roughly at 10 watts versus a supercomputer on the right, which works at about a megawatt. It has many CPUs, this supercomputer, and this one is pretty small. It's about 2 square feet, about 1,000 times smaller. And this is area efficiency. There's a power efficiency, and overall, I think the brain is cranking out about 1 million times more energy efficient operations than a computer for the same energy. So this is pretty exciting. So what are the aspects of the brain, or what are the components of the brain that one needs to sort of study? And for people who are not biologists, like electrical engineers and material scientists, what we look at is that everything for us is an input-output system. Let's sort of take that abstraction level. So there is a synapse and there's a neuron. So that's what the two elements are. And let's look at what are the input-output behavior of these two. So the synapse, essentially, the input of these are spikes. So these spikes are some sort of very high frequency, sharp signals. And these are essentially voltages as a function of time. The output is a current as a function of time. And the current essentially is a much sort of more gentle variations. So you can sort of think of this as a low pass filter that converts the spikes to voltage spikes to current. Then what you have is the neuron. So the neuron sort of accepts this current in the synapse, and so it has the gentle currents that come as input, and then it drums out these spikes. So you can think of it as a converter of sort of spike frequency as a function of the input. So it's almost like a voltage control oscillator. So for us, a low pass filter and a voltage control oscillator are things that humans understand or electrical engineers understand very well. And so these are good abstraction levels for us to build systems. And at this abstraction level, it is sort of interesting to ask the question that, how is the neuron able to sort of build really large efficient networks with these elements? Okay, so so to do this, now there are 3 levels. So first is the device level. So the brain, as we realized, has synapses, and synapses are roughly memories. Then there are neurons, and neurons have sort of a more complex function. They are like voltage control oscillators, and that's essentially a small circuit. So you do have your device and you have your circuit, and then ultimately you have your system, which means that you may want to sort of create a connection between one neuron and a synapse and then another neuron. And then ultimately you may want to have many neurons connected to many other neurons through a crossbar of synapses. And that would essentially be something like a neurosynaptic core, which is a circuits question. And then that should be able to demonstrate an algorithm. So this is very exciting in the field because, you know, device engineers have essentially been working in silos because the circuits and the architecture part for digital systems or analog systems is very well developed. But in neuromorphic engineering, it's a sort of a place for generalists. And you can sort of do interesting things here by looking at the entire sort of chain of ideas, or sort of the entire vertical integration of all these aspects, right, from devices to architecture. So what are the different devices that we can build? So out of PCM-ORM, we have built synapses, we have built neurons, and today we are going to talk about in-memory computing. So what are the synapses? So synapses have this thing called spike time dependent plasticity. People who know this, this is something like, you know, if you have an input neuron and an output neuron, or a pre-neuron and a post-neuron, and there's a synapse, then the synaptic conductance changes as a function of the time difference between when this spikes and when that spikes. So when the pre spikes before the post, it's called causal. So the pre caused the post, and so the conductance will increase more, meaning that that connection is strengthened. And if the pre spiked after the post, which means that the pre could not have caused the post, then the conductance would reduce, which means that that connection would weaken. So this is called spike timing dependent plasticity. There are many sort of biological patterns of this spike timing dependent plasticity, where the x-axis is time difference between the two spikes, and the y-axis is conductance change, and lots of shapes are there. So our group had demonstrated analog conductance change based on PCM-ORM, and then we had come up with a generalized scheme of creating different types of STDP, and these were published in EDL. Then we have also created what are called energy efficient synapses by combining an RAM with a selector experimentally. So the selector is an NPN selector, which is bipolar, and the RAM, of course, is also bipolar. So what happens is that when you apply a waveform on this RAM, which is how you get these STDP curves, you can essentially get your voltage profile, and along with that you get a current profile, and the voltage times current is the power, and the integral of that in time is energy. So you really spend a lot of energy doing these long waveforms. As you can see that they are milliseconds long, because brain has that sort of time scale. Now if you really want to ask the question, is this efficient? Well, the answer is not really, because you really want current to flow only when there are these spikes, and not during this waveform. So what we had done was to add these sort of thresholding elements or selector, and here we adjusted the input voltage, and the output voltage essentially became output current essentially became pretty much non-existent, except for when there were spikes, and the energy consumption was reduced. So these are good ideas, meaning that they are ideas that will enable systems level improvement by device engineering, or by putting two devices together, which are emerging in nature. Then the question of neurons. So neurons are essentially integrate and fire. So RAM is a memory, and one can definitely demonstrate how integration works. So Just to sort of give you give you a little background, here is a PCMO RRAM. So here is PCMO, there's tungsten and platinum, these are the 2 electrodes. And you can see your hysteresis loop. And the point here happens to be a point of current shoot up, which essentially means that there is sort of a positive feedback between current, which causes self-heating, which causes ions to flow, which reduces the resistance, which increases more current, and so on and so forth. So this happens, and then one can use this sort of a process to do this, create a cumulative, a sort of an additional, an adding process, an additive process, where as it receives more and more spikes, you can see that the conductance would sort of increase in this RRAM, and then beyond a point it'll exceed a threshold, and after that an external circuit would reset it. So you can do this experimentally now and show that depending upon the input you can get different spiking patterns. So this is about -2.4, this is -2.5, and you can get spikes. And similarly, you can sort of also change the time and also get different kinds of spikes. So this is sort of the overall picture of neurons and synapses, which is what we had done in the past. Going forward, what we want to talk about is the topic for today, which is in-memory computing. So what is in-memory computing? So this is essentially this idea that if you have an input to a computer, what the computer does is that it takes the input into the CPU. The CPU then would like to compute something with this input. To compute something, it would require some prior information which is stored in the memory. When this memory is accessed, it sort of consumes energy, right? And the CPU has to wait. And then the CPU sort of computes things, and the result of this computation is again put back to the memory or pushed out as an output. So this is how things have happened. And in the paradigm when you would sort of require very little memory, but you want to do a lot of computation, this was fairly efficient. But in cases of things like search, or in the case of pattern recognition, where the whole idea is to compare the data with lots of past information, then this becomes the bottleneck, right? Where you really are sort of struggling to with the bandwidth of memory. So the next sort of paradigm shift has been to add memory directly into the CPU and to do computing there. And essentially, that doesn't mean that your memory sort of is in one block and the logic is in another block. What this means is that one block consists of memory and logic together, and it sort of takes the input, processes it, and stores the output in the same array, and then also passes on the output. So this is sort of a memory logic enmeshed architecture, which is closer to the brain. So what do we need for this? Well, we definitely need a computational device which can do this. And things can be, for example, inputs can be voltages, and the output can be the state of the resistor, right? So this is an RRAM example. Okay, so let me not go into this. Okay, so let's look at what is called a complementary resistive switching, by which I want to do an AND operation. Okay, so let me say that this is my device. So this is the RRAM. The RRAM essentially is bipolar, which means that it is directional. So these are anti-parallel, meaning that if you look at sort of this is facing, both are facing down, but they're anti-parallel with respect to the ground and the voltage sources. Okay, so that's why they're anti-parallel. So now what I need to do is I need to first reset this device and make it, some standard state. Then I will write the information. So I will write the top device first. Then in the next cycle, I'll write the bottom device. And once I do that, then I'm ready to go to the computational state. Okay. So in the computational state, what we'll do is we'll apply a voltage and we'll compute some sort of a logic function. So what is a logic function? Let's look at an AND function. So look at it here. So here is my I've added in different kinds of data, right? So this is low, low, high, 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 low, and low, high. So these are my inputs. And once this is written, I can now apply a VDD and a ground to all these cases. Now, when I do that, then when this is low, low and high, high, then this point in the middle is between VDD and ground. So I can set it such that this voltage difference is much below the tripping point, right, when the memory is written. Next, if this is high, low, then this position, essentially the voltage here is closer to ground. And so a significant voltages exist in the top device. And this polarity is also correct, right? So this one switches. Now, if this was flipped, which is this low and this high, then the point potential in the middle would be higher. If this is high, then of course there's a high potential difference on the bottom device. However, you can see that the direction of the polarity is flipped, meaning that the direction here is the same, but the device is flipped, right? Hence, this one will not cause a write because it's a bipolar RM. Having done this, what this one will do is this will convert it to low. And now if I just read the upper device, I will see that this is a low, high, low, low. So I can now read this as an upper device, and you can see that this is an AND operation, right? So this is what this sort of a two RRAM complementary resistive switch can do. Now, what can I do better than this, right? One interesting thing would be to sort of take an RRAM and then apply voltages, right? So let's put it in high resistance state. Now, if I apply low, low, then there's no potential difference. If I apply high, high, there's no potential difference. If I apply high, low, then there's a potential difference and the field is in the right direction. So it will switch and it will go to low. And if I do a low, high, then even if there's a potential difference, the direction of the potential difference, that's the polarity, is wrong. So this will not switch. So ultimately, this would give me a switch, which is that it will give me a low output, which is essentially an implication operation. So this is for a two-terminal RRAM. But now, if I want to read this, I'll have to wait for this voltage to go away, and then apply a read voltage and then read it again. So there's a second state of read that I need to put in. Okay, so so here what we see is that there are many steps to this. One is initialize, one is to write the data, and then the second is to compute and then to read it out. Now, if I could create a three-terminal RRAM, then what I would do is I would essentially have the third terminal coming in and sense this out within the same cycle, right? So ultimately, if my three-terminal RRAM, I would only have one write cycle. I'm not sort of computing, talking about the initialize. Like initialize is common, and there is no extra read cycle. So this is very efficient. So just to sort of quickly go through the fabrication, what we came up with is sort of a standard RRAM process where you have a two-terminal RRAM and we modified it. So we sort of had the bottom platinum layer. On top of that, we sort of did a sandwich structure where we had zirconium oxide, platinum, SiO2. And then on top of this, we deposited tungsten PCMO in the hole here. There's a hole here, right? And then we opened up this SiO2 here and put a electrode to touch. So if you think about it, then this is your tungsten, this is your PCMO, this is your platinum. So this is your standard vertical RRAM. And then you sort of sneak in a platinum electrode on the side. And this is your three-terminal RRAM. So this is the fabricated device SEM. And this you can see is the top view. What you can see is this is the third terminal. This is the top terminal. And this small hole here is that edge contact device that exists. So I'm sort of doing a little badly on time. So what you can see is that, I can do program and erase here. So this is programming and this is erasing. And when I then take measure between the side terminal, this T3 and T2, I see that there is a difference between the high resistance state and low resistance state that I can pick up. So this means that I am able to sort of sense this. And now, how good is the correlation? So we can do a gradual reset. So this is my reset voltage and reset resistance in this between the T1 and T2. And you can see that there's a very large change in the resistance. Now, if I measure between this T3 and the T2 on the lateral side, what you can see is that I do pick up a correlation, which is very clean, but it is, you can see that the ratio is very low, but it is still able to pick it up. Similarly, for set, I can do the same thing. So also set, I can change the resistance, and it is fairly large, and I do it by current compliance. And as a function of current compliance, I also see a resistance change that I measure, and it's correlated. But again, the ratio is much, much smaller. So we sort of are able to do this. Now, I think that I am a little out of time, so I will not go through the modeling work. But what I would sort of like to show you is that once this is done, right, you can sort of look at a NAND operation. And this is NAND. So you have this truth table, and we can put in inputs and input 1 and input 2. So here you have your input on the left and input at the top. So third terminal is input and top terminal is input, and the output is the current. And you can see that there is a very nice output that you can see, which gives you an AND operation. You can also do an implication operation, which was what we discussed, that you have this vertical RRAM, which will give you an implication operation, but then in parallel you can read the state with the third terminal. So you can also sort of see that you can measure this nicely. And you can also do what is called a converse implication, which is nice. So overall, we've been able to sort of demonstrate three universal logic gates with this 3-terminal RRAM. And what we show is that these are the different papers that people have worked on. Here are the different points of comparison, the kind of materials, the cell type, the mode, which is sequential or parallel, number of terminals, number of devices, number of steps, which means how many cycles do you need to do this, and do you need an extra read. And in all this, I think this is where we are. So we can do a parallel operation, 3 terminals. We only need 1 device, we only need 1 step, and we don't need an extra read. So this makes this a fairly significant capability demonstration. So to conclude, we have made a 3-terminal RRAM, which is successfully fabricated, and the third terminal is about 20 nanometers thick or wide. And the PCMO shows very interesting interface switching, which I did not sort of talk about. We were able to do these NAND and implication operations, which enable in-memory compute. And essentially, the in-memory compute that we can demonstrate is essentially a 1-step single device. And it is essentially owing to this bulk conduction mechanism, which, of course, I skipped. So with that, I wanted to thank you, and I can take questions as needed.
Thank you very much to Professor Udayan Ganguly for the wonderful talk. And now the floor is open to questions. Any questions from the audience?
So one question from my side, sir.
Yes, please go ahead.
Yeah, sir, during that current, there might be some variability for this PCMO devices. So how are you considering for logic gate this 0001? Yeah, there might be some variability. Like, so how are you considering that things, that variability from devices to devices, or from like if it's in a big circuits or in an array, there might be some variabilities.
Yeah, so this is a very good question. To back up a little bit, variability in RRAMs, in filamentary RRAMs, is supposed to be legendary, right? I mean, there's a lot of work on how filamentary RRAMs are difficult to deal with. This is a bulk conduction RRAM, so in that sense, the variability is much lower than a standard RRAM. However, your point is really correct. There is variability. Now, what we don't know is that whether the variability comes from the fact that we are making it for the first time and our processes are not very controlled, or these variabilities are fundamental. So this is something that we need to work on, and going forward, we need to sort of establish. But PCMO RRAM variability being low is something that we have established earlier. And for memory applications, for logic, of course, the requirements are maybe more stringent. That's a very good question. Thank you.
Okay, thank you, sir.
Thank you. So, Udayan, I have a question. This is Nihar here.
Sure, hey, Nihar.
The voltage levels that you are talking about is around 1.5 volt, kind of.
Yes.
Yeah. So, and the current, basically, your threshold current is almost around 6 to 7 milliamperes. So this is a high current value. So how are you planning to handle this current, and how will you read this current, because the output is in current form?
Yes. So this is a good question. So first of all, Nihar, the current values are high because these are still large devices. Okay, meaning that though the lateral third terminal is very nanoscale, right? The area of the device is still 5 microns. Okay. So, and this is area scalable. So typically, if I go down to say 50 nanometers, then I would get about 100x reduction in current. Okay.
Okay.
So in fact, even more, I think. Yeah.
So
maybe 10 to the power 4x, right? So that's a lot of current reduction. And the second thing is that the readout is for sure current, and that needs to be handled. So also the state of the memory, right? In memory, you always sort of measure resistance, right? And the way to measure resistance is either by passing a current and applying a voltage and passing a current, or applying a current and finding a voltage, right? So that is something we have to figure out. What is the best way to do it?
Okay.
Yeah.
So what about other kind of gates? What about NOR? You definitely might be trying, but is it possible?
So what we figured was that, because we have these are universal gates that we have shown, right? So the universality of it is definitely something that is demonstrated. But you're right. I think the ability to demonstrate other types of gates, even which are universal gates, would be interesting. And but my PhD student who did it just graduated, so so I need the next person to pick it up.
Okay, and this RRAM will be in the front end, or let's say you are planning it in the normal technology, so it will be in the front end or back end. This will be in the back end mostly.
So this PCMO RAM, this is also again a very interesting question. So the PCMO RAM has one fundamental flaw. Okay, it requires about a 650-degree anneal. So it has to be midline, right? I think most of the RRAMs which are backend compatible end up being filamentary. Some of them are not, but then there are other problems. But this is a fairly ideal system, but there's that one flaw. So, but from a logic point of view, this is okay, right? Because in principle, you need lots of routing in logic, right? And in that case, maybe front end is better than back end.
Okay. Yeah. Okay. Thank you.
Okay.
Thanks.
Thank you so much, and thank you so much to Professor Udayan for the wonderful talk and wonderful discussion we had. The starting session for these Icee conferences. Thank you so much. I once again, share our heartfelt thanks to Professor Ganguly for this wonderful session. Thank you.
Thank you, Shribal. Thanks a lot.
Now our next speaker, I think already he's with us, Professor Andre Godoy. Yeah, Professor Godoy, can you hear me?
Hello?
Yes, Professor Godoy,
Hello.
can you hear me?
Yes, I can hear you. Can you hear me?
Yes,
Okay,
definitely.
perfect.
So our next speaker is Professor Andre Godoy from University of Granada, Spain. So just to give you a brief introduction about Professor Godoy. So he is the professor in the Department of Electronics and Computer Technology at the University of Granada, Spain. He is a reputed expert in analytical and numerical modeling of electronic devices, semi-classical and quantum transport in heterostructures, and leads an emerging line in simulation and modeling of 2D materials devices at University of Granada. He has participated in more than 27 research projects, both as PI and as collaborator at national and international level. Professor Godoy has been a researcher at the Beckman Institute of University of Illinois and at the University of Siegen, Germany. He is author or co-author of more than 90 journal articles, 3 book chapters also is published, and is a regular contributor to international conferences. He has been the chair of the MSc program in physics at University of Granada for 6 years. So today, his lecture will be on nanobiosensors for the detection of ions and biomolecules. Professor Godoy, the floor is all yours.
Okay, thank you very much. Can you see the slides?
Yes, Professor Godoy, you can see.
Okay, perfect. So first, I would like to thank all of you, the organizers of this international conference, and especially to Professor Nihar Mohabata for giving me this nice opportunity to present our results related with the study of nanobiosensors. As you mentioned, my name is Andres Godoy, but I also would like to thank all my collaborators, Alejandro Toral, Juan Cuesta, Enrique Marín, Francisco Pasadas, Juan Rodriguez, and Francisco Ruiz, all of them members of the same institution. This is the outline of the talk. First, I will begin with a short introduction and motivation about the growing importance of this field, especially nowadays, where the early detection of viruses and diseases is of utmost importance. I will try to provide some description, not very exhaustive, of recent advances in materials and devices that are trying to increase the capability to detect different chemical and biological species. And I will present some examples of recent technology development that are showing new fascinating applications that demonstrate the quick evolution of this field. Next, in the second section, I will give a brief historical introduction to the application of the FETs for ion detection and mainly for pH sensing. From there, some fundamentals and basic concepts that are necessary to understand the basic performing of any biosensor. The third point, I will try to dedicate it to the advanced simulation and modeling of biofets, where I will show some of the main results of our research. And finally, just to finish the talk, I will wrap up the main conclusion. Let's go with the introduction. So the possibility of detecting and quantify the presence of different ions, biomolecules, chemical species that could be present both in the environment or in the human body is a topic of interest, not just for today, but from decades ago. But currently, due to this sanitary emergency that we are facing all around the world, these topics are concentrating a lot of interest for an increasing number of research groups. The amount of potential applications for this kind of devices is huge. And just to mention a few, we can talk about environmental monitoring, food safety, tracking security and explosive, and also especially preventing healthcare and medicine through the early detection of biomolecules related to a specific disease. In addition, all these applications are mainly those related with wellness and medicine are being inserted inside the broader context of wearable electronics and the Internet of Things, thanks to the use of mobile phones and also of the cloud computing. And the logical consequences to this disruptive technology is the growing interest of the companies, and it is estimated that the market for biochemical sensors is going to get around 59 billion for just next year, as according to the Trends Market Research. Focusing more specifically on biosensor, the development of this technology is based on a multidisciplinary approach, and because the development of this kind of biosensor is based on different topics of material science, chemistry, biology, physics, electronics, engineering. So all these subjects has to be combined just to achieve the successful implementation of biosensors. Most of the recent progress achieved in the nanomaterial synthesis and nanofabrication have created attractive opportunities for developing biochemical sensors with small dimensions that try to enhance the sensitivity. In recent years, a wide variety of nanomaterials and devices have been designed for a specific application with active materials that include organic substrates, such as, for example, pentasene, and also other ones, like, for example, P-DOT, PSS, with this strange and long name that you see here. I'm not going to the advantage of this type of materials are related with the compatibility with the living beings, reduced cost, and also the flexibility, which is inherent. But the drawbacks on the other side are related with the lower performance and quick degradation. Other group of materials that are attracting interest is the ultra-thin two-dimensional materials that seems to be appropriated to implement biosensors, considering their mechanical, electrical, and chemical properties. The most fascinating feature of these 2D materials is that they are atomically thin, and therefore they provide extraordinary softness and flexibility to the device that are fabricated. Graphene, maybe is the best known member of this Y2D family, is very stable, chemically very stable, and promising high compatibility with the human body, and also allows the fabrication of flexible devices. Here, let me show you an example of graphene transistor that have been employed for the detection of action potentials in neurons, and also for ion channel opening in kidney cells. Graphene neuroelectronic system is a very active research topic that tries to develop neural implants for electrostimulation in the clinical treatment of mental diseases, as well as for the creation of soft human-machine interfaces. Additionally, also molybdenum disulfide has been employed for the fabrication of extremely sensitive pH sensors. Well, let me also mention silicon, and maybe you can wonder why silicon can be considered as a new material, because it has been also used for decades in the fabrication of integrated circuit. But the thing is that for biosensing application, silicon is designed in the form of nanowires, nanoribbons, or nanomembranes, so which are completely different to the traditional technology. See here? For example, I want to show you a schematic of a silicon nanowire sensor that has been functionalized with an antibody receptor, shown in green, and how the binding of a protein, shown in red, yields a decrease in the conductance. Okay? Below, it is depicted the cross-section diagram of a scanning electron microscopy image of a single silicon nanowire and a photograph of the sensor biology. Here on the right, we can see the image of a scanning electron microscope of a reticular bioactive scaffold made of silicon nanowire, and below you can see the photograph of a multiplex array of silicon nanomembranes on flexible polyimide in contact with the cortex of a rat. More information about this implementation can be found in the web page of the corresponding research group here, Professor Lieber and Professor Roger. But independently of these materials and structure, it is expected that they show improved performance in terms of sensitivity and response time compared with the current implementations of the traditional sensors. Let me, just to finish this section, let me show you an interesting new type of biosensor. Really amazing because they have the capability of physically disappearing or disintegrating through hydrolysis and bioresorption. The figure represents here the implementation of a silicon nanomembranes that behaves as a pH sensor. But interestingly, in the bottom row, you can see how the sensor disappears after immersion in a solution in just 12 hours at room temperature. Now, in this second section, I will try to provide some fundamentals and basic concepts required to understand the behavior of biosensors. To begin, I would like to mention the pioneering works of Piet Berger with the first application of the FET transistors to measure chemical compounds in the neurophysiological realm already in the 70s. Okay? After that initial work, a considerable attention was paid to the development of electronic devices sensitive to different ions and chemical species, giving rise to a new pole of devices, the so-called ion-sensitive field effect transistor. And for a comprehensive review of this topic, I recommend this reference. Okay, it's a little bit old, but just for the history of the first lecture. Attending to these historical reasons, I focus on the effect, ion-sensitive effect, that share features that are common with the conventional MOSFET. The structure represents a semiconductor channel connecting source and drain. And then on top of that, there is a dielectric layer deposited on top of that. And the main difference with the conventional MOSFET is the metal gate is eliminated. And then instead, we have a liquid electrolyte in direct contact with the surface of the insulator. And this electrolyte contains a wide variety of ions, molecules, and compounds that we try to identify. An important feature is also that a reference electrode here on the top is inserted, and this is usually made of silver or silver chloride, just to provide a stable potential in the electrolyte that allows the measurements of surface potential variation. The basic working principle of FET sensor is based on the modulation of the conductance of the semiconductor channel produced by the binding of ions or sharp molecules on the FET surface. This attached surface charge modulates the carrier density in the channel in a way that is analogous to the application of a gate voltage that changes the threshold voltage, so that this analyte-induced voltage was achieved in the source to drain voltage and the current. And as a result, the FET sensor usually operates on the basis of estimating variation of this drain current. Actually, the sensor sensitivity is usually defined as the normalized current response. And this is the typical definition of sensor sensitivity, although no, it's not the only one. The transduction limit of the device depends on the rate of diffusion of the analyte to the sensor surface. The development of nanoscale bioeffects has demonstrated an advantage compared with the traditional planar devices for detecting low concentration in the order of femtomolar. And the explanation is related with the geometry of the system. For example, here, in this case, when the analyte is absorbed by the surface, A concentration gradient forms in the solution, and the analyte, which is located far from the sensor, must travel through it to reach the sensor surface. And the time required for this analyte to reach the surface depends on the geometry. And in this case, in the case of this planar structure, the diffusion is produced only in one dimension. However, in the case of nanowire, the response times is faster. The reason has to be that the molecules are coming from two different dimensions, from two different directions. And this is a specific consequence of the reduced dimensionality. Once the analyte reaches the sensing surface, several reactions can take place. Here, motivated by its importance, I will explain the processes that take place to detect the presence of hydrogen ions that are used to evaluate the pH of the solution. The model commonly used for the absorption of the hydrogen ions is the side binding approach. This model is based on the chemical reaction that are shown here, and they are produced at the sensor surface in the reaction with the electrolyte. We assume a surface made of silicon dioxide, but different insulator can be also employed. It contains a high density of hydroxyl groups here shown that can be neutral, positively charged, or negatively charged. These two reactions are described by the corresponding dissociation equilibrium constant that are expressed as the ratio of the concentrations. Protonation and the protonation of these hydroxyl groups at the surface produce a difference in the hydrogen ion concentration between the surface and the bulk, and therefore a modification of the surface pH value compared with the bulk one. Normally, the surface proton concentration is related to the bulk concentration in the electrolyte through the classic Boltzmann distribution. Additionally, we have another parameter to consider, which is the total number of available sites of the interface related with the structure and the quality of the interface. Any available site at the interface can be neutral, negative, or positive, and then we can obtain an expression for the net surface charge, this one, as the difference between the positive and the negative groups. So after some algebra, we can obtain an expression that depends only on the proton concentration, the dissociation constant, and also the surface, the number of available sites at the surface. So everything here is already known for most of the material, like for example, silicon oxide, aluminum oxide, and tantalum oxide. And the only unknown is the proton concentration that can be solved in a self-consistent simulation. So we have seen that this surface concentration depends on the classical Boltzmann distribution. However, this model has a problem, is that it considers that the concentration at the surface can be very extremely high when a large voltage is applied. And the result sometimes leads to some unphysical values of the ion concentration at the surface. So this phenomena is known as aesthetic effect, and make reference to the fact that the ion concentration gets saturated at the surface. Therefore, it becomes mandatory to model this effect to avoid a physical situation produced by this unrealistically high concentration. So one solution was the use of this modified Boltzmann distribution, which takes into account the effect of the ion signs through this parameter A, which is the ion radius. The effect of this modification is to achieve a limitation of the maximum ion concentration. So we can see here that the ion concentration is limited to a maximum value. According to the theory developed by Berkel, two important definitions are proposed. First is the intrinsic buffer capacity, which is defined as the capability of the surface to store charge when the surface proton concentration is modified. And the second is the diffusion capacity, which is defined as the ability of the electrolyte to adjust the amount of stored charge as a result of the change in the electrostatic potential. So with these two magnitudes, we are able to calculate, to estimate the variation of the potential at the surface produced by a modification of the surface pH. Combining the previous expressions, we can also estimate the sensitivity of the surface to the bulk pH. And we see that this value depends on a parameter, alpha, which is limited to values between 0 and 1. And this maximum value of the sensitivity is 59 millivolts per pH. This value, this maximum value, is known as the Nernst limit. And there are many attempts to enhance the sensitivity of the ISFET sensor. And we will talk about this issue in a few slides. The presence of a high concentration of ions originate the screening of the sharp biomolecules. And they produce a key limitation to the sensor sensitivity. Counter-ions inside the solution compensate the charge of the analytes to be detected, and as a consequence, the potential decreases exponentially as a function of the distance from the charged biomolecule in the surrounding solution. So the device screening length is defined as the distance over which this charged analytes can influence the surrounding electrostatic potential. And we can see that this screening length is reduced for higher concentration. So we can observe that the values of the screening length is really short, can be very, very short. And this implies that makes much more difficult the detection of the anomalies. So there are different techniques that have been used to try to overcome this limitation. And the first one was the use of truncated antibody receptor. The second one was try to use microfluidics and purification to increase the analyte concentration. A third alternative was the use of alternating current signal to decrease the effect of the double layer capacitance. And the physical reason was that for high frequency, the ions in the electrolyte don't have enough time to create the electric double layer. The consequence is that for AC, the potential decreases linearly compared with the DC that decreases exponentially. A new approach has been also proposed that considers the addition of a polymer layer, the PEG here, that has two main characteristics. The first one is that this polymer is permeable to the biomolecules of interest. And the second one is that it provides a constant potential in the whole thickness of the polymer due to the presence of some immobilized charge. The results obtained in the laboratory provides very good results, and it improves the signal amplitude obtained. However, more theoretical studies are required for a complete understanding of the working principle of this layer. Let me go now to some advanced simulation and modeling tools that we have developed. First, we have considered the structures here shown, the ACE-FET, that in our simulator we have considered to be material, but it can be any other one. And it is sandwiched between two insulator layers, the substrate and a thinner one above that separates the channel from the electrolyte. We also incorporate here the receptor layer in green that is usually employed to capture the target molecules. The biomolecules are represented on the right as a black box, split into regions. That neutral one, which is in the close to the binding region, and a charged molecule, a charged region, which is on top of that. So in order to analyze these molecules, we have considered three different models. The first one correspond to the hollow box model that allows the penetration of the electrolyte ions inside the volume. The second one is partially solid box that allows the penetration of the electrolyte ions only in the neutral region but not in the charged region. And the third model is a solid box that forbids the penetration of ions inside the whole volume. Then we have consistently solved the whole set of equations that describe the carrier transport in the channel and inside the electrolyte. And we can obtain a different number of electrical magnitude, but here we have highlighted a two-dimensional color map of the total ion charge density around the molecules in the three models. Important differences were observed is that the responsivity of the device depends on the model employed. So here we have evaluated the output characteristic of the device, and in this case we can appreciate that in the calculation of the charge in the electrolyte, depending on the molecular charge of the charge induced in the channel, we observe important differences. As for example, here, 90% of the molecules of the charge is screened by the electrolyte ions, compared with only 10% of the charge induced in the channel. Moreover, when the concentration of the ions in the electrolyte is increased, we observe that the amount of charge induced in the channel is almost negligible. So we can see that these different types of models of molecules produce a different response on the sensor. The application of one of these models for a specific type of molecules depend on the feature of that molecules and also the density and size of the ions contained in the solution. Yeah. In a macroscopic approach, the effect of water on the electrostatic interaction is quantified by the Gaussian equation by means of the electric constant, which is considered uniform with a value of 78. But the behavior of water close to an interface has been studied using molecular dynamic simulation, and they have demonstrated that the water density near to a solid deviates from the back value due to short-range interaction between the macroscopic object and the water molecules. The reason is found in the polar nature of water that affects the electrostatic environment, making the electric tensor is a position-dependent magnitude, as shown here in the figure. So we can see that the electric constant is not uniform or constant anymore, but it has a position-dependent variable and even can be oscillating. Moreover, it has been demonstrated that the hydrophobic or hydrophilic nature of the solid surface has a strong influence on the adjacent water. As for example, here in the blue line corresponding to the hydrophobic, we see that there is a region depleted of water. So we have also included the potential of mean force in the simulator to account for the repulsive ion substrate interaction in the proximity of the hydrophobic or hydrophilic surface. Just to include another feature to our simulator, we have observed that the pH sensor can be modified when the salt concentration in the electrolyte increases, even if the pH is kept constant. The application of this traditional side binding model is not able to explain this result, so we have to include a new model, which is shown here, the modified side binding, that basically takes into account a new chemical reaction on the surface. This model is important, especially for physiological solutions where different kind of ions can be present. We have evaluated the influence of this additional reaction just using a simple capacitor, different pH values and chlorine concentration, and we can see that In the case of here on the left here for the side binding bubble, we see that here we are representing the interface charge is modified when the pH is changing, but there is no any dependence with the chlorine. In the case of the modified side binding on the right, we are only representing two pH values, 4 and 10, and the different chlorine ions concentration, and it's clear the influence of these ions, of these chlorine ions, on the charge sensing surface, even for a fixed value of the pH. So the conclusion is that it becomes mandatory to include this effect. Just to finish, we have put everything, all this model in our simulator that correspond to a standard pH sensor with a monolayer of molybdenum disulfide as a channel, silicon dioxide as the substrate, and aluminum oxide as the active interface. We have considered two types of interfaces, hydrophilic and hydrophobic, and 4 values of the chlorine ion concentration. And we have also tried to use these two different models, side binding and the modified side binding. Here, for the hydrophilic surface, we can see that the solid line that corresponding to the side binding and the dashed line to the modified side binding, and we see that increasing the pH produce an increasing of the threshold voltage as it corresponds to the increasing pH value. That is the expected result. But we can see that the effect of the chlorine concentration is not reproduced by the side binding, but it's also included in the modified side binding. So it's important just to have an accurate result also here for the sensibility. And the next case corresponds to hydrophobic surface. And we see that the results are shown here for the threshold voltage. And we can see that there is a linear relation between the threshold voltage and the pH for both models. And the main difference is the presence of the effect of the chlorine concentration on the modified that is not seen in the side binding. So that the presence of these different salts dissolved in the electrolyte can lead to different values of the sensor measurement, even for a fixed value of the pH. Let me conclude. So the first conclusion is just I would like to highlight that the current sanitary situation in the world has boosted the interest to develop this kind of system that are able to provide a fast, cheap, and reliable diagnosis of viruses and other biomolecules. This interest was already shown for preventive medicine application, and the social and economical implication of this kind of system is huge. Second, the number of available materials and possibility has grown with the emergence of the two-dimensional materials and their structures, and therefore increased performance could be achieved through a small combination of these new materials and structures. Third, the combination of the physiological solution and the solid sensor gives rise to a solid-liquid interface that works in a way that is radically different to the traditional semiconductor devices. So that we need new models and simulators to achieve reliable and accurate results. These models have to be extracted from a multidisciplinary research where the frontiers between physics, material science, chemistry, and biology become diffuse, because all of them has to be combined to get the whole picture. Fifth and last one, there are lots of opportunities and possibilities to research in this field, both from experimental and theoretical perspective, and it is quickly developing nowadays, and we encourage you to participate. Thanks for your attention. I hope you have enjoyed this talk, and don't hesitate to contact me or just let me know your question. Thanks.
Thank you very much, Professor Goddard, for the wonderful talk. Now the floor is open to questions. We can take one or two questions, quick questions. So Professor Goddard, I have one question on your talk. Like you mentioned your probably futuristic work in this domain will be on 2D material based sensing. So which 2D material actually you are looking to target, like to start with? Which kind of 2D material you're thinking about?
I think that the first material that is most interesting right now is graphene. The reason is that graphene. The material that people are right now using more oftenly is graphene. And second, I will have to mention molybdenum disulfide. And the reason mainly is because they are already well known from other kind of application. I have to say that graphene and molybdenum disulfide have already been applied for a different number of applications, and now they are getting to this field of biosensing. I think that all this experience is one of the main reasons that graphene and molybdenum disulfide are the more popular elements to be used in biosensing. But it doesn't mean that there are no other kind of material that would be more interesting or more useful. The thing is that there are a lot of opportunities because there is still lots of unknowns and a lot of questions to be answered. So I think that also another important possibility for graphene is that it is biocompatible. So it has been already tested with in direct contact with cells, and it behaves and it has shown a very good performance in this. So I think that these two materials are already employed and they are already used in this kind of biosensing application.
Okay. Thank you so much, Professor Kadai.
So, Professor
anybody else?
Yeah, so Professor Kadai, I have one question. So, your model, so have you actually matched your model with the experimental data?
Yes, actually, we are in close collaboration with some experimental groups here in Spain. And we have tried to compare our results with some of them obtained in the laboratory, and also with some results from the literature. The point is, I have to be honest. In this case, it's important to consider some non-ideal effects just to reproduce the experimental result. For example, as the material is in contact with the water and other compounds, sometimes we need to add some kind of interface charge in order to reproduce the experimental result. It's not simple at all because the surfaces are not so clean as we use in our CMOS devices for logic application. But here, the surface is in contact with water and a lot of salts like chlorine, sodium, chlorine, potassium, and so this possibility of additional reactions that are not still very well known. So we are able to reproduce experimental results, but we have to put a lot of sometimes empirical, or we have to add some unknowns, like for example, interface charge.
Okay, so will your model change if you change the biomolecule, or it will still be same if the means just the parameters will change for different biomolecules?
Yes, that's a good question. Modeling biomolecules are still quite difficult. As you have seen in my presentation, we are using just a box that looks like a column. It's completely striped, in a rectangular shape, but it has nothing to do with a real molecule because molecules have different shapes that are not rectangular anymore. So that's something that, of course, should be improved, but is adding more complexity to the numerical simulator. Also, I think that in the future it could be important just to go to a 3D modeling instead of a 2D, but of course that will increase the complexity and the time required for the calculation.
Okay. So thank you. I think so it's a very interesting talk. So I think I don't have any more questions. So thank you.
Okay. Thank you so much, Professor Goday, for the wonderful talk.
Thank you, all of you.
So
Thank you for your invitation.
yes, thanks, thank you. So Manoj, are you online?
Yes, sir. I'm here.
Yes.
Sir.
So our next
And,
speaker will be put on the
yes, sir.
video mode.
So,
This will be playing his video, right?
Salval, I see now to in
Yes.
the participants thing. So could you please
Oh,
ask him if?
yep, Professor Nauto.
Can you hear me?
Yes, we can
Yes.
hear you.
Yeah.
Yes, I'll just give you a brief introduction about Professor Naoto Horiguchi. So the next speaker will be him from IMEC Belgium. So for a brief introduction, Professor Naoto is the director of Logic CMOS Device Technology Program in IMEC Leuven, Belgium. He started his career in semiconductor device R&D in Fujitsu Laboratories Limited in 1992. During 1992 to 1999, he was engaged in device development by using semiconductor nanostructures in Fujitsu Laboratories Limited and University of California, Santa Barbara. Between 2000 to 2006,
नहीं ठीक है राइट साइड में जो
he was engaged in 90 to 45 nanometer CMOS technology development in Fujitsu Limited. From 2006, he is with IMEC Belgium, where he is engaged in advanced CMOS device R&D together with worldwide industrial partners, universities, and research institutes. His current focus is CMOS device scaling for 2 nanometer technology node and beyond. The title of his lecture for today will be on device architecture evolution from nanosheet to CFET for CMOS scaling to nitrogen and beyond, into technology and beyond. So, Professor Naoto, the floor is all yours.
My name is Naoto Horiguchi from IMEC. I will present device architecture evolution from nanosheet to CFET for CMOS scaling to N2 and beyond. First of all, I would like to appreciate organization committees of this conference for giving us the opportunity to present our latest device roadmap. Thank you very much. This is outline of my talk. First, I will start from the CMOS scaling trend and identify the latest CMOS scaling challenge. Then I will propose a CMOS device roadmap for the further CMOS scaling. Then I will go more detailed description of device architectures, nanosheet, fork sheet, complementary FET, so-called CFET, and finally I will summarize my talk. Let me start from CMOS device scaling trend. This slide describes the trend of the CMOS scaling in the past and for future. The goal of the CMOS scaling is to reduce the cost for the transistor, or increasing this transistor density, we could reduce this transistor cost. In the past, we had a very good period. We could follow this ideal CMOS scaling trend by innovation of these materials, patterning, even some device architecture. However, in a recent CMOS scaling, start to see some of the gap between ideal scaling trend and actual scaling trend. Then important question is, can we close this gap? And then if yes, how to do that? So that's the important question of this future CMOS scaling. Then if we look at more details of this latest CMOS scaling challenge, we see a strong reduction of the pitch scaling slowing down. In the past, our CMOS scaling counted on this pitch scaling, either CPP, contacted per pitch, or metal pitch. We could reduce this number generation by generation to follow the ideal as a CMOS scaling trend. However, if you look at, for example, CPP, this pitch scaling is slowing down. We see clear gap of this ideal trend and then actual trend. To compensate this slowdown pitch scaling, industry introduced so-called track height scaling. Track height means we can reduce number of the metal per standard cell, and then without this pitch scaling, we can still reduce the area by reducing this Y direction. So that's the trick industry introduced, and then we could follow ideal scaling trend. However, this drug height scaling has this one problem, which is this fin depopulation. Since fin pitch cannot be scaled as fast as the drug height, we have to reduce number of the fin in the device to follow this drug height scaling in the fin pitch scaling trend. Because of this fin depopulation, we have to just reduce number of the fin from 3 to 2 today, and probably in the future we have to reduce number of fin to 1. In this case, we'll have an issue in this device performance and also variability. So this is a problem we have to solve today for the further CMOS scaling. Then to compensate this performance reduction from this fin depopulation, industry introduced taller fin. By introducing taller fin generation by generation, industry could compensate to some extent this performance degradation. But once we come to this single fin architecture, this drive current reduction is quite significant, and also this variability increase also is very big. So this is a critical point for this further CMOS scaling. For this, we need new CMOS device architecture for further CMOS scaling. So this is just a second section for my presentation. This slide provides this cross-section of state-of-art standard cell, which has 2 fins for each device, and which has relatively lax NP spacing. This number of fin reduction from 2 to 1, and also reduction of NP spacing is an opportunity for the further CMOS scaling. For example, to reduce track height from 6 to 5, we can propose single fin architecture, but by using, in this case, nanosheet architecture, then which could compensate single fin performance degradation by inserting this multi-stack nanosheet, which has wider effective width perfectly. So that is an opportunity for this nanosheet architecture. Then to improve CMOS scaling further by using this nanosheet architecture, we could introduce so-called fork sheet. In this case, we inserted dielectric between NMOS and PMOS, and we can reduce this NP separation smaller than nanosheet, and which will enhance even wider this nanosheet in the fork sheet architecture, which will help performance improvement. And thanks to this NP reduction and wider nanosheet, and this fork sheet provide further performance and area benefit over the nanosheet. Eventually, we could go to this NP stacking structure for targeting 4-track height standard cell. In this case, NP separation becomes vertical direction, and which will not have area penalty anymore. So this is an ultimate CMOS device architecture for the future device scaling. For summary, we can just move from device architecture from FinFET to nanosheet to provide this performance improvement in a single fin architecture. And for further improvement on nanosheet, we could just propose this fork sheet architecture, which has a smaller NP separation thanks to this dielectric wall. Then finally, we could introduce this CFET architecture, which has NP stacking structure, which has ultimate scaled CMOS device architecture. So these are the device architecture roadmap for the future device CMOS scale. Then for the next section, let me start from this nanosheet technical details, motivations, and also integration flow. Then this moving from FinFET to nanosheet, there are 3 key motivations. One is this maximum effective width per footprint. This will bring this drive current increase, especially at single fin architecture. And also, nanosheet has this gate-to-run architecture, which will enhance this short channel control due to this gate-to-run structure. And finally, this nanosheet has this variable nanosheet width, which has some flexibility in the design. So that's the 3 advantage over the FinFET in nanosheet. Then thanks to this large effective width per footprint, and clearly this nanosheet has this wider width, and which will enhance device performance by this larger drive current. And thanks to this larger drive current, we could get larger this frequency as compared to the FinFET reference, And also in the scale technology node, we can maintain this advantage by using this nanosheet. So this is just an advantage over the FinFET. Then process flow of this nanosheet is very similar as a FinFET. And in this slide, I highlighted key difference between nanosheet and FinFET process flow. Nanosheet integration starts from this silicon germanium multilayer, and then we have to make it thin by using this multilayer. Then this silicon germanium will be used for the sacrificial layer at RMG step to create this nanosheet channel. The second key difference in the nanosheet flow is so-called inner spacer formations, and we have to introduce some dielectric between source drain and gate, which will reduce this capacitance between source and gate, which will enhance this AC performance of this nanosheet. Then if process flow comes to this RMG step, we have to expose this multi-layer fin, and then we will remove this silicon germanium layer selectively to these other materials. Then we can create this silicon nanosheet channel. We can use this nanosheet channel for this good electrostatic channel. Then finally, we can continue to this gate last integration. This exposed this silicon channel will be surrounded by high K and metal gate, and also this proper NPA work function metal patterning has been done. So these are the process flow of the nanosheet. Except for this silicon germanium stack fin, inner spacer, nanosheet release, and work function patterning, other process flows can be reused from this FinFET. So that's just a commonality of this nanosheet and FinFET. Then originally, initially, this nanosheet integration was quite complex, but we could manage this process control properly. And I'll show some cross-section from this IMEC experimental data. Starting from this silicon germanium fin formations, we could manage this good fin formation without damaging this fragile silicon germanium layers. And then we could insert this small inner spacer dielectric between silicon germanium source drain and then active fin. Then by tuning our selective edge, we could just enable this highly selective silicon germanium removal without damaging this silicon nanosheet channel. And finally, we could integrate this high K and work function metal and tungsten field around this nanosheet channel without any issue. So those are the example of this module process of this nanosheet, which is naturally controlled today. By using this develop this nanosheet module, IMEC and also industry can just integrate many different stacks. So this slide describes the example of this nanosheet ring oscillator and also SLAM. So these nanosheet integration technology are getting matured. It is very close to the production today in the industry. Then let me move to the advanced nanosheet architecture, which is forksheet, which has advantage in area scaling and performance over this nanosheet. So this is just our next topic. First, this slide provides a key difference between nanosheet and forksheet. The difference between this nanosheet and forksheet exists in this dielectric wall between NMOS and PMOS. Then thanks to this dielectric wall, we could reduce this NP separation in forksheet is extremely scaled one. Then moving from nanosheet to the forksheet, we could introduce three key advantages. First one is, as I already mentioned, NP spacing becomes very small thanks to this dielectric wall. And also thanks to this dielectric wall architecture, we could reduce this mirror capacitance, which will enhance this AC performance of this nanosheet. And then finally, this nanosheet architecture has flexible device connectivity with less dummy gate, and also gate connections are quite flexible. So this will help also further area reduction. Then in this slide, let me explain how to enable this small NP space by using dielectric wall in a forksheet. So this left-hand side shows this nanosheet example in the RMG. In the nanosheet RMG patterning, we have to apply relatively long over edge to remove this work function metal between these nanosheet particle space. During this lateral over edge, this NP boundary is also moved to the other direction. And then once we complete your over edge, and this some amount of this NP boundary has to shift to the other direction. Ultimately, this NP boundary merge will decide NP separation of the nanosheet. However, in the fork sheet case, we can use this dielectric wall as edge stop layer. Similar as nanosheet, we can start this work function metal edge from side, and we need some amount of the over edge. But always this lateral over edge will stop in this dielectric wall and will not go beyond this dielectric wall, which will enable this NP separation extremely scaled dimensions, and which is very similar as this dielectric wall thickness. So this is advantage of this fork sheet with this dielectric wall. So this and this scale dimensions are enabled. Then thanks to this very scale this NP spacing, and this will be translated into this area reduction of standard cell and SLAM. And this slide provides example of this SLAM scaling. By reducing this PN separations, we could reduce this SLAM cell area beyond the standard FinFET nanosheet limitations. And roughly speaking, we could get like a 20% area reduction for the high performance SLAM, and the high density SLAM, we could get a 30% area scaling, which is quite significant advantage of this fork sheet. And in addition to this NP scaling advantage, and fork sheet has also flexible connectivity, which will help also further this area reduction. For example, in the circuit design, we can reduce number of the dummy gate in the fork sheet, which will help to reduce this standard cell area. And also, fork sheet has very flexible this gate connection, and which will also help good gate connectivity over all this chip area size, and standard cell area size will be reduced. Then, for example, in this example, I compared flip-flops from nanosheet, FinFET, and fork sheet. Thanks to this advantage, we could get like 20% area reduction in flip-flops by using fork sheet. This is the additional advantage for this fork sheet for the further area reduction. Then fork sheet advantage is not only in the area reduction, but also it has advantage in the performance. This is because fork sheet has a smaller mirror capacitance, and then if you tune your fork sheet design for the capacitance small design, we could get 10% reduction of this mirror capacitance, which will be translated into this frequency improvement as compared to fork sheet. So this is just one more additional advantage in the performance from the fork sheet. Then I mentioned this fork sheet has an area advantage from this small NP separation with this dielectric wall. But this small NP separation can be used for the different way. For example, if you use this smallest NP separation with dielectric wall, we can use this scaled dimension for the wider nanosheet. In this case, we can enhance this drive current in this design. Or we can just maintain this dielectric wall wider to accepting somewhat this narrow nanosheet. In this case, we can tune our standard cell design for the capacitance optimized. Then by using different combination of nanosheets, dielectric wall, we could tune our design from area, drive current, and capacitance. This is some additional advantage of this fork sheet architecture in terms of this design. Then this fork sheet process flow is very similar as nanosheet, and key difference exists in this dielectric wall formation after STI. In this case, we put this NP STI separation is very small, and we deposit this dielectric field conformally, and then this dielectric will film isotropically etched. And then only in the dielectric in this small branch will be maintained during this isotropic etch. And in the subsequent process flow, we can maintain this dielectric film as much as possible to avoid any loss during the spacer etch, inner spacer integration. Then we can use this dielectric role in this RMG patterning, as I explained in the previous slide. Then finally, I would like to explain this CFET, so-called complementary FET, as this ultimate CMOS scaling device architecture. This concept of this complementary FET, so-called CFET, is the folded inverter. In the standard inverter has NP on the horizontal placement. On the other hand, this CFET has a stacked architecture. Thanks to this NP stacked architecture, we could make the CMOS-like function on a single device footprint. And then this will enable any scaling without pitch scaling. And also, we could introduce different materials top and bottom device by using a sequential integration, which is additional advantage of this complementary FET CFET. Then, thanks to this NP stack structure, it has quite strong area advantage, both logic and SLAM. So both as logic and SLAM, this CFET shows quite significant advantage as compared to the other FinFET or nanosheet architecture. Then one of the challenge of this CFET is its integration, because we have to integrate NP on top of each other. This integration must be very special. We have two integration approach. One is this monolithic CFET, which uses this bulk substrate, and we integrate from bottom to top all this source range, contact, and RMG. And other approach is so-called sequential CFET, which will separate integration to bottom tier integration, wafer bonding, and top tier integration. This monolithic CFET has advantage in the cost and small parasitics, but the challenge is this very complex vertical direction on the source range, contact, and RMG. So that's we need to use some more exercise for the further improvement. In a sequential CFET, process flow is simplified since we divide this integration to the bottom, wafer bonding, and top integration. And however, it has some challenge in the wafer bonding, this defect control, and also we have to deal with some budget top and bottom device integration to avoid any negative impact. Then let me explain the process flow of this monolithic CFET more details and with some cross-section from the experiment in IMEC. Then this monolithic CFET integration starts from silicon germanium multi-layer stack, which is very close to the nanosheet. And also this silicon germanium layer will be used for separation between bottom and top silicon channel. Then once you start from this silicon germanium layer fin, and we need to some high aspect ratio gate patterning on top of this taller fin, and then we start this complex source range contact integration. Then first we start from this inner spacer formations, and then continue to this silicon germanium source range epi, and then contact on top of this bottom source range, and we insert some into this dielectric layer for electrical isolation. Then this top source range is the epi will be grown, in this case phosphor doped silicon for the NMOS, and then this continue to this top contact formation. And then complex integration flow will be finished by this gate last integration, and integrating this different work function method bottom and top. Then this flow or this monolithic integration has advantage, cost, and parasitics, but as you can see, this vertical integration is quite complex. That's still is a challenge. But so we could manage this vertical integration in this smallest device lot, and we demonstrated PMOS FinFET at the bottom and top NMOS nanosheet. So we confirm this device functionality in this integration. Still, this vertical integration source range contact RMGs are remaining. We need much more process control improvement and also this process modules innovations. Then let me switch gear to this sequential CFET flow. As I mentioned, this flow has the simplified process flow, dividing integration to bottom integration, wafer bonding, and also this top tier integration. But this sequential CFET flow has also its own challenging. For example, wafer bonding defect control, and then we need additional this top and bottom connection, and also we need to deal with some other budget difference between bottom and top devices. So this challenge has to be tackled. Then this slide provides an example of this process innovation or process development for this sequential shift. And as I mentioned, this wafer bonding is a special process flow for the sequential shift. In this case, we need to start from this bottom tier device, process bottom tier device, and we will deposit this SiO2, and we planarize by using this CMP. And after this planarization, this top surface has to be extremely planarized to avoid any like bonding defects, bonding voids. Then this combination of this oxide deposition thickness and then CMP process control the key how to reduce this bottomless bonding oxide defect. And then by tuning this combination, we could move to this high density of bonding void toward this almost no bonding void process control. So that's one example how we develop how we deal with this bonding in this process. And also we develop laser annealing for the top tier device to avoid this negative impact to the bottom tier device. And in the top tier device, we confirmed the advantage of this laser annealing in the blue dot, and also this we didn't observe negative impact on the bottom tier device in this case. Also, if we have to reduce your summer budget in a top tier device, one more concern is this gate stack reliability. Usually high-K metal gate, we need quite high summer budget for this reliability improvement, but we cannot apply this high summer budget in the top tier device in sequential shift. Then in this case, we apply some dipole engineering to improve this top tier device BTI. We confirm both NMOS and PMOS. This BTI is dramatically improved and close to the target by using this low temperature process. This is an additional example to this control summer budget and still provide a good process and reliability control. Then also I mentioned this sequential shift has an advantage of this hybrid channel integration. Means we can introduce different channel materials top and bottom devices. And this is a concept is already reported in IDM from the Intel. For example, left-hand side, they integrated silicon bottom FinFET with this germanium nanoribbon nanosheet device on top. And also this right-hand side, they integrated gallium nitride at the bottom and the silicon transistor top. So those are the good example of this sequential shift advantage by using this hybrid channel. In this case, they could enhance device performance and also they could enhance functionality of the shift. So this is another opportunity of this sequential shift integration. Okay, this brings me to this summary sections, and I would like to summarize my talk. At the beginning, I'll talk about this CMOS scaling trend. So recent CMOS scaling trend shows this slow down this pitch scaling, which has improved scaling trend. And to compensate this slowdown pitch scaling, industry introduced this track height scaling. However, this track height scaling has an issue in this fin preparations, and especially this fin population comes to the single finless device architecture, which has a big impact in performance degradation and variability increase. So device architecture, new device architecture have to solve these issues. Then to improve this CMOS scaling in the future, we provide device and see that about the care by using and this space. Then the guy and
Hello.
think flow is very similar as now, and transformation, which will help to reduce emission in the Then and I bought the device and then something, and also significant to use in this such as a waveform and also larger gap in top of that knowledge to my and also
Hello? Hello, Professor Naoto. Are you with us?
Yes, I'm online. Can you hear me?
Thank you so much for the wonderful talk. Yes, thank you so much for the wonderful talk. And the floor is open to questions.
Yes.
We can quickly take a few questions from the audience.
Participants, if you have any query, then you can ask to Professor Naoto.
I think someone switched the video. I think one of the participants. So she can ask questions. I forgot who opened the video. Someone I could see switched on the video.
Hi, Ekta, do you have any question?
No, thanks. Actually, I'm facing a problem with my own poster. Sorry for disturbance.
Okay. Just keep your mic on.
Saibal, I have a question to Naoto.
Yes, please.
Yeah. Naoto, so basically when we're talking about complementary FET, this is a very nice architecture, but do you see any any loss in capacitance because you are stacking PMOS on top of NMOS? So are there will there be an issue in the capacitance?
Okay, I think to some extent this architecture could have some capacitance. Device capacitance increase, but this track height reduction also reduce overall capacitance. And then today, this CFET, it's more position of this area reductions. And then performance-wise, it's very actually similar as a standard 2D device like a nanosheet or forksheet. Then at the end, we have some capacitance increase from architecture, but from this track height reduction and will contribute some capacitance reduction. So that kind of compensated. Then eventually this CFET is ended up some of the areas scaling booster, but performance are actually quite similar.
Okay. So what will be its effect on the routing? Because as you scale if you increase the number of transistors, so we have to route it because PMOS being on top of NMOS.
Yeah.
How are you routing? Means how means basically how does the backend look like, right? So because you have to connect both N and P also.
I understand. So then yes, I think connection to this track. And one key difference is we have to introduce different depths of the beer. And to connect this top device, you need shallow beer, and to connect to the bottom device, you need like a deep beer. But once you enable these connections, and then beyond this track, and should be as a similar as standard approach. But still, I think routing is all these circuit or blocks with this 4-track itself, it's still challenging. But we could manage, and we see some advantage also in the block level. This is what I can say today. Yeah.
Okay. So what is the in CFET? What is the minimum thickness you're talking about? If I'm looking at 2 nanometer node, the seed thickness will be less than 5 nanometer, or it will be around 5 nanometer.
Which thickness you're talking about? Is the top and bottom separation?
No. I'm talking about the silicon thickness you are using.
Silicon thickness. I see. Okay. Probably I'm thinking something like 5. And
your PMOS is also silicon.
I think channel can be selected according to your final device performance, and we can probably include the silicon germanium channel too. And then top channel could be it's silicon, but it could be like a strange channel if you use like a wafer bonding technique in sequential CFET.
Okay. So also, I mean, so you presented the process flow, but for to me it looks a little bit complex. So the point is,
it is complex.
Are you facing? Will you face any process integration issue? Because is that a doable thing? I mean, in the future for very high. When you increase the number of transistors, so how difficult is to integrate all of them?
Yeah, I would say the monolithic CFET is quite difficult, and especially for the scale dimension. Then today we are trying to integrate from bottom to top, like by repeating some feeding edge back and then feeding edge back. But this vertical control is quite challenging, and it's actually not very common in current industry. So that's a clear challenge. Here, we need clear process innovations or some module innovations. Otherwise, it's very difficult to integrate. But sequential CFET is actually simplified process. I think it has some chance to be integrated.
Okay.
Yeah, that's our opinion today. Yeah.
So the plan for CFET will be in which node, which CMOS node?
Probably it will be something like 1
nanometer.
Yeah, beyond 2.
Okay. So
which is that separation?
No. I'm talking about the silicon thickness.
Silicon thickness. I see. Okay. Probably I'm.
Okay. So I think there is a disturbance. So I think that has been okay. So basically 1 nanometer CMOS node. Means basically the SRAM means, are there any SRAM yield related issue? That is my last question. So have you? Yeah.
You were talking about SLAM yield or SLAM demonstration.
SRAM demonstration yield will come later, but So SRAM has been demonstrated with CFET, right?
But it's not really scale dimension, right?
Yeah, it's not scale dimension.
Yeah, so that case, so the real integration we have to still demonstrate, and CFET technology is still not matured to me. Yeah.
Okay.
Yeah.
So thanks for your informative presentation. Thank you.
Thank you very much for your all comments. Yes, appreciate it.
Yes. Thank you so much, Professor Naoto, for the wonderful talk. So
thank you.
With this, we'll conclude this session for the invited talk by the participants. And thank you to all of you for joining with us in today's session. And we'll see you tomorrow in the morning time for another invited session, talk sessions. Thank you so much.
Thank you.
Hello.
Are any organizers there?
Hello. Yeah. Nihar sir. Hello. Shabal sir. Can you hear me? Hello. Hello.
We can hear you, Manoj. I think the
Yeah, we
professors
can hear
have, I
you.
think, left.
Participants, actually, this is the time for a tea break, and another session third will start at 5 p.m. Okay, so till then you can have a break and you can enjoy your snacks. Okay. Hello.
Thank you.
Okay, thank you. So, ICW team, you can play the theme now on our screen.
Yeah, sure.
Okay.
Hello, sir. Which one, sir, Mr. Manoj?
Yeah.
Which one theme, sir? Can I?
Sir, the fifth, the theme which you were playing earlier.
Okay. Yeah, sure.
Yeah, the ICW conference, like.
Sir, I have a question. Hello,
Hello.
sir. When will be the poster will be presented? That time was 3:30, I think.
No. The postal session in for emerging logic and neuromorphic devices will be tomorrow. Okay. Hello.
For MEMS and NEMS, it was today only.
Uh, for which symposium you have given your poster?
MEMS and NEMS.
Okay. So for MEMS and NEMS, just let me check.
The poster should have been started at 3:30 to 5.
Yeah. They are being displayed in hall number 5. Okay. So can you see the delegate link? Get that?
Yes, sir.
So by going there and by going into e-poster lobby, you can see all the posters. Okay.
Okay. So is there? Will I have to present anything, or I have to just be there for some time?
You have to be there just for actually there is a evaluation committee. Okay. They will call out your name and then you will explain your poster. And then they will I mean among those posters they will select the best one. Okay. Whatever the content is and whatever you explain. Okay.
Thank you, sir.
Okay. Thank you.
There was a technical issue because of which we couldn't get started earlier. So let's get started. I think all your posters are visible under e-posters. Dhiman, is there specific any poster that you would like to call up and ask questions, or how do you do
No,
this?
so we can start with whatever is first in the queue.
Okay. So I think the list I have. The posters are also visible on the main website through the delegate link. So there's a session for e-posters that one can see. But anyway, we can go here. So first poster here is Mr. Zakir Hussain, studies on DC conductivity and LPG sensing behavior of Pani or calcium sulfide nanocomposites. Poster number 112. So, okay, so Dhiman, I think what we have to do is we have to look at the poster on the ICEE website and ask questions here. I think that's what we have to do. So you can probably go there. Poster number 112 is the one we're looking at.
Is there any error in the posters? Because I am seeing some error message.
No, I can see it. So did you go to ePoster, then close the initial YouTube thing that starts off? Okay, so first one, I think there's some problem with the first one. Yeah. Maybe if you go to one.
I think, sir, poster number 111 is missing on website link.
112. I'm looking at 112. So there is no poster for 112. So has this person submitted a poster? I'm not sure.
113 is visible.
113 is visible. So let's go with 113 then.
Shubham, are you there?
Shubham, are you there? He's not here. Maybe we'll go to next one and then come back if he's there later on.
Hello, sir.
Yeah, hello. Who is this?
Sir, yeah, this is Mahesh Kumar.
Okay.
And actually, I have gone through many posters, but like most of the posters are having giving an error message. So even my poster, my poster is also giving a message, error message. So I'm not able to access that. So
What
might
is
be
your
this is
poster
happening
number?
with the other posters as well.
Mahesh, what is your poster number?
No, I don't think Mahesh is in this session.
Sir, I am in this session. My poster number is 114 and I have submitted. Please check. So you can check that one first.
Okay, so I think 114 is visible. So why don't we get started with 114? Pulraj, can we get started?
Oh, sorry. Actually, I'm in the another meeting also. So can you please start? Maybe I'll join shortly.
Okay, sure. So Dhiman, can we get started?
Yes, 114.
Okay, so I'll pulled it up.
Or should I share the screen here? Should I share my poster here, sir?
That's fine if I'm not sure. So we'll do it. I can see your poster. I think that's fine. Dhiman, can you access it?
I can see the poster as well.
Okay. Okay. So do you have any questions? Okay, I have a couple of questions.
Yeah, please.
Okay, so what kind of array are you looking at for your microvalve, for your
So firstly, this microvalve I'm using here as the test object for the proof of functioning of the control system that we are proposing in this work. So the reason of choosing microvalve is because it is the basic entity which makes a complicated microfluidic chip. So yeah.
So what is the yeah.
Okay.
Bhaskar,
Hello.
can you share this maybe screen so that
That will be
everyone is
better.
there?
Yeah, I'll share it and so all the participants will be able to see. Wait.
Sure, I think that may be better.
Mm-hmm.
If you can do that, I think that's fine.
Yeah, is it visible to everybody?
Please go to full screen. Yeah, see it.
Yeah. Yes.
Yeah, it's visible.
So, should I give you a brief explanation about what the work is?
Probably 2 minutes.
Yeah, sure.
That's it.
So like we have see microfluidics, it's has grabbed the attention of various researchers, and there are various very complicated microfluidic chips also we have as per what the application it is being used for. So it is something similar please, others, please, can you please go on mute because there is some. Hello, I can hear some noise. Can others please go on mute? Yeah. So here, for any functional microfluidic system, we need a control system so that it can work as a complete system to finish one application that the microfluidic is meant for. And the complicated microfluidic structure, it comprises of various microfluidic components integrated on the same chip. It is something similar to what we have VLSI for electronics. Same way we have MLSI for microfluidic systems. So here, in order to make use of such microfluidic chip and to control the flow of the fluid on the microfluidic chip, here we are proposing a homemade control system. So this overall, the experimental setup which is shown in the section 2 here, it is the proposed system. So here for the demonstration of the functioning of this system, we are using a microfluidic, we are controlling this microfluidic chip, and the microfluidic component that we are targeting is a microfluidic valve. The reason of taking this microfluidic valve is, as I said, that this MLSI is similar to what we have VLSI for electronics. So in VLSI, we have a transistor that works as the basic element. So in microfluidics, we have a micro valve which works as the basic element based on which we can make any complex microfluidic component. So the micro valve that is chosen here is a quake valve. Quake valve, it is actually it is named after Professor Quake Valve from Stanford, who has made this valve. So it is a pneumatically based valve. So it is having a flow. I'll just maximize so you can see. It is having three PDMS layers. The bottom layer is for the fluidic flow to flow. That is the sample that we want, and the top one is the control channel where the compressed air will be given, and in between these two is a very thin PDMS membrane which is sandwiched. So the compressed air comes from the pneumatic valve. It reaches the control channel, and this bends the PDMS membrane which is here. Hence, the flow of the fluid which is in the flow channel, it gets impeded. So these control channel and flow channel, they are oriented orthogonally to each other. So the experimental setup consists of an air source because we need the compressed air to be in the control channel. So the pressure regulator is needed to control the pressure, and which valve has to be, suppose if instead of having one valve, we have many valves on the same microfluidic chip. Now in order to set which valve has to be actuated, when we have a valve here which is controlled by a relay module, and this relay module is controlled by a single board computer. So in our experimental setup, we are using a Raspberry Pi computer board. Now in order to do the analysis, we have used the optical analysis using an optical microscope, and I'm sorry. The testing of this system is shown here. So here, when the valve is open, it looks like this. When the valve is closed, it looks like the brighter white part you can see. So this is the structure of a closed valve. Here, the vertical one is the flow channel. The top control channel is the horizontal channel. So by default, the valve is open. So this is the default condition. But when this pressurized air is made to fall into the control channel, the appearance of valve becomes like this. So here in the top row, we are showing the flow of liquid and how it is being controlled by the control system. So this is being shown by at different instant of time from T0 to T3 here. So here the liquid is flowing smoothly in the flow channel. When the valve is open, that is, it is not functional, so liquid can easily pass through. So here you see liquid is easily flowing, but as you close the valve, it stops the flow of the liquid here itself, and because of the high pressure here, the liquid starts to backflow in the opposite direction. So here we are showing that yes, we can monitor the flow direction of the liquid, and not just of the liquid, also of the particles. So here, just to show the proof of concept, we are using polystyrene 10 micrometer diameter micro beads, and we are showing that when the valve is functional, that is, it is closed, so it is not allowing the small 10 micron micro beads to pass through this intersection channel, because here the this is acting as a barrier. So that means that yes, our valve is perfectly working. So when we release the pressure, that is when the valve is open, all the beads you can see are can pass through this barrier here. So yes, our system is working for one valve. Same way it can work for any number of valve or any complexity microfluidic chip that we have. And this system is very easy to make, and it is semi-automated. We have made use of Python scripting to interface the hardware with the software that we are using to control the system, and it can be used. Here we are showing particles as microbeads, but it can be used with the other biological samples also. For example, cells. So this is going to provide an overall integrated system to perform any microfluidic application. It can be a biological application also, even in the less sophisticated laboratories. Yeah, anybody has any question, please.
So quake valves are fairly old. Around 2000 they came out, and Steve Quake even has on his website detailed instructions how to make these valves, how to make the circuitry for the valves control.
Yes.
So my question is, how is this different from what is there is essentially out in a tutorial form on a website?
Yes, sir. So actually, our work is inspired by them only, but they are actually, this is a piece of overall work that we are doing. Plus, we are making this is overall going to be a miniaturized system, sir. Because we are here going to we are using the single board system and the switches here, and we are doing the optical microscope analysis directly here.
So Quake also uses a very similar system. He has a relay here, and this cannot never be miniature as long as your pneumatic valves are micro scale. So if you have so right now you're doing single array. If you have to do 10 by 10, you'll need an array of these valves, and that's what will consume your space.
No.
And I mean that's one of the
So
issues.
in the microfluidic design itself, if we make the multiplexer and demultiplexer such that it is
Right. So even then you will need a series of valves, right? So I mean, Quake's original paper, he had multiplexers and demultiplexers, and I believe he has a 1024 by 1024 array. And still you will still need at least an array of 8 or 10 valves, and I mean these things have been fairly standard. So there has to be some innovation. I'm not seeing how is it different from the same system that's been there, and it's there in his website as a tutorial. So I don't know.
Okay, sir. So
what's
the point of innovation in our work will stand here in the microscope. Actually, this the next part of the system we have not shown in the conference, but it's going to be in the journal. So we are going to make use of the lensless microscopy instead of the optical. So overall system will be, the analysis system will be really miniaturized. They are making use of the Yes, they are making use of the conventional microscope, that is the benchtop microscope that we have. But we in our lab and in our system, we will be making use of the lens-free microscopy. So that we are going to show in the the next publication that we are going to have.
Okay.
So we have shown its basic module here in the conference.
Diman, do you have questions? Or anybody else?
No, I do not have any questions.
Okay, so let's move on to the next speaker or
Thank you.
next. Yeah, thank you.
Thanks.
So participant.
Before going forward, so I was just checking. So there are many posters which are not accessible at the moment.
So the users can, I think,
So
what the
at
users
least
can do, they can project their screen, and we can see it that way.
Okay.
So I think, yeah. So let me see. So Zakir Hussain, are you here? He was the first one. I don't see him here on the list of participants. Zakir Hussain.
Shubham.
Yes, Shubham is here. So, okay, so
Hello.
hello. Yeah, who is yeah?
Good afternoon, sir.
Yes, please. Can you project screen? Your voice is breaking up, so I hope try to stick to within 2 minutes. So Shubham, maybe we can start with you later on once Pushpa joins. I think I'll have somebody else present right now.
Hello, sir. My poster is 116. Can I show?
Sure.
Uh,
So Shubham will have to come in later on. This is Ben Kutla. No, that's fine. So
What is your name?
my name is Mandeep. Poster number is 116.
the poster number 116 is under some other username, right?
Yes, that
Dr.
poster upload my senior, but I am presenting that poster.
Robin Khosla is the one who is registered as the poster.
Yes, he is the one of the author of the poster.
Okay.
So,
sure.
can I share? Hello.
Yeah.
Yeah, please go on.
So
Sir, is this visible?
Yeah. Yeah.
Okay, sir. Can I start if everyone
Yes,
is okay?
please.
Yeah. So, sir, here I show this accelerometer. That is the final accelerometer is based on SU8 material. But firstly, we optimize it. So in the first, we did some spring optimization. So we took four type of spring. That first is a single beam spring, then double beam in parallel, then double beam at the corner, and then the serpentine spring. So I did this simulation in the console 5.4a. So firstly, I calculated its spring constant by this force and deflection slope. So I simulated this. I applied force here in a micronewton up to 100 micronewton, and then displacement was measured. So the different spring constant I got from this graph, and then
Sorry to interrupt you. So is this
yes,
an in plane or out of plane accelerometer? What plane are you
this is
using?
Z-axis accelerometer, sir. Z-axis out of.
Okay.
Yes, sir. And then I measured this displacement sensitivity after applying the acceleration up to plus and minus 50 G. So then I compared all these results here. If you can see here, is this visible, sir?
Yeah.
So in serpentine, I find this there are parameters spring constant and displacement of mass fruit at 50 G. So serpentine was the spring constant I found was 8.42, and the displacement that it was going in plus z and minus z direction was 17.88 micron at acceleration of 50 G. And when we use this double beam in the corner, the displacement was 7.51 micron, and the spring constant was 33.5. And when the double beam are used in parallel geometry, then the spring constant was 19.2, and the mass proof displacement was 6.80 micron. And with the single beam, the spring constant was 11.3 and the displacement was 11.85 micron. So then we concluded that we can use serpentine's spring for our device that we are planning. Then we used 4 different material for the as a structure material. We went for the SU8 that we planned for the fabrication later on. Polysilicon, silicon nitride, and silicon carbide. So it is the dimension of the serpentine structure shown in figure 4 here. And then we calculated the displacement density for each of the material that we used in the structure material of the MEMS accelerometer. So we find that here SU8 has the highest displacement sensitivity as compared to the remaining one. Then same we went for the stress analysis that if the SU8 is quite reliable or not if we make that structure. So then we did the calculated von Mises stress in the SU8, then the COMSOL multiphysics. Then the stress analysis is shown in figure 6. And finally, the resonance frequency we calculated for each of the accelerometer having different materials. So these all things are shown here in the table. So the displacement sensitivity for the SU8 was 357.68 nanometer per G. And while the for polysilicon, silicon nitride, and silicon carbide was 12.50, 11.30, sorry, 33, and 4.18 nanometer per G. Similarly, resonant frequency for SU8 was around 1.4 kilohertz, while for polysilicon it was 4.21. For silicon nitride it was 4.80, and for silicon carbide it was 9.10 kilohertz. And the stress we measured was at for SU8 it is 2.7 into 10 raised to 6. And but the yield point for the SU8 is 0.06 into 10 raised to 9 Newton per meter square. So this is quite reliable structure that we showed here. And for the polysilicon, silicon nitride, and silicon carbide, all are the stress is shown here. That is 5.4 into 10 raised to 6 Newton per meter square. Here the 6.9 mega Newton per meter square and 7.29 mega Newton per meter square. So we finally concluded that SU8 has a potential of highly sensitive accelerometer with good resonance frequency that having good applications, and that is quite reliable in the stress analysis also. That we concluded finally. Hello.
Any questions?
Yes, sir. Any?
Diman, any questions?
Yeah. So, what is this resonance frequency requirement for this accelerometer design? Because you're saying that the SU8 has a very good required resonance frequency as well. So, what is the criteria?
Yes, sir. For up to 1.4 kilohertz, there are many daily life applications. Like for athletics, we can use this for sensing this movement of the athletes. And for some biomedical application, we can use in the range of frequency range of up to 1.4 kilohertz. There are many applications.
Okay, so I have one. Okay, Diman, are you done?
Yeah, you go on.
Yes.
Okay, so when you use silicon, you use piezo resistance to, or use capacitance to, but generally people. So how do you plan to use piezo resistance with SU8?
So sorry, sir. Can you repeat, please?
So when you use a silicon accelerometer, you generally either use piezo resistance for low cost and probably capacitive for more sophisticated. So now that you have
Yes, sir.
as a polymer, how do you plan to use with piezo resistor to detect your acceleration?
Sir, actually, these I showed these all schemes are capacitive schemes. But if we have to use this piezo resistor, that we can combine with this SU8 only. Like some paper already has used carbon black that is mixed with the SU8 and shown the piezoresistive behavior.
So carbon black is mixed with SU8. So then, so if that
exposed, yes, sir.
So if you are mixing a carbon black with SU8, then you only need to do the piezoresistive at the surface, right? If it's going everywhere, then it won't give you any response.
Yes, sir, you are right, sir. That should be at the maximum stress point.
No, maximum stress point is one thing, so that is one thing, but it has to go, if you do throughout the beam, then the tension and compression will cancel out. You won't get anything. So you need to do only at the surface. So how do you plan to do piezoresistor with the SU8?
But sir, in this work, we did not went for piezoresistive. We did this capacitive sensing scheme.
Where is your second electrode located? If you're doing capacitive sensor, where is your...
Okay, I will show you, sir. So can you see the gray up? This one upper, and this below is this lower electrode. If you can see.
Right. So capacitive again. So if you are making a low cost accelerometer, capacitive is not the way to go. You'll have so much nonlinearity and issues. Then
yeah, sir. Actually, we have almost completed this work. We did this using grayscale lithography. So this whole device is made with a grayscale mask in the single exposure.
Right.
So,
SU8 has no doubt about it. You can make the structure. My only question was sensing. And if you can do piezoresistive, then it would be best. But so there's some.
Yes, sir. But piezoresistive will be, I think, more complicated as compared to in view of this fabrication process.
Okay, sure. So we can move on to the next one. So Dhiman, poster number 1. This is a 116. Maybe we can go to 117.
Oh, okay, sir. Then thank you, sir.
Okay, can we have the next presenter, poster number 117?
Sir, actually, my poster number was poster number 115. Earlier, I couldn't hear you. That's
So
why I missed it.
our presentation will happen when Professor Pushpraj Singh is there, because there needs to be 2 people who are not your advisors to judge your poster.
Okay.
Okay.
Thank you, sir.
So I will request Mr. Murugan, number 117 here. Development of a MEMS threshold G switch with enhanced contact time. It seems he is not here.
We can go to poster 120. Miss Niharika.
120, Niharika.
Hello, sir. My voice more audible?
Yeah, we can hear you. Can you project your poster?
Yeah, sure, sir. Is my poster visible?
Yes.
Good evening, sir. So, my poster topic is...
Before you start, you have 2 minutes. Try to stay on. Okay, so your time starts now. Okay.
Thank you, sir. So, topic is effect of actuation electrode design on RF performance, RF MEMS shunt switch. Actually, we have 2 type of RF MEMS switch, shunt switch and series switch. So basically, we have to design a electrode position here in this picture, I'll zoom in this picture. As you can see that, in order to actuate in electrostatic actuation, in order to actuate the top beam, we have to position our actuation pad in order to have low impact on RF performance of our switch. So this paper is designed on the performance effect of biasing electrodes on the RF performance. So type 1 is already available. In this type, the biasing is going below the our signal line. That means fabrication step is increased. In type 2, we have to make, this design is basically, in this design, fabrication is on the same line, but we have to fabricate one more process in order to connect both the grounds. So there are different type of, these 4 types of actuation arrangement are already available in literature, and this one, type 5, is proposed by me. In this case, what we have done, we have edged out some, this is ground plane, this is also ground plane. We have edged out some part of ground plane in order to directly access this biasing as an actuation pad, and we can directly connect probe to these parts, or we can use these actuation pad to connect larger actuation pad on the other side through wire bonding, or we can directly use this as a probe. So including this, etching this in the ground plane will affect on the current path of the RF signal. So it will increase the inductance of our device. So in order to compensate this RF performance affected, what we can see that this edged out part is introducing inductance effect. So this effect results in changing the performance of our structure. So in order to manipulate this, we can reduce the length. This inductance effect reduces the phase velocity of our structure. So in order to maintain same performance on given frequency, we can reduce the length of our structure to obtain high performance in our device. So this is the graph showing that this one is the normal simple transmission line, and of S parameter, return loss for a simple unloaded transmission line or simple without any MEMS switch, and this is for my proposed switch return loss. And these 4 are for the type already given in the literature. So we have found from simulation in HFSS that we have improved our performance a lot as compared to other type, and further we can also do optimization to achieve it same as there was unloaded transmission line. And in this graph, I have compared different type of substrate we can change, the substrate we can use to make our device. So as we can see that silicon is giving high resistive. Basically, this is a high resistive silicon simulation. Is giving best performance on in same situations. So in this structure, we have in third figure we have seen that by reducing the length, that I have already told that by affecting the by making defects in the ground structure, we are disturbing the inductance of transmission line. So directly we are disturbing the phase velocity. So in order to as phase velocity has reduced, in order to maintain, we can reduce the length and we can obtain almost same performance with the or better performance in our case for type arrangement we have designed for our structure. That's it. Hello.
Yeah, thank you. I think
sure.
good you structured. Okay. So any questions? I'm good. Okay. I think we can go to the next one. Shivam Pawar. Yeah. Thank you, Niharika. We can go to Shivam. Shivam. Yeah. Okay. Are you there, Shivam? Let me see list of participants. So there's no Shivam Pawar unless somebody else is on it.
Sir, I'm Shubham Saxena is here.
Shubham,
No.
we'll wait for Dr. Pushpa before
Okay,
we
sir.
do yours. Okay. So Shubham
Okay, sir.
Pawar is not here.
Next is Faizan.
Faizan Tariq Beg. Poster number 112. Faizan is not here. Okay. Next is, I think, Shalini Dhiman. You're on this paper, so I would like him to be there. Vinit Yadav, are you here?
Yes.
I see Vinit Yadav here.
No,
Okay,
he is also not with me. So
you're okay. Okay, so then we'll wait for Push Price to come there. Sushil Kumar, are you there?
I am here actually.
Yes, sir. I'm here only.
Okay. So
Yeah, Sushil is here, sir.
Okay. So then we can start with the Subham. Then I can probably. So Shubham, if you are ready, okay, start your presentation. 2 minutes. Stick to time. Hear you.
Okay, thank you for
Shubham, there's a problem with your audio. Your
So your audio is not clear.
no, it's not. No.
now.
No. Try to speak some sentences. So it's speeding up for some reason. Do you have it on phone? No, Shubham. So we can't. So let us get poster and probably we'll ask. Or maybe we can try later on. Sure. How to do it. So Pushpraj and Dhiman, maybe we can look at his poster later on directly and ask him questions because this is not his audio is not good enough to present.
okay.
Okay, so Shubham was there. So now I think Divyajyoti you can present 115.
Okay, sir. So I'm sharing my screen. Is it okay, sir?
So Shubham, I can see Shubham's screen now. Divyajyoti present.
Yes, sir. I'm sharing my screen.
Your screen, please.
Yes, sir. I'm sharing my screen. Can you hear me?
We can hear you. We can't see your screen yet.
Yes, sir. I'm sharing. Please give me a minute. Can you see? Can you see it now, sir?
Yes, I can see it, but probably need to go in full screen
David,
mode.
zoom in.
Yes,
Yeah.
I am zooming in.
Go through it section by section. Okay. And, yeah. So go through it section by section, and you have 2 minutes. So start.
Now, can you see it, sir?
Sure. Go through it section by
Okay.
section. Spin on one section, then
Okay, sir.
another.
Okay, sir.
Okay.
Okay, sir. Okay, sir. Okay, sir. Hello, everyone. I am Dibyajyoti Mukherjee, and I am from Interdisciplinary Microsystem Lab, IIT Delhi, from Electrical Engineering Department. And in this work, we present a feasibility study of unified microscale magnetoelectric transducer platform for wireless implantable devices. And we have designed a micro scale magnetoelectric based transducer structure for two different purposes, and to unify it to design full phased self powered neural implantable devices. So first thing we have done, that is we have designed a magnetoelectric transducer structure to operate it for low frequency application at 50 kilohertz. And we have also designed, by modifying the geometry of that structure, to operate the device at 2.45 gigahertz, and that can act like a magnetoelectric antenna. And another thing we have done, that is we have optimized the thickness and the number of laminates to minimize the eddy current loss through any ferromagnetic material like FeGAV. So in the first section, in the introduction part, we can see these diagrams are taken from two articles. They have proposed a design, that is a pair of transceiver circuitry to transfer the power wirelessly deep inside the brain. So why we are using this magnetoelectric structure? That is the conventional electromagnetic based and IPT based, that is the inductively coupled coiled based structure. Their size is a very difficult thing. There is a limitation, and their reliability is another thing, because wired structures are very often gets infected by any foreign object, and they are also invasive in nature. So using this magnetoelectric structure, we can miniaturize the device dimension, and the reliability is quite high, and they are less invasive. The operational frequency, when we are using lower frequency, the device size we can minimize, because magnetoelectric structure works on the principle of acoustic resonance. That is, when we apply a magnetic field, AC magnetic field, the magnetic field is getting sensed by the magnetostrictive layer, and the magnetostrictive layer produces the strain, which is then transferred to the underlying piezoelectric layer, and through the piezoelectric layer we can collect the the equivalent electrical potential. This is the principle on which this works. So the theoretical background of this work is, that is the to minimize the large size device and to make a efficient device that can be used for self powered neural devices, and also to optimize the eddy current loss in any ferromagnetic device. We can see from this formula that the eddy current loss increases as we increase the frequency. So we have also optimized the eddy current loss by introducing a dielectric layer, that is alumina, to minimize it for 10 kilohertz to 10 gigahertz frequency range. And from the Faraday's law, we can see that breaking the eddy current loss into smaller loops, the total loss can be reduced. And these are the result analysis that we have done. That in the left part, this is a magnetoelectric based transducer structure. We are operating it for 50 kilohertz frequency, and when we are applying AC magnetic field of 1 millitesla, it can generate 15 millivolt. And for the next structure, when we are applying 10 nanotesla magnetic field, it is operating at 2.45 gigahertz frequency and can generate 0.14 microvolt output, and it can be used as a sensing device and to establish a communication system, wireless communication system. And we have also done the BVD model fitting, that is to obtain the uh, admittance magnitude and admittance phase for both the structure at the resonant frequency, and this is for the 50 kilohertz structure, and this is for the 2.45 gigahertz structure. And coming to the last part, here we have optimized the thickness of the laminate by introducing alumina substrate. And here we can see that as we are increasing the number of laminates, the loss is getting reduced. And while in case of the laminate, number of laminates is 10 and the thickness is 35 nanometer, the loss is quite high. And here we have compared the FEM based simulation from the Commodore multiphysics and the closed form equation that I have already mentioned about. We have compared both the result and obtained its thickness of the magnetostrictive material, that is 10 nanometer. And we can see that as the frequency is increased, the loss is getting higher and higher. And for the lower frequency, near about 10 kilohertz is quite low. So we can optimize the number of laminate and the thickness of the laminate to minimize the loss, and thus we can improve the performance of our magnetoelectric power transfer device for neural implant. And lastly, I would like to conclude that in this we have provided a brief introduction for a unified design toolbox for optimizing the microscale magnetic transducer for battery-less, cell-powered wireless communication system in case of neural interfaces. And we have optimized the thickness and the number of laminates. We have compared the FEM-based results and compared it with the analytical equation for 10 kilohertz to 10 gigahertz. And further, we want to set up a complete system and we want to integrate with the CMOS based power management circuit to operate it entirely as a wireless system in case of brain implants and neural implants. Thank you. I would like to thank IIT Delhi and DST Sera for providing the necessary funding. Thank you, sir. Thank you, sir.
So what kind of resonator is it? A fixed beam resonator, or is it just the resonance of the film that you're looking at?
Uh, no, sir. It is a single. This is a single side clamped beam.
So it's a cantilever beam because your figure that you've shown.
Yes, sir. Yes, sir.
So,
Yes, it is a cantilever beam.
and your magnetic material is your elastic material as well, or are you coating it on some substrate?
Actually, we are coating. We are placing the silicon dioxide layer, then piezoelectric layer, then magnetostrictive layer. So first, the magnetic layer will produce a friction. It will be transferred to the piezoelectric layer.
That I understood. What's your structural layer for your cantilever? Is it silicon? Is it silicon? What silicon
Silicon
dioxide?
dioxide. Silicon dioxide, sir.
So how thick is your silicon dioxide cantilever?
It is about 600 nanometer.
600 nanometer. And how big is your structure?
For the 50 kilohertz, our structural length is about 100 micrometer in length, and it is about 25 micrometer in width.
Okay, so 100. So I mean, again, why choose silicon dioxide? Why not choose a stiffer material?
Actually, we have observed that using the silicon dioxide, we can generate higher voltage. Earlier, we have also studied it using the silicon-based substrate, but we are getting lower voltages. So we just chose silicon dioxide for this purpose.
Why is that? I mean, can you explain why that is?
Maybe because of the stiffness that it is providing.
Okay, so I mean, see that you're comparing apples to oranges, right? Because you can adjust the size of your structure to give you the same resonance frequency, I guess.
Yes.
So, okay. I guess the answer is you actually want a low stiffness material with so that your collection area is larger. That would be my guess.
Can you please repeat, sir? I couldn't hear you that time.
Guess is you're intentionally using a low stiffness material, so it's over a larger area, so that you're collecting over a larger area.
Actually, yes, sir. Means combining the whole, that is the frequency also depends on the structure. So maybe whatever you are saying, that is correct, sir.
Okay, so maybe on some other. Okay, Pushpra, any
Thank
more
you, sir.
questions? Yeah.
So
Okay,
I'm saying, like, why did you choose this FEGA-B? Specifically.
Actually, the combination of FeGAB and aluminum nitride we have chosen for the piezoelectric material. The combining this FeGAB and aluminum nitride, it acts as a zero bias material. That is, we do not require any biasing magnet for this purpose. And if we choose any other magnetostrictive and piezoelectric material, that time we require some biasing field, means some permanent magnet. So for this structure, we have done some literature survey, and got it that for the combination of FeGAB and aluminum nitride, it is zero bias structure. So we can just use any AC magnetic field, and we can generate some voltage.
Also for the, because you say that this is for the wireless implantable devices, right? So how much power is your target? How much power you really want to generate actually from this?
Actually, we want to generate about 10 microwatt, like 10 mic kind of power from this device.
Are you close to your target, or how is it?
Now we are getting about 5 microwatt, almost 4 to 5 microwatt power, but we need more and more analysis on this part. So we are
But
doing more and more analysis.
have you started your fabrication in this?
No, sir, no, sir. So far, I have not started fabrication in this part.
Okay. Okay. Thank you.
Okay, thank you, sir.
Next person.
Yes, sir. So can I stop sharing, sir?
Huh? We're done. Thank you, Debijyoti. So is Murugapan is probably not here. So Satish, can you present?
Am I audible? Hello, sir.
So your poster, just
118.
Satish.
118.
Okay, 118.
Yes, sir.
Yeah.
Am I audible, sir?
Yeah, you can hear you. We can't see your screen.
Yes, sir. I'm sharing.
Okay. So,
Good evening, everyone. So, I'm
Yeah, please go ahead.
Yes, sir. So we are presenting the spring softening and damping effects in micro resonators with the internal dielectric transduction. We are using that. So why this study is about the spring softening, because see, resonators are versatile devices used in many applications like oscillators, band select filters, and even in sensors like mass sensors and everything. So this study dedicated a device.
yeah, continue. Get straight to the point.
Satish, we cannot hear you.
Satish, your voice is very low. We can't hear anything.
We can't hear anything. Your voice volume is very less. We can't hear you. Use your computer mic instead of your microphone is probably not working properly.
Okay.
Okay. So get started. You don't have much time.
Hello, Satish.
Hello, Satish. We can see your screen. Just go to PowerPoint. Just go to PowerPoint. We can see your screen. You don't have to log in. If we can see your screen, please don't try to connect. Just click on PowerPoint and get started.
I think he cannot hear also, I think.
Yeah, he can't hear. His volume is low. He can't hear. His system
think
volume is low.
to the next one and probably come back to him later on.
Yes.
Co-host, if
So
you
maybe we
can
can just disconnect.
thank you. This, yeah, I have else. co-host can, I believe can do it.
क्या हुआ?
I think co-host, can you
close करो.
knock Satish out or something? I think, or the next.
Disconnect. It has disconnected.
I think Nadeem can present and
Yes, sir.
okay. So Satish, you have some technical problem. We can get back to you later on. Please log off and log back in.
No, so if the next presenter starts sharing the screen, it will be, I think, automatically.
Nadeem, you can get started.
In chat box, you can write the message for him, Satish.
Close.
Yes.
Okay, Nadeem. Nadeem, can you start also?
Yes, sir. Am I audible and is my screen visible?
Yes,
Yeah.
Okay. Hello, everyone. My work is on tuning of bistable piezoelectric MEMS energy harvesters for low frequency, low G applications. The focus of this work is self-powering of IoT nodes, and we are concentrating on the vibration energy harvesting side. For this work, we have been designing and optimizing nonlinear vibration energy harvesters with considerations of shape optimization. As you can see that we have a focus on bistable systems, which is a nonlinear system in which we have the availability of interval oscillations, which are high amplitude frequency independent oscillations, providing a broadband response and amplitude dependent snap through oscillations, but with a threshold amplitude requirement that needs to initiate these oscillations. So when we look at the design perspective of these types of energy harvesters, we see that we need to consider nonlinear harvesters, and in nonlinear harvesters, we focus on bistable magnetless buckle beam designs. Theoretically, we have understood that clamped beams or double clamped beams are inherently nonlinear, and we need to do several small modifications to transform them into bistable systems. Since bistable systems are advantageous for wideband response, and also since the vibrational energy present in the environment is wideband, so bistable oscillators are the best choice in this case. So in this work, what we have done is we have considered double clamp beams and done a shape optimization to understand which type of buckle beam design is best suited for bistable operations. Given the figure, which is the general beam shape, we have variable tapered width and variable curvature, and we have two types of bistability introducing mechanisms. The first one is the axial buckling, and the second one is the residual buckling. We see that when we introduce bistability into the system, the main thing that changes is the linear stiffness. In both the cases, either in axial buckling or in residual buckling, the linear stiffness changes its sign. That is, it becomes negative when the beam buckles. And as soon as the beam buckles, there is an energy barrier that is created between the two stable states. The energy barrier is dependent on the nonlinearity. If we if we increase the nonlinearity, we decrease this energy barrier. So our main focus is to decrease this nonlinearity while using the bistability mechanism and interval oscillations. So what we have done is we have designed three different structures in COMSOL. The first one is a clamped beam. The second one is a curved beam. The third one is a tapered beam, and we have analyzed its eigenfrequency, and we have seen that the tapered beam structure, as expected, is having a low resonant frequency. But to understand the bistability mechanism, we need to understand how the potential energy curve of these three beams vary. So what we have done is we have applied a fixed force to these beams axially, and then we have plotted the response, plotted the potential energy by varying the transversal displacement. So what we see is we see that the tapered beam structure has the lowest energy barrier. That is, it has the least requirement to initiate interval oscillations. In the other figure, we also the energy barrier difference is evident. So the first two graphs are for the axially buckled beams, and the second two graphs, the other two graphs are for residually buckled beams. Residual buckling is also another option to initiate buckling in a double clamp beam by varying the fabrication parameters and intentionally introducing residual stress into the different multi-layer structures. And again, see that we are able to get a, bistable curve in case of residual stress beams. But the point is that these energy harvesters should be realizable and should be reliable. So for that, what we have done is we have tried to understand the von Neumann stress at the clamped end of the three beams. So again, varying the buckling parameter, we see that the tapered beam has the least variation of maximum support stress or the von Mises stress when it is buckled. So the values are quite low and are very less than the tensile strength of silicon, that is the structural material in this case. So even from stress analysis, we see that the tapered beam structure is best suited for use in a vibration energy harvester for low frequency applications. One more important result that we have seen using bistability is the frequency tuning. That is when we apply an axial stress to the beams, the resonant frequency of the beams change because of spring softening and spring hardening effects. So this kind of result uh, is very good for the reliability of the device because we can tune the frequency to whatever range we want and without using additional proof mass that increase or add to the stresses at the clamp ends. So we can directly tune the beams to our resonant frequency and without using some additional proof
Can
mass.
you wind up?
Yes, sir.
Okay.
So concluding this, that we have shown that tapered beam structures have minimum energy barrier and support stress, which ensures reliable low amplitude interval oscillations. A fixed tapered width ratio optimization of the beam is required to further optimize the designs, and also a multi-layer structure control of residual stress is also required. So we are planning to fabricate our designs using piezo mumps process in future. Thank you. So if you have any questions.
I have a question.
Yes, sir.
So how do you control the post buckling behavior if you're applying a force and it's buckling? Is there a way to control the post buckling behavior?
Yes, sir. So for force buckling behavior, we
Post
are
buckling.
actually buckling. Okay, post buckling behavior.
Yeah.
So first we will define the parameters that we want the beam for. We want the energy harvester for. So for example, I want a energy harvester of 50 hertz resonant frequency. So I already know what is the critical buckling displacement that needs to be applied to this beam. So I will only apply those parameters to it to buckle it to the exact height and exact stress.
Okay. Yeah. So I think we'll rush through the next ones. Okay. So Nadeem, you are done.
Yes, sir. Thank you.
Okay.
Hello, sir. May I forward Charlie?
Okay. Please go ahead. Ezan Tariq Beg is not here. Okay. Please go ahead. And we'll really need to stick to time because the session is running out. There has to be another session here. So we really need to. So, in fact, now I will keep you to 2 minutes. Right? Okay.
May I start?
Please.
Yeah. Hello, everyone. This is Charlene. I want to present my work that is writing and dividing transition in chemically structured surface for the application in droplet-based energy harvesting. it's a theoretical approach. And so I want to introduce our upcoming device that is energy harvesting device. Since we are going to harvest energy by microfluidic droplet. So there's some basic results we studied like morphologies of liquid on a chemically structured surface. So the concept behind the device is variable capacitance and the bulge instability. It's and the objective of this study is we want to study some contact. We want to optimize the channel width at various contact angles of hydrophilic and hydrophobic surfaces. So hello. Yeah, actually we droplet needs to roll over on the surface with minimum friction losses, so which require low contact angle stresses. So contact angle stresses occur by roughness and heterogeneity of surface, which leads to the droplet occurring in the different metastable state. So it's all about introduction, and I want to come on simulation methodology. To simulate these results, we used Surface Evolver 2.7 is an interactive program
मैं
that
कह रहा था कि
that used to study of surface liquid surfaces which shaped by following parameters that like surface tension, contact angles, and volume constant. So these images show some ideal case and real case. In ideal case, there is advancing receding angle that is equal, and in real case, advancing and receding angle that is not equal. So it's all about contact angle stresses. So our aim is to optimize the channel width where we can get. Hello.
Please continue.
Yeah. So I want to come on results and discussion. These are the wettability on surfaces. Wettability on surfaces in first image. Here's low wettability, like a contact angle is greater than 90 and less than 180 degrees. That means solid and liquid interaction is weak here. And in the section of wettability on surface, B image shows contact angle is less than 90, that is high wettability, and solid and liquid interaction is weak, and liquid and liquid interaction is weak here. And C is perfect wetting spreading, and that is contact angle is 0 here. So the first section is shows only about interaction of liquid with surface, and second is ring-shaped surface domain. So as I said, we want to optimize the channel width. We can where we can get some less minimum friction losses. So this shows as we increase the volume of channel and contact angle, the channel grows until it undergoes a certain transition. So
Shalini, you can wind up now within next 30 seconds or something. That would be wonderful.
yeah, sure. Okay. So this shows channel state which now exhibit a single bulb. This ring-shaped circle domain shows only that, and this is a morphological transition of bulb by varying channel width. We studied some different channel width, and we studied where the bulge is deepening from the channel boundaries. So it's a typical like we optimize typical channel width that is 800 micrometer, where we cannot get deepening of from the channel boundaries. And these are the two we studied two different two hydrophilic strips that is separated by hydrophobic strip. That is only where we go to know that there's some division of droplet between two hydrophilic strips. So conclusion is like for low contact angle hysteresis, channel width is desirable. It will be around 800 micrometer, and this graph shows only that part. Thank you.
Okay, so we have to wind up now. We'll join back again on Saturday. I think there are many posters which are left to be evaluated. So I think we'll send out an email probably. So we have to move now because there's a plenary talk, which is going to happen here. So we'll do again on Saturday. I think the details will work out and send it to you. But unfortunately, now we have to end this session. Thank you all who could present, and thank you everybody else for joining us. So hopefully rest of you will meet your posters on Saturday. Yeah. Thank
Hello.
Yeah. So
Yeah.
Manan, you can.
Yeah. Am I audible? Yeah.
Yeah.
Yeah. Okay. So thank you, Professor Bhaskar, and sorry for interrupting you in between the poster session. So I would like to welcome everyone to the evening session for the neuromorphic symposium. We'll start in the same neuromorphic memory devices symposium. We'll start in this same room. So because we are already running out of time, I'll not waste any further time. I'll quickly introduce our first invited speaker. So our first invited speaker is Dr. Amir from VBIT Nano, and we are really honored to have him here among us to share his knowledge and his research in the domain. So Amir has more than 2.5 decades of experience in device and technology, manufacturing, reliability, and product on the semiconductor industry, with an expertise in flash memory. And prior to it, he was working as a senior engineer in some of the leading technology companies, including Intel, SanDisk, Micron, Marvell, and he has a broad expertise in multiple engineering fields, all the way from device technology development, quality, reliability, and ASIC. And he has also worked as a senior device engineer in developing advanced 45 nanometer NOR flash technology. And so we would like to welcome Amir to enlighten us with his nice work. So please, Amir, please feel free to start and welcome once again to CWE. It's great to have you here. So hello, hello.
Hello?
Yeah, hi, Amir. Can you hear me?
Yes, do you hear me now?
Yeah, I can hear you now.
Okay, great. Thank you, Manan. Hello, everyone. Thank you for inviting me to this session, Manan. I'm very excited to do this. It's kind of strange to me to present in such conference virtually, and I can't wait to travel and talk in front of people again. So thank you for this kind introduction. Before I begin, I want to tell you a few words about myself. So I've always been fascinated by two things. The first one is technology, and the second one is how our brain works. So when I was young, I studied material science and electronic engineering, and I got the experience of the amazing world of semiconductor. Lucky enough to see development over several generations, since micron scale of the 90s to the nanometer range of today. But 20 years later, I found myself back in the university learning psychology and cognitive neuroscience. So that was my other interest, to better understand how our brain works. And I always wonder how it will be possible to combine between these two worlds, technology and neuroscience. So I found that these two are combined well in neuromorphic computing. So that was a bit about myself, and I would like to present the outline of my talk. I'm going to talk about fully integrated spiking neural network using silicon oxide based ReRAM as a synaptic device. It's a work that we did together with Letty. So I'm trying to advance the slide. So, okay. Yeah, now it's coming. So in this presentation, I will discuss the fully integrated spiking neural network
using a ReRAM made by silicon oxide. And I will start with a brief introduction about the technology and its operating principle. And then I will briefly introduce the ReRAM market a little bit about, and I will talk about our neuromorphic demo that we presented in 2020. Just I'd like to introduce a little bit about Weebit Nano. I haven't talked about it, but we are kind of young company that we started in 2015 to commercialize ReRAM technology. This is just our company management. So we have Dadi Perlmutter is the IEEE fellow. He was the vice president of Intel. Made it to be the executive vice president, second in command to the CEO. Yoav Nissan-Cohen was the tower, started up Tower Semiconductor, and he was the CEO. And Kobi Hanoch is our CEO with the business experience. And that was just an introduction. So before we continue, I'd like to go over a little bit by a basic principle of ReRAM technology. It is based on simple structures of metal, insulator metal kind of structure with the anode and cathode in a dielectric material in between. The basic principle is fairly easy. It's based on creation and destruction of a conductive filament of oxygen vacancy within the dielectric layer. And when we apply the positive voltage, the top electron, we can induce a forming process, which is basically a soft breakdown of the oxide, which create a conductive filament between the anode and cathode. And this leads to the conduction of the device. And after we formed this conductive filament, we can cycle between a low resistive state and a high resistive state. When we want to create high resistive state, we are just applying a negative voltage, and we are creating a gap within this filament. So the data can be erased with the reset operating in high conductive resistance state, and recreated with a set operation, leading to a low resistive state. So that is just the basic principle. It is a very scalable technology because the filament is just nanometer size. So in scaling, it doesn't change much. It's very easy to integrate, just basic few layers. And also its ionic movement within this filament can easily mimic biologic synapses because of resembles. The ReRAM itself, this is the resistive RAM, has many advantages and is considered to be the next generation non-volatile memory because it's very energy efficient. It's very fast compared to flash memory. It's highly scalable, and it's very, very low cost in comparison to the floating gate technology, which requires a lot of added masks. So a few years ago, we started to collaborate with LETI, which is one of the most innovative research institute in Europe and in the world. And our collaboration yielded a very exciting development. So we started the 250, 216, and in 2017, we were working on single devices. We scaled up to bigger arrays later on, and up to megabit array about 2 years ago. And this demo that I'm showing today was presented at the Flash Memory Summit in 2019 and in ISSCC in 2020. So now we are continuing stabilizing and developing the technology of various technical parameters. This is a great challenge and very, very interesting. So this is just the basic stack that you can see here in the cross section between metal 4 and the last metal. It's very tiny. This is a magnification that you can see at the bottom electrode, the top electrode, and just the silicon oxide in between. You've got the characteristic, the IV characteristics of set and reset, which creates a memory window. Okay, now I'm going to talk about the ReRAM for artificial intelligence. So there are a few modes of usage models for using ReRAM to accelerate artificial intelligence. The first one is a classical deep neural network accelerator, which works as a multiply and accumulate operations. So instead of implementing them with a lot of usually memory, the usual stuff is with DRAM, which you need to export the data between the CPU and the external memory. That consumes a lot of energy. So the first usage is doing a crossbar architecture, and by doing so, you get a built-in MAC operations with Ohm's law and Kirchhoff's law. The resistive RAM cells are programmed in between these two metal lines, metal layers, and their resistivity level will naturally provide you the sum of the accumulation, and the multiplication is being done on this. So it is possible to store weights and all kind of stuff, and needs to scale down, scale up. So this is a say more direct approach. It's the main challenge is scaling up, and this crossbar architecture needs not just resistive RAM but also a selector. And this is currently not mature enough, so it got a great potential, but still is not commercialized yet. The higher approach, the more next generation is the neuromorphic chip of the AI, which is more resembles the biological cell, and this is to implement synapses and neuron and synapses, and by spiking, you can transfer the signals in spikes between neurons, and this is more challenging, of course, and this is what we're trying to do here in our work. So why doing so? It's quite, this is the way our brain works. So everything you can do in computing, in classical coding and computing by using CPUs and GPUs will consume a significant amount of power, and will be limited. You will need a massive amount of power, and the computer does, the human brain or any brain, biological brain, does much more computation in a parallel way, but without consuming a lot of power. So this is obviously the aspiration point for brain-inspired computing. The human brain is a lot of parallelism. It combines the memory and computation together, so you don't have to export data between memory and computing. And the spike coding is much more energy efficient because you don't have to have a clock that works in very high frequency. You can just, instead of gigahertz, work in single hertzes or tens of hertz frequency, very low frequency, but only react to events. So spy coding versus classical coding. Classical coding is what is implementing artificial intelligence today. It's got a lot of significant progress during the last decades. The spy coding, on the other hand, is the communication, the neuron by spikes. It's very noise tolerant, unlike the computing that every fault can fail the device. It's very low power, and the co-integration of neuron and synapses, it saves 200x energy of exporting with and importing to an existing to an external memory. So I will now talk a little bit more about the demonstration. We call it a spirit. It's the first co-integration that we are, according to our knowledge, of analog spiking neural network on based ReRAM-based synapses for inference tasks. It's a proof of concept demonstration. Generally, you have a tablet. You just draw a number. It's an MNIST recognition task. You draw any digit, and it's supposed to decide which number, which digit did you write. I will I will elaborate of how it works. Generally, the interface is that you are writing is this tablet. It goes to an interface that process the data, and we are storing the weights inside inside the chip with the ReRAM. So that's where we program it. I will talk about it later. So it's combining analog neuron and our silicon oxide ReRAM synapses. It's fully connected, so each neuron is connected to the entire images. Everything is connected. The grayscale, the digit is converted into grayscale, and then it is translated into spike frequencies. And we also implement integrated fire. So this to mimic the biological operation. Yes, this is a bit of it on the explanation. We are the input is being done on the tablet. It's downscaled to 12 by 12 array, and it digitized for a gray level. And this gray level is converted to spike frequency, where the pixels that got the strongest gray level, you've got more spikes, and the less gray level is just the spiking frequency decreases. So this 12 by 12 image is fully connected to the neuron, and then it's a perspectron. We got 10 neurons at the end, because for 10 digits, in order to inference between 10 neurons, so everything is connected to all the neuron, and it's multiplied by the weights. So this is a layout of this small chip. The weights are stored in the ReRAM array. It's only 11.5 kilobit of ReRAM with 1T1R configuration. It's being done on 130 nanometer CMOS. So first of all, the training is being performed offline by backpropagation, which is currently most efficient algorithm. So it's a one-time trained, and we have a hyperbolic tangent hyperbolic function in order to have a threshold, positive and negative threshold, and to clip this signal. So in this weight, in this map, you can see the more or less the each spikes, each synapse can give you excitatory or inhibitory signal according to the weight. So so for each neuron, you've got a different map according to the number, to the digit it needs to recognize. So once you draw the number on the screen, some signal will be inhibitory, some excitatory, just like in a biological, and it's all being programmed into the specific area where we store the weights. So these weights are being stored, and they can be updated. We did not do that on this demo, but it's supposed to be non-volatile in order to be updated for accuracy and continuous training. This is the neuron design. So we took for each synapse, we got inhibitory and excitatory neuron cells, and we integrate the entire signal, and eventually it creates everything is stored in this capacitor. We also have the implementing integrate and fire neuron that is the refractory. There is the period that you can integrate the signal, and then refractory period, which at the end of this it can be tuned, and then the integration of these spikes is being fed up to the neuron themselves, and then whichever got the most of the spikes fires, and then it's the neuron that has the most of the fire is the digit that is being used. So in more general, when we write the digit, it's go to AER, which is address event representation. It goes to the FIFO, and then address decoding. So address decoding is connected to the word line, and the word line is common to the entire neuron, and it scans all the word lines according to the address to integrate whatever the spikes according to the weights, and then we have also a termination parameter, which is counting the number of spikes, and it determines which neuron has most of the spikes, and in order to do the inference of recognizing the digit. So after we did that, we did some benchmarking to assess the system performance. In this chart, we can see the accuracy and the consumption, the required number of spikes for recognition according to the termination. If we allow less time to integrate the signal, then the accuracy drops. So we should have a sufficient number of delta S in order to reach to acceptable accuracy level, and it integrates more spikes. So on average, we have 160 spikes to recognize an image to get to a distinct decision. and we calculate about 3 picojoule at the synaptic level. We have some overhead for the SPI interface and all the logic itself, and we reached about 82% of accuracy. So that is not bad for a first demo. If we look here at all these similar spiking and non-spiking recognition task, we see that our work is just on 130 nanometer technology, which is not advanced. It's not the state of the art of 14 nanometer, 28 nanometer. Here in the spike, you can see here that spiking is being implemented with SRAM, and we are using ReRAM, but the number of synapses is very, very big. So overall, it consumes a lot of power. In our case, we just use the least number of synapses, just 11K, 11.5K. So we don't have a lot of synapses. All the other uses much more, and still it allows us to consume a very small amount of power and reach nearly acceptable level. So in this level, you are recognizing 80% is the theoretical. Of course, it can be upscaled if we increase the size from 12 by 12 to more than that, and going to more advanced node and have a more efficient. Here we did a lot of. We wanted to be bulletproof, so we didn't use. We used the 8 rerun cells for a synapse. It can be much less than that. So right now we are planning the next demo, which will be very exciting use case. It will be on advanced technology of a 28 nanometer FDSOI, and it's going to be some kind of LiDAR application for recognition. And it will be much more all the metrics will be much more increased. So I'd like to conclude my talk by summarizing that spicy neural network. We were the first implementation that we saw that practically ReRAM implementing a spiking neural network with a fully connected matrix using ReRAM and CMOS integration, recognition accuracy above 80%, and quite a good energy efficiency. So thank you for this talk, and if you have a few questions.
So thank you, Dr. Amir, for such a wonderful talk. Actually, Professor Manan Suri had to leave because of some urgent meeting, but he will be back soon. So thank you again. Participants, if you have any query, then you can ask your questions here.
Thank you very much.
Maybe let me start.
I have one question, sir. Hello, can you hear me? Hello,
yes.
Professor Amit?
Hello?
Yeah, can you hear me now? Professor Amit?
Yes, yes, I hear you.
Yeah, I have just a small question for you.
Go ahead.
Achha, just one of the slide you have shown that you are using SPI communication for generating the spikes. When the signals are sending through the chip and generating the spikes, you are using an SPI-based communication in the chip. So isn't that is it possible to use the parallel communication in that case? Because SPI might be one of the bottleneck of flow communication and generating the spikes over there.
Unfortunately, I didn't hear I couldn't understand. The line is not that good. If you can repeat.
Is it audible to you now, sir?
Hello?
Hello, is it audible to you now, sir? Is it audible to you now?
You're asking if it's
Dr. Amir, are you there?
Yes.
Okay.
Hello? I hear you, but I difficult for me to understand. Can you try again?
Yeah. So you are using SPI based communication over there for sending chip and generating the spike. SPI communication.
Yes. Using
So
SPI communication, yes.
yes. So can't we use parallel communication over there because SPI might be one of the bottleneck for low speed and other facilities.
Yeah, that's. I think that's interesting thought, but yeah, we use standard interface. We will need to check it out. It's a good comment, but I don't have any information about different interface.
Oh, thank you, sir. Thank you.
Hi, Amir. Can you hear me? Vinayak here from Global Foundries.
Yes.
Yeah, very interesting talk. So I have two questions. The first is, what is the typical cycles do you need for this kind of applications from RM?
Can you repeat what is there?
How many number of cycles is sufficient for this kind of applications? The write cycles.
Oh, okay. So, yeah, our cycle right now are using a single pulse. So the forming is a longer process that we're trying to optimize. Currently, the set and reset are single pulses. Right now, we are working on a module which is integrated into IP, and we are working on a more sophisticated programming algorithm. We are right now designing it, but we are still doing it in a single pulse.
Okay. Yeah, thanks for that. So my question was another question related to for your AI computation. So how many number of cycles do you need from RM for AI computation?
So are you referring to the cycling endurance?
Yeah.
Or for the weight themselves for the updates of the information?
Okay, so the question is more related to the endurance of RM since it is limited. So typically, what kind of number of cycles is enough for this kind of AI application?
Oh, okay, yeah. So at this demonstration, we just program the weight once, and every once in a while there's going to be a weight update. So it's not a lot. It's not a lot of cycles. You don't need a lot of cycles. You just update it as the model get better or the training have more information. So this is a use case that doesn't require a lot of cycling. But this is just one use case. We are working on, of course, endurance is something that this technology is, we are working a lot to improve because our main application we'd like to have is targeted for non-volatile memory. And for non-volatile memory, of course, you will need a significant amount of cycling, at least 10K, 100K. That should be acceptable. And this is
Okay.
also feasible with this technology.
Yeah, I guess so. One last question, if you may, if you allow me to ask.
Sure.
Okay, so I see the power, the total power is lesser compared to other work, but if you see the energy per event is still higher compared to the other demonstrations. So is it related to older technology node from the logic side, since you use 130 nanometer compared to other guys, they use 28 nanometer, or something else is going on?
Yes, this is the amount of energy that ReRAM consume is significantly lower. The switching time is fast, and the voltage level are not high, are also CMOS compatible levels, and you don't need to export the data between the memory and the CPU. So there's no reason for. So most of the energy consumption is due to the overhead of the SPI interface and the logic.
Okay, so sorry, let me clarify my question again. So you showed one chart where you have a comparison for 28 nanometer and 130 nanometer, your work. So I see energy per event is higher for 130 nanometer compared to 28. So is there, I just wanted to understand what is the main reason for that?
Yes, the fact that we are using 130 nanometer versus 28 nanometer or 40 nanometer, that can be the cause. And also we want to reduce the number of spikes that is required for recognition. So we are working that this metric will be improved by at least 30x.
Okay, interesting. That means you do have a scalability when you go down to lower tech nodes. Okay, interesting. Thank you.
Yes. And we will have numbers when we'll present our next demo, which is supposed to be expected in 2021, towards the end of 2021.
Yeah, very interesting. Thank you, Amir. Yeah, interesting work.
Thank you. Thank you, Manan. Thank you, Vinay.
Hello, I have a question here. So in this design, for the synapses, you are using your SIUX based device, RM device. But for the RM, you are using just the CMOS based integrate and fire neuron, right?
Yes.
For the neuron part, you are not using any RM device.
No, the neuron themselves are not used the ReRAM devices. They are the logic.
Right. So the integration is basically the RM based synapses with the pure CMOS based neuron circuits.
Yes, CMOS and the integrate and fire and the acquisition, the rerun store the weight. The rerun is the array that stores the synaptic weights.
Yes.
Hopefully, in the future, we'll be able to combine them also with logic, but there's still time for that.
Do you think at a larger, like in a larger array, these membrane capacitors, the size can become a problem in larger array?
You mean higher capacity?
No, the capacitance that we are using in the neuron as a membrane capacitor. So if we want to achieve a larger integration density, so might be it might pose some problem in a larger array size.
We don't have any information for that, so it's something that we'll have to check. But I think when we are now working on the new design, probably we will be able to address these issues, because the new design will be much more scalable.
Right. And one more question also, like you mentioned, it is offline training using back propagation. So are you also, I mean, have you tried some online on-chip learning mechanisms also with your these designs, or is it possible with the same design?
Well, here, not in this demo. In this demo, we wanted to demonstrate to develop the spiking neural network, the spike decoding, and thing like that. But we did not do online learning. We would like to do it, but we wanted to have this demonstration ready. So this one did not include online learning.
Okay. Thank you. Thank you for your answer.
So thank you once again, Dr. Amit. Thank you so much. Now I would like to call Dr. Anjan Kumar from IIT Hyderabad for oral presentation. So Anjan Kumar, are you there?
Yes, yes. Can you
Okay.
hear me?
Yeah. Now you can start.
Okay.
Okay.
Hello. Can I start now? Hello.
You can start.
But you can't. The downscaling of transistor is assumed to come to an end within the next years, and the semiconductor non-volatile memories are facing the same physical downscaling challenges. Therefore, it is necessary to consider a new computing paradigm and a new memory concept. So most of the conventional ARM technology devices are by the application of high voltage and current. But here we choose a multifunctional material, and we try to operate a multiphoric based device in the presence of magnetic field, because multiphoric is a multifunctional material because of its multifunctional properties, like it possesses more than two ferroic orders simultaneously, single order in a single phase material. So it is a registered random access memory. It is a it is a where a dielectric material is sandwiched between two electrodes, and and it is one of the promising candidate for the future non-volatile memory applications. So why RAM is important? Because of low power consumption, and it have a very good endurance at the long retention, and with have a large memory density. It have very fast polar beam, and one of the very good property of this, it have the multi-level storage capacity. Then how we can explain this one means most of the resistive random access memory with the application of voltage, the device fluctuates the resistance state from means high resistance to low resistance state. The process is called the set, and whenever the device is returned back to low resistance to high resistance state, the process is called a reset. And the two types of resistive switching is there. One is unipolar, where a single voltage required to switch the resistance state. Similarly, when both polarity voltage required to switch different state from different resistance state, the system is called bipolar resistive switching. So we used multiphoric based iron devices because multiphoric is the material which is possess more than two ferroic atoms simultaneously in a single phase, and it has several many would effects like visualization. It has magnetorestriction, it has ferromagnetism, and it has ferricity. So by the using of magnetic coupling, we try to develop a memory device and how it behaves. That has been studied through different IV curves. So we choose bismuth ferrite as a our prime the parent material, where it is a source excellent multiferric metal at room temperature. And it have oxygen vacancies. So this type of device mostly operate through the formation and rupture of the conducting filaments. So the XRT results suggest the material is a single phase with a uniform film deposition, and the material thickness we just try to fix with 420 nanometer. And the concept is like this: most of the rhombohedral type of ferroelectrics having three type of switching: 180, 71, and 119. 109. That means when a domain, ferroelectric domain, start to switch, it start first it switches from 71, then after that it possesses 109 switching. When that 180-degree domain is completed through two different states. That means different polarization state, and as it is a multiferrous material, so both electrical and magnetic properties simultaneously can be tuned by the application of any of the external parameters. It is either its magnetic field or it is electric field. Then we studied its. Then for our material also we studied PFM images, and we found it have three existing domain structure: 180, 71, 109 domain, and also it shows the material have very all the phase and the amplitude results suggest it have very material. Then the device characteristic has been studied to different IV curves. The material initially records a forming voltage of 9 voltage to achieve the high resistance state. Then the device shows at a particular voltage it show low resistance state, and at a negative voltage it shows means again come back to the original configuration. That means the device shows a systematic resistive bipolar resistive switching characteristics. The existence of registration effect in the material is further examined through conducting AFM. The voltage with the positive voltage return suggests the complete switch when the device is in application of positive voltage. Similarly, when you apply negative voltage, the device return back to original state, and that complete switching of the current suggests the existence of the resistive switching in multiferric based BFO compound. Again, we tried this system in presence of electromagnetic system, and it is found that, and we applied both perpendicular and parallel magnetic field with the with two electric field, and it's found that with increase in the with increase the voltage, the threshold voltage start increasing towards the higher voltage, and it is due to the application when we applied a perpendicular field to the electric field, and the Lorentz force is, appears, and which opposes the which delay the moments switching process from ether state to LR state. Similarly, the magnetoelectric effect of the BFO. It is found we also studied that magnetoelectric coupling in terms of voltage. When the magnetic field increase, the alpha value of BFO is increasing systematically, which is also found in our device trace. So both the Lorentz force and magnetoelectric effect of the BFO responsible for the delaying the switching from high resistance to low resistance. Similarly, the Endorse characteristic has been examined for 100 testing cycles for the material, and it is found that it is stable, and the on-off ratio is found around 12, and the cumulative probability study studied that the device possesses a stable configuration at the low resistance state and very minimal unstable when we switch to the high resistance state. And similarly, the device also tested at a very different magnetic field, and we intentionally remove the magnetic field to check what are the means exact immediation effect when we remove the magnetic field. And it is found that the magnetic field, when we remove it return to the configuration, original configuration. That means after we remove the magnetic field, it did not affect any any states. But with increase the magnetic field, it is found that the resistance of the both HRS and LS increase systematically with increasing due to the presence of the Lorentz force and magnetoelectric of the BFO. The on-off ratio they degrade from 12.2 to 10, which is the on-off ratio is found is not that much of good as conventional RM device, but still this technique may be useful for the further future multifunctional operations. Similarly, the conduction mechanism of the device at LRS the LRS and SRS has been studied, and it is found the two types of at low resistance ohmic resistance and high resistance. This SCLC conducting mechanism plays a crucial role. Similarly, with increasing voltage, the number of injected charge carrier are larger than the smaller than thermally generated charge carrier. So the entire current is unable to pass through the device. But when we apply some high voltage, the traps in the film is slowly filled, completely filled, and the current will enter for the device suffer a steep increase in current and jump to the low resistance state. And at that moment, the injected charge carrier dominate over the thermally generated charge. Similarly, the same process also occurs for the negative bias. And the intrinsic electric and magnetic intrinsic properties of the HRS and LRS state has been investigated by using resistance effect, and it's found that with increase in the magnetic field, and the impedance value is increases with increase in the magnetic field due to the resistance effect. And also, if you find at HRS that the impedance value is found in mega ohm, and at LRS it is found in kilo ohm, the large degradation of the device suggests the existence of the process, the its effect of the resistive switching mechanism. Similarly, the oxygen vacancy related has been studied with XPS analysis, and it's found whenever we
Sorry
apply
to
positive
interrupt
voltage, the
you.
conducting field.
So, can
Yes,
you hold on? Ankur Saxena, the participant, can you mute your mic? Ankur Saxena, can you hear me? Supriyo, can you put him on mute?
That thing is not visible there.
Ankur Saxena.
Yeah, he's out now.
Okay. Please continue. Thank you.
Okay, so with application of positive, a conducting filament has been created through the dielectric layer. But when you apply the negative voltage, the oxygen vacancies move to the cathode side, and a conductive filament breaks down as the device is restored at HRS state. Similarly, we also studied that this FECM images, and it is found that there is no diffusion in the material, so that the complete switching mechanism is performed through the oxygen vacancy conducting filaments. Similarly, level resistive switching has been studied through different pulse width and pulse height modulation. In the first case, we studied means we fixed the plus 3 for the LR state. Similarly, minus 3 voltage is applied to achieve the different HR state. With and also we tuned systematically the pulse width of the device, and it's found that with increasing the pulse width, the resistance of the device increases systematically, which suggests the which is one of the which is one of the property of the multi-state memory application. And with increasing the time, frequency is decreases, and also which decreases hopping of charge carrier, and that increases decreases the conductivity and increases the resistance of the material. So that's why we found higher resistance in with increase in the pulse height, sorry, pulse width. Similarly, whenever we increase the pulse height, it takes a larger time to break the filament. Similarly, for pulse height, we apply plus 3 volt to the LR state. Similarly, different from minus 3 volt to minus 5 volt voltage, we operate to achieve HR state. Similarly, it is found that with increasing in the pulse height amplitude, it is the resistance will increase automatically, and multiple resistance states. And at whenever we increase the voltage, more number of oxygen vacancies oxygen ions migrate driven from the interface, and which is delay the breaking the conductive filament between the two electrodes through the dielectric layer. Similarly, when the device is placed in the magnetic field, similarly some multi-level state has been achieved. And so we just we by using pulse width, pulse height, and also in terms of whenever we place this device in the magnetic field, it shows various resistance state. And this resistance state, as it is multi-level state, so each state can be useful for the multi-level synaptic type numeric computing device. Till now, we did not try this one, but due to this pandemic. But as this from what was the result we obtained, it is promising for the neuromorphic computing devices. And this is summary. So we developed a multifaric based multi-level RAM device. So discrete resistive state has been achieved by modulating the magnetic field, pulse width, and pulse results are the reproducible, controllable, and non-degradable. And the device can be used for possibly multi-level RM application, and also it can be used for the remote way application. In the it has the application in the multi-week data storage may have, and also may have the application and application. Thanks for that.
So thank you, Amir. So participant, please, if there is any query, then you can ask here in the chat box or live. You can ask. So I think there is a query from Sanjay Kumar. What is the thickness of BFO layer?
So we put 420 nanometer. As it is whole gel film, so we just check average means around 410 to 420 nanometer.
Okay.
I have one question. You have shown that the R1 by R off ratio is up to 100 cycles, and in other cases it's 20 cycles. Is it the maximum endurance of your device, or it can go beyond than that? Yeah, this one.
Here, sir, as means a device is means here with no magnetic field.